So we're very proud and very honoured to have Dr. Dietmar Pilz, who's the ESA Director of Technology, Engineering Quality. He's the head of the ESA Estec establishment, and he's been kind enough to help let us host our event here today. Dr. Pilz is a recent addition to the ESA family, and he took up his role in May 2023. He has over 20 years of professional experience in the European and international aerospace industry, in various engineering and program management positions in the defence and security sectors of the space community. He joined ESA from Airbus Defence and Space, based in Immenstadt, Germany, where he was the head of space, chief engineering and products, as well as the head of site for Friedrichshafen, I think I said that right, involved in all Airbus space programs and hence many ESA projects. So, Dr. Pilz, floor is yours. Thank you so much.
Good morning. Thank you very much. Good morning, everyone. I would like to welcome you. It's a little bit strange. Unfortunately, I cannot be at Estec right now. As you might see, I am at home right now, and therefore I have to host you from outside of Estec for Estec. So that's a little bit of a strange situation. The first time that I do this. Nevertheless, I would like to say welcome to this system engineering symposium at Estec in Nordwijk. My name is Dietmar Pilz. As was just presented, I am since 1st of May, not just less than 100 days in my new position as head of Director of Technology, Engineering and Quality, and as the head of establishment at Estec, where I welcome you as the host today. Looking forward to this symposium. I was asked before to say a couple of words regarding the importance of system engineering, but nobody would have to tell me that. What has not been mentioned, the last 4 years in Airbus, I was responsible for the system engineers, for what we call chief engineers, for the last 3 years of all Airbus space programs, and therefore I know very well the importance of system engineering and of the system engineers themselves. I'm always sad, you know, the system engineers are having to make the largest trade-offs. Any mistake by a system engineer has much more impact than if you do it on a lower detail level. So therefore, system engineering is crucial. System engineering is crucial for making the right decisions, the right trade-offs, and particularly also the trade-offs between different performance parameters, requirements, but also on cost and schedule. And I think that is what is in that seminar. I myself, I'm not an alumni of this particular system engineering course, but I have been at a course some 20 years ago, pretty much, which was later on called inside Airbus the SAQ, the System Engineering Qualification Course, SAQ. And I have to say that was a fantastic experience. Not only did we learn what is important for system engineering in terms of requirements, verification, we discussed about agile development at this time already, the V model, the way how things are verified and qualified, but also the importance of being a leader as system engineer, because you always have to lead and convince people of your decisions. So there's also a number of soft skills required in order to lead the project teams and also justify and explain your decisions and how you made the trade-offs. So again, for me, system engineering is very vital. It's probably the most vital role, not only in space, but throughout space or beyond space. And therefore, since it is a system engineering is an engineering role, it is also something that is absolutely inherent and omnipresent and vital for Estec. As you know, Estec is the engineering heart of ESA, with probably some of the most brilliant engineers in Europe in space, and therefore obviously also super important to have and to breed and develop the system engineers of our fantastic great missions that we are flying and launching, as we did, for example, 2 weeks ago for Euclid. So there is definitely a clear sense in me seeing the importance of this, and all the more I think this is a great opportunity to show this in such a field of solar power or energy resourcing as we do today. I think we all don't have to repeat how important it is to have different sources of energy and not carbonized energy production, but energy production that is obviously not producing CO2. Solar power energy might be one of the sources. We need to explore this. We need to see whether we can benefit from this on Earth. And then once again, you start, of course, with a system engineering exercise to figure out the right compromise between cost, schedule, feasibility, but also on the other hand, with the most possible power output of that source. So I think that is a fantastic and very important use case that you're looking at here today. And I know that Sanjay will give a very interesting and deep first introduction into the topic in one area, and the other one, which was just on the slides right now. Of course, I know that yesterday was already a presentation on solar power for our lunar endeavors, where ESA is also quite involved, and you know all of this, and same thing. We need also power on the moon. I think that's one thing, but again, the second point is probably we need also power on Earth, and therefore we need to exploit and need to see and discover whether solar power energy could be something that we can use also to overcome our energy crisis that we're still clearly having right now. With all of this, once again, welcome to Estec. Sorry I cannot be there. I would have loved to be there. And would love to in brief the atmosphere of excellent former and current and trainees of system engineers, which is not possible, but I'm still sure that you will have a fantastic and great and very informative, but also networking and an excellent event and symposium today. And with this, I once again wish you a very successful symposium. Enjoy Estec, which I cannot, and I wish you all the best for today. And with this, I would go back to, I think it's John.
Thank you, Dietmar. No, thank you so much. That's much appreciated and very kind words. Okay. So next we're going to have a few words from the SpaceTech academic lead and director. So there's two gentlemen we're very grateful to introduce today. We've got Professor Franz Teschl, who's the academic program lead for SpaceTech. He studied telecommunication.
Wait. Frank needs to present.
Say again?
Frank needs to present. And Wiley.
Franz needs to present, you mean?
What?
I'm introducing Franz. Sorry.
I'm not really.
He's German, Jose. He's not British, you know. So Franz let's get this right. Apologies if we get your name wrong today, Franz. Studied telecommunication engineering at Graz University of Technology in Austria, obtaining his master's and PhD degrees in 2001 and 2005, respectively. Dr. Teschl has been a key researcher in several ESA and Estec activities, field experiments to study satellite to indoor and satellite to mobile propagation effects, as well as working on ESA nanosatellite missions. Since 2012, he is an Austrian delegate in the SG3. Franz Teschl is the co-author of more than 40 papers in international journals and conference proceedings in these areas. Did you want to speak now, Franz, or? Yeah, please come to the stage. You can use this one as well if you like.
Okay, thank you, and good morning. A warm welcome also from my side and from TUGraz. So, as we've heard, I'm working in the field of telecommunications, but I'm also a teacher at TUGraz in the field of electrical engineering. And whenever I talk to students and whenever students approach us, they often, and most of the time, within minutes, the topic turns to energy. This is a topic that students are interested. Do we use it efficiently? Where do the energy come from? How we can collect energy? And this is a topic that is so interesting for so many students. And that's why I'm so happy that today we are talking about one way how we can potentially collect energy. And I'm so happy that the students of this year's and last year's class of SpaceTech also have a focus on this topic. And recently I've learned that when all the energy that humankind needs in 1 year could be collected from the sun within no time. And that's why I'm very proud that I can stand here in front of you in the name of TUGraz, and that we can present you together with SpaceTech TUGraz, ESA partners, and also our alumni organization, this program. And myself, I'm looking forward also to hearing all these presentations, because I think if I would convey these answers back to my students, this would be certainly the answers or the ideas that they want to hear. And so with this, I am looking forward to an interesting day, and I would like to thank especially our alumni organization, Jose and John, for organizing this event. Thank you.
Thank you, Professor Teschl. So our next guest today is Dr. Wiley Larson. Wiley Larson received his doctorate from the Texas A&M University in Space Systems in 1988. He's an experienced leader and internationally recognized author and editor in space-related development, operations, education, and training. Dr. Larson served in the Air Force as a GPS spacecraft engineer, spacecraft launch controller, flight test engineer, spacecraft program manager, and associate professor in astronautics. He is currently contributing to the US space efforts by creating an integrated set of 18+ published books detailing how to design, develop, launch, and operate space systems. Dr. Larson continues to work with NASA, ESA, CNES, DLR, and many other national and international corporations as a consultant, educator, and mentor, and remains an active member of the International Academy of Astronautics and a prolific author, as I think many of us all know. Oh, and by the way, in his spare time, he's the director of SpaceTech. So, Dr. Larson, the floor is yours. I'm just going to switch to the presentation here locally, if I can. That's good. Okay. Apologies.
Right,
Carry on.
Thank you. Thank you. Well, first off, I'm really proud to be here as well. And this bit is about really these gents, these 10 gentlemen that have been through a lot over the last year and a half. And I want to share a photo if I can. Not quite there. So I'm not seeing it change here, but I want that one. Right here. If you notice, they look really happy. And I guess if you would, please stand up so we can distinguish you from the rest. Here, if you would. Come on, Mirren. And so my guess is your classmates stayed up too late last night? Or they're online, right? They're probably here. The thing I notice is these guys are at least a few centimeters taller now. The weight of SpaceTech is off their shoulders. And so I'd like to just give them a round. And this is their org chart for Lunar Spark. And all I'd say here is they were good, and some of us can expect to be working for them soon. So who's that CEO there? Could I submit a resume, please? Yeah. For others that don't know SpaceTech, I know we got on you guys for looking at the screen, but that's a really convenient place to look, actually. So think about project management, mission design, space systems, engineering, business engineering, leadership and teams. The coaching is phenomenal. And I think the one thing that distinguishes SpaceTech from most of those master's programs out there is the Coach Central Case Project, because it's learn by doing. Petra, you're here, probably more scars per week than you'd get on the job. And so many years of experience in terms of scars. And then hardcore navigation, Earth observation, human spaceflight. And then, of course, the thing that's looming over this group is their thesis. And they've got that to go, but they're aspiring to be alumni as well. And hopefully they'll get there. So with that, just wanted to talk a little bit about how things changed. I think it was 1997 when we did our very first graduation. That group paid 18,000 euros. They had a one-year program, same fundamental lectures, certainly a CCP, and no thesis. And of course, this group, 18 months, a Master of Engineering degree, starting 2024, a little longer program to allow for development of the thesis, so there's not so much pressure trying to get both done at the same time. You see 11 courses in 23, 18 courses in 24. That's just a rearranging of how we account for CCP in the courses. So you get more credit for what you do in CCP. And then the price went up just a little bit. So that's a program hard to get into, but hard to get out of sometimes too. So there's a schedule. I want to read this. So Peter Van Wert, I copied your approach. And last night while you were all out there having fun, I was slaving away with Chat GPT. Slaving away for maybe 15 minutes. But if you read this, I loved what it came up with. So in the realm of cosmic dreams, where stars ignite their golden beams, a group of visionaries rise, bound by bonds that touch the skies. That's you guys, right? And then it went on and it picked on each one of you. And I just think it came together very nicely. And at the bottom, together they form an alumni band of Lunar Spark's illustrious hand. And let's see what's next. Through the eons, they'll pioneer beam space electricity crystal clear, innovating with relentless might to shape a future bathed in light. So that was it. And then I took a look at your executive summary again, and I put some keywords into ChatGPT, and it took about 5 minutes, and I got your executive summary. So it was easy here, but it's amazing. You could almost take Solar Harvester out and put your name in. The difference is you did the work, and you probably showed up here already. Who knows? But that's pretty much all I have at this point. I just say congratulations and thank you, alumni.
Let me remove this. Good. So, thank you, Professor Teschl and Dr. Larson. So our keynote speaker is coming next. But before I introduce the bio of Dr. That's wrong, actually. It's Vijendran. Sorry, Sanjay, if I spelled your last name wrong there. I'm in trouble already. But I just want to give you a little story, because as part of the organization of the symposium, we get a topic. We get a topic towards the end of last year. So we're panicking around, running around, trying to organize, trying to find out a little bit about the topic in our ignorance. And I admit, completely ignorant of space-based solar power. But we learn a few things talking to the potential speakers, presenters, reading papers online. Now, I'm a security guy, so we tend to work on a glass half empty, a bit of a realistic, pragmatic view, I like to say, but probably a bit more, let's say, a healthy dose of cynicism. And I was quite, let's say, looking at the scale, looking at the size of the challenge. Orders of magnitude, larger vehicles in space we'd have to launch, completely different mindsets. I couldn't get my head around it. For me, it was just too big a challenge. I was lucky enough to spend a long lunch with Sanjay. And at the end of that lunch, I'm sold, completely and utterly sold. So I think at the end of this keynote speech, I hope those who are like me, maybe don't know a little bit about it, know a little bit, enough to be dangerous. I hope you take a gram away of the passion that you see that Dr. Vijendran has. And through the day, I think at the end of the day, you too will be sold. I'm looking forward to working on Sanjay's team on his mega project. So, Sanjay Vijendran is ESA's lead for the Solaris R&D initiative on space-based solar power for terrestrial needs. Previously, Dr. Vijendran has served for more than a decade in ESA's Mars Robotic Exploration Program, another mega program, planning and implementing the studies and technology development activities that prepare for future European robotic missions to Mars. He was instrumental in establishing the 2019 international partnership between ESA and NASA on the multi-mission Mars Sample Return Program. And this is aiming to robotically return samples from Mars to Earth for the first time in the next decade. So again, another mega challenge, amazing technology behind it. He has also the privilege of working as payload development scientist on the NASA Phoenix Mars mission, which landed on Mars in 2008. Sanjay holds a PhD in semiconductor physics from the University of Cambridge and has published widely on semiconductor devices and Mars exploration missions and technology. It is with great pleasure that we welcome from the beach, because we've been lucky enough to drag Sanjay away from his holiday today. So let's welcome Sanjay to the stage to address his topic on energy and space. Dr. Vijendran, over to you.
Thank you very much, John. Good morning, everyone. I hope you can hear me okay. So first of all, thanks very much to John and the organizers of SpaceTech for this opportunity to address you all on this very important topic of space-based energy for Earth. I'm sorry I can't be there at Estec today. As John said, I'm on leave, but this topic is very close to my heart now, and I consider it important enough to take the time today to share with you what ESA is doing on space-based solar power right now, and hopefully for those of you who are not familiar with the topic and its potential for helping with the climate crisis and our energy crisis here on Earth, I hope you will, by the end of this talk, also be similarly convinced as we are that it is important enough that we look into the feasibility of this capability to see if it can actually help address our biggest concerns. So I will now share my presentation. Please let me know when you can see it.
We see your presenter, not the full screen, if you're trying to share the full screen.
Okay. Let me see.
That'll be under slideshow.
Yeah, let me just go to play from start. Are you seeing the full screen?
Yeah, that's good. That's good.
Okay. So the talk is titled "Energy from Space," and I think John has chosen this nice title, "The Compelling Need for Space-Based Solar Power and ESA Solaris Initiative." So the first aspect is indeed the important one, understanding why we should try to look into something as mentioned as challenging as space-based solar power for Earth is, and to really understand that, the why we should go down this road or try to go down this road, one must first understand the big challenge, the big problem we have, which is the climate crisis and the energy crisis, and to understand that challenge is enormous. And I hope I will be able to spend a few minutes with you today explaining where we are with that and why space-based solar power is so important in that conversation. So first of all, the vision. Where do we want to get to? I think we can all agree that we would wish to have energy available to humanity that has these characteristics, that it's clean, it's abundant, affordable, secure, and available to everyone on Earth. We're very far away from this today, as you're well aware, in terms of the cleanliness of the energy. 80% of the energy used by humanity is still coming from fossil fuels. It is not abundant. Fossil fuels, we know, will run out at some point. It's the source of the biggest part of the climate crisis. It's not affordable to many people already now, and it's only going to become increasingly unaffordable in the future, and certainly not secure in many parts of the world, and not available. So this is where we want to get to. That's the vision. Where we are is right here. It's an urgent problem that we have, not only for the climate crisis, which is the biggest issue, but of course the energy security aspect, especially here in Europe. We've come to realize in the last year that we cannot take that for granted either. So these two major issues for our continent, but globally as well, are very interdependent and inextricably linked. And we do know that there is a path towards a cleaner future, to have energy available to everyone. And it's going to be relying on a mix of energy sources. There is no silver bullet amongst all of these energy sources that you see on the screen here, which are the clean and low energy sources that we have today: wind, terrestrial solar, hydro, and nuclear power. These are the ones that are already being scaled up, already reached a reasonably significant scale in terms of its contribution to our energy needs, and being scaled up as fast as possible, especially wind and solar. But they each have their benefits and their drawbacks. They have scalability issues, for example, hydropower or even nuclear power in some areas. There are public perception issues with increasing the scale of that application. There's the availability of the resource, solar and wind being the obvious ones. They're not available at all times of the year or in all geographies equally. So while we know that these sources we have today, these existing technologies need to be scaled up, they still come with sufficient challenges that make our wish and our goal to get to net zero, and that's a European goal, but also shared by many countries in the world, to get to net zero by 2050, meaning we're emitting no more carbon than we are sinking annually in the world, around the world, to try to arrest the climate crisis. This challenge is extremely great. And I think this is very important for us to understand, for you to understand, that this challenge of getting to a decarbonized power system on the planet, when we're having to scale up our electricity use by more than a factor of 2 or 3, as you can see from this chart from the International Energy Agency, their net zero roadmap has us going from just over 20,000, 25,000 terawatt hours per year of electricity supply in the early 2020s, up to 70,000 terawatt hours in 2050, with most of this being provided by solar PV and wind. So not only does electricity use have to increase by many factors, it has to also be decarbonized at the same time as this huge increase that is expected around the world. And this is a humongous challenge. There are pathways that you would have seen, like this one from the IEA, but also from the EU and other organizations, have worked out what would need to be done to get to 2050 in terms of scaling up the different energy sources that we have. But nobody, I would argue, nobody has a really credible pathway to really getting to net zero today with the scale of the challenges and the disadvantages of the technologies that we have available today, and even the ones that are being developed in the future. So on top of this huge challenge of scaling up these different energy sources, and you might notice that hydro and renewables have to be scaled up by at least a factor of 2. Nuclear is a line there that also has to be doubled over the next 30 years. And fossil fuels with carbon capture are even featuring in 2050 at some level. And this is to show that there is no single source that is going to solve the problem to get us there. And even solar and wind, which everyone expects to be the biggest source and has all the advantages of being low cost already now, and relatively easy to scale up, is insufficient on their own. And you need a substantial amount of the power provision, the electricity provision, coming from reliable, relatively weather-independent, stable sources like hydro, biomass, nuclear. And so this points to the challenge that we have in that intermittent power sources have their disadvantages to supply a highly reliable 24/7 supply of power, which is how we use power here on Earth right now. And to get to net zero, the IEA expects that this increase of these sources of generation need to still be combined with demand side management, meaning human beings changing, our societies changing how and when we use our energy to help make this challenge not too great to be achieved. We have to still operate flexible power sources, meaning power sources that can be turned on and off when energy is needed, because solar and wind disappear at certain times of the day or certain seasons. And there needs to be a vast increase of battery storage as well to help balance some of this intermittency. So even with all of these new challenges, problems that haven't been solved yet, the big challenge of using the energy sources here still exist. So when we've looked at this from the ESA side in the last few years and asked ourselves if space can do something more to help with this enormous challenge that the world has, we've tried to understand if we can make this transition less painful. Can we accelerate it and give it a better chance of achieving its goals by 2050? So the question is, can space really help plug the gap of clean energy that the world really needs? So we would argue that yes, there is the potential to do that using a technology called space-based solar power, delivering solar energy from space down to the Earth. This is not a new concept. It's been around for decades. It started in science fiction by Isaac Asimov. It's been looked at from a technical point of view from the late 60s. It was developed quite substantially on paper by NASA and others in the 1970s during the oil crisis that existed at that time, when people had to, around the world, the West was scrambling to look for alternative sources to oil and gas because of the oil crisis from the Middle East at that time. And space-based solar power was investigated quite deeply, and the clear benefits of space-based solar power, which you see on the bottom of this slide, that it's green, it's 24/7 weather independent, and that's absolutely key. It can be affordable once it's deployed at scale. It's scalable in the sense that there's enough room up in Earth orbit to put thousands of these satellites eventually to be able to provide a good fraction, if not all, of the world's future electricity needs. It's secure in the sense that the fuel is there available to everyone coming from the sun. It is not fueled by a source of material that needs to be found somewhere on Earth and that's limited in terms of access, and it's available to everyone, geography independent around the planet. So it's got this mix of very enviable characteristics for an energy source, that if you could have all of this in one, plus one that I haven't shown on this slide, the ability to move that energy geographically over vast distances essentially instantaneously. And that is absolutely unique to space-based solar power. No other energy source, not even fusion, can do that. Can send power from, say, Dublin 1 minute and send from the same power-producing asset, that same satellite, send power across to Berlin or down to Cape Town in South Africa, all because you're placing these satellites in a very high Earth orbit, and you can use beam steering to essentially move that power beam from one place to another over vast distances with no loss at all. So these are the good aspects of space-based solar power. Now, what are we exactly talking about? For those who are not familiar with space-based solar power, it's actually broken down into relatively simple steps conceptually, 5 of them. We get sunlight up in space. We capture it with essentially a solar farm in space. So think about taking one of those solar farms in the countryside that you drive by and putting that huge structure up in space, capturing the sunlight and converting it to electricity, just the way we do now on satellites or even on the ground. And then comes the tricky part, the little bit of magic that's required, and the aspect which many people consider the science fiction part of the whole thing. How to get that electricity you've generated in orbit at the levels of hundreds of megawatts or even gigawatts down to the ground safely and accurately, continuously, so that it can be used. And that's when we use a technology called power beaming. That's putting it through, converting it to another form, typically microwave, radio frequencies, but it can also be optical lasers or reflected sunlight, sending that power down to the ground to a receiver, which receives it, does the power conversion back into electricity and feeds that into the grid. So 5 steps, conceptually relatively easy to understand, but the big challenge is how can we actually realize this in an engineering level? Now, when I mention microwaves and radio frequencies, that is the preferred choice for most of the architectures for people who have studied this in the past, because you are able to send that through the Earth's atmosphere with almost no loss, and it can pass through clouds and rain and weather, thus giving you the chance to have a truly 24/7 weather independent power source available this way. Another way to get the power down is either through optical lasers or simply reflecting the sunlight using giant mirrors in space down onto existing solar farms, which we know are going to be mushrooming up all over the world as we move towards net zero. But they don't operate at night, for example. And if you had a giant mirror in space, able to reflect natural sunlight down to these solar farms, either during the day or especially at night, you're able to use existing infrastructure, which is laying dormant, and generate more energy, generate more revenue from the commercial side as well. So here, again, 5 steps, but even more simply, instead of having to have solar arrays and conversion systems into microwaves or lasers, here you're just having a large structure, can be very thin and flexible, that reflects sunlight, essentially a mirror, down onto the ground for the conversion to happen with the existing infrastructure. So ESA is looking at both of these different ways of getting power down from space, because they each have their own benefits and challenges. So what will this take to realize? So this is where we go from the relatively easy to understand to a completely different level to realize. And one of the main, probably the biggest challenge to space-based solar power has always been for Earth, the application has to be at a very large scale. So we're just providing megawatt or tens of megawatts of power for Earth application, especially if you're trying to address the climate crisis. Here we want to provide a good fraction of Europe's energy needs in the time frame that we're talking about in the next 30 years, but ultimately the world's energy needs in the longer term. So we have to provide from each of these structures in space at least hundreds of megawatts, if not gigawatts of power, which is typical for a large fossil fuel station or a nuclear power station. So here's an example architecture coming from the US, where the design provides 2 gigawatts of power into the grid continuously. So this is not the power that's generated on the spacecraft, but this is what's actually delivered into the grid to the customers. 2 gigawatts continuously, 24 hours a day, 7 days a week. Now, to do this, there are going to be losses along the way because of the different conversions that happen. In this case, we're converting from sunlight into electricity and then into 2.45 gigahertz radio frequencies and beaming that down to the Earth and doing some conversions back to electricity. So you're going to lose a bit more than 50% of this along the way. So you have to collect at least twice as much in terms of sunlight power in space. So no matter how you cut it, physics limits you, nature limits you to 1.4 kilowatts per square meter of power from the sun at the distance of the Earth. So that means if you want gigawatts of power collection, you're going to have square kilometers of solar array or collection area up in orbit. And that leads you to thousands of tons of space hardware has to be put up into space in order to make this happen. Thousands of tons, in this example, 7,000 metric tons of space hardware, and dimensions of the order of kilometers. So as I mentioned, you need something like 10 or more square kilometers of collection area. We're talking about dimensionally a few kilometers in diameter for some of these elements of the solar power satellite. And then on the ground, because you're putting the satellite typically up in geostationary orbit at 36,000 kilometers, the beam, if you're using a microwave beam, is going to spread out somewhat, even with the best focusing you can do that physics allows. You're going to have a receiving area, if you want to collect all of the power, in the order of a few kilometers, up to 10 kilometers in diameter. So relatively large structures on the Earth as well in terms of dimensions, but they can be quite simple because the collection devices, little Schottky diodes, can be relatively simple compared to solar panels on the ground. But still, importantly, you need to have a large contiguous area on the ground to collect all of this energy. That's the ground station part, which then connects up into the grid. What would this look like for the mirror concept? So here, as I said, it could be a lot more lightweight than the solar array option, but you still need to have, you can't get away from the fact that these need to be large areas. So you still need these kilometer scale structures, but they can be much lighter weight to reflect the sunlight onto the ground. So here you can get gigawatt scale power down to the ground, but because of optical physics limitations, you're unable to put these structures up in geostationary orbit over a single solar farm and try to get all that power down in a reasonable beam spot. that is similar in size to the solar farm. And so the concepts for these structures tend to be in lower orbits, something like 1,000 kilometers. Of course, that means that you're not going to be stationary over your solar farm. You're going to be passing over relatively swiftly. So if you want to have quasi baseload or continuous power, then you're going to need to have a train of these satellites in orbit so that each one can hand off from one to the other as it passes over for a certain amount of time, delivering the power down to the solar farm below. Now, that's the space side of things. On the ground, you need these large structures, as I mentioned, which take up some area. But this chart is just trying to show you that compared to other intermittent renewable sources, the areas that are needed are not that great. They are keeping in family, certainly with wind, where in this example, there's a wind farm off the coast of Denmark, which is providing a peak power of 600 megawatts. So that's even less than a gigawatt peak. But of course, we know that that's very variable. And it takes up 130 square kilometers off the coast of Denmark. A 2 gigawatt rectenna, the receiving antenna for space-based solar power, would take up 75 square kilometers, shown in that ellipse down there, a much smaller area, but provide far more energy per year because of its 24/7 continuous nature. So you would we get many orders of you get many factors more energy per year per square kilometer of the receiver on the ground compared to wind and even compared to terrestrial solar, especially in European latitudes where the average amount of sunlight that you are able to get delivering into the grid from a solar farm in Europe is much lower than the amount of energy you'd be able to get from a space-based solar power receiving antenna. I mentioned the ground rectennas can be relatively simple in construction. Here's a picture on the left there, which gives an example of how these rectennas, which are essentially wire meshes that could be laid out over large areas on posts. And if you were to raise these high enough, you have the potential of using the land for other purposes as well, the so-called dual use of the land that these rectennas allow, because the light, rain, everything passes through this wire mesh down underneath. So you can imagine having agriculture below, or indeed even solar panels underneath the rectennas, which can collect sunlight when it's available, but be getting 24/7 additional power from space to the rectenna as well. So we talk about thousands of tons of structures, kilometers size spacecraft. This is, of course, wouldn't be surprised if you're thinking this is science fiction. It has been science fiction, but it need not be science fiction for much longer. And I hope by the end of this talk, you'll be convinced that we may not know for sure if we can do this in the next 10, 20, 30 years, but we should be convinced that we ought to try, because the potential is so great if we are successful. So what are the biggest challenges? As I mentioned, the wireless power transmission is probably the most science fiction aspect of this. And most people don't realize that wireless power transmission is actually a thing. It goes all the way back to Nikola Tesla, no less, more than 100 years ago, who was already thinking about delivering power around the world with wireless power transmission. He wasn't successful at the time, but many people have since then in the US, Japan, Canada, all over the world shown that wireless power transmission using usually phased array antennas at the kilowatt scale and at the kilometer distance scale is possible, has been done. People have flown UAVs, little helicopters, planes. They've done point-to-point transmissions, as shown down there by JPL Goldstone in California, where tens of kilowatts of power was transmitted over more than a kilometer distance. And most recently, US Naval Research Laboratory also demonstrated in 2022 wireless power transmission of just over a kilowatt over a mile distance as well. So it is, the technology is there. It's not just in the lab. It's not just on paper. It's definitely out there being demonstrated. And there are even companies commercializing this. And ESA worked with Airbus in Germany and a startup company from New Zealand called Emerald, who are commercializing this wireless power transmission technology for terrestrial use with the long-term view towards applying this to space-based solar power. So we did a demonstration in Munich last year. Over a distance of 36 meters, we delivered 2 kilowatts of power across that distance. And the key thing was that we collected almost all of the power that was delivered from this 2x2 meter antenna, as you see there on the right-hand side. It was collected 36 meters away by another 2x2 meter receiver. Almost all of that power was collected. So essentially, there was an invisible conductor of power, electrical power, that went across that distance. And we were standing watching this happen just a few meters away, showing that this can also be done very safely in a controllable and accurate way. So that technology is existing. Of course, 2 meters to 36 meters and 2 kilowatts happen to be exactly 1 million times smaller than 36,000 kilometers, that's geostationary orbit, and 2 gigawatts, that's the power we would like to be delivering from into the grid. So we certainly have a long way to go to scale up this technology to where it would be really useful for addressing the climate crisis and our terrestrial needs, but the basic fundamental building blocks are there. Now, the other aspect is how to build such large structures in space. The largest thing we've ever built is the International Space Station, essentially by hand with astronauts, that is 100 meters across, made up of a bunch of large and heavy modules. Here we're talking about a solar farm, so a hypermodular structure, which is large, but made up of lots of similar parts. And these, of course, need to be launched in separate rockets and aggregated in orbit, all the parts, and they need to be put together in space. There's no way to launch such large structures. So in space, robotic assembly is absolutely key to making space-based solar power work. And this is one of the things that made it too challenging in the 70s, when people could only imagine doing this with astronauts without having the robotic technology at that time. But the world has moved on a lot, space technology has moved on, and now we can see that there's a path towards doing this autonomously with fleets of autonomous robots in the next 10, 15 years. And the designs of space-based solar power systems have also matured such that they are now being designed to be buildable in this way in orbit. The other aspect, which was an economic showstopper in the past, was the sheer cost of launching thousands of tons of hardware into space. It wasn't the technical feasibility in the past that people were most concerned about. Really, it was the economic feasibility. It was, how can we do this cheaply enough, affordably enough in terms of construction and capital investment, such that the electricity that we will be selling to the users on Earth would be actually affordable and competitive. And that came down in the past largely to how much it would cost to launch all of this hardware into space. And as you all know, things have really fundamentally changed in the last 15 years on this topic, which is why we are really convinced now is the time that space-based solar power could really become economically feasible, because we've seen this massive drop in launch costs potential from thousands, tens of thousands of euros or dollars per kilo down to potentially hundreds of dollars per kilo, or even less, to low Earth orbit. So if and when, I should say, when Starship finally works, we'll have that existence proof that space-based solar power, at least from a launch perspective, can become economically viable. On the European side, we've not had a business case for any application thus far to actually embark on a heavy lift, reusable, low-cost launcher system, which is why we have not been even trying to develop that. But this application, arguably, space-based solar power, if it were to go ahead and be used for addressing our energy needs, would be that killer app that would drive the need in Europe and other parts of the world to have low-cost reusable launch capabilities. So we see this as offering a big potential, especially for Europe, to develop this capability, which would then be useful for many other things, of course. The final aspect on the economic feasibility, of course, is the cost of the space hardware itself. In the past, space hardware was made in small numbers by hand, essentially, and the cost per kilogram of the hardware was extremely high. If you were just to use those cost references and multiply that by 7,000 metric tons, you would again come to complete economic infeasibility. But we've seen from LEO constellations in the last decade as well, this trend to mass produce satellites on the factory line, duplicate them in the tens of thousands, even in LEO constellations. And this is exactly the mindset, the thinking, the paradigm shift in our industry that we're seeing now that is needed for space-based solar power. We're talking about a structure that's built up of up to 1 million individual parts that are all exactly the same, built on a factory line and then launched up into space. So again, when we're seeing costs coming down to $1,000 per kilo, 1,000 euros per kilo or less of the space hardware, the business case starts to close. So if we can achieve all of this, low-cost launch, low-cost hardware, do the robotic assembly, and start to deploy this, how big a contribution could this actually make to mitigating the climate crisis? I mentioned before, unless we deploy this in large numbers at the gigawatt scale, we're not going to make enough of a dent to really warrant going through all of this effort. So to answer this question, ESA did 2 cost-benefit studies last year with independent contractors to really understand what the benefits of space-based solar power and the cost of space-based solar power in the context of achieving net zero 2050 were. Is this something that could be available in time if we really put our mind and our funds to it to help with getting to net zero? And how much of a difference could that make for Europe in particular? And the long and short of it, from an economic point of view, and my colleague from Fraser Nash later on this morning will talk a bit more about this study. But here, just to give you the snapshot on how the cost would compare once this was deployed at scale. So this example is giving the cost of space-based solar power once you have 10 of these satellites, these duplicated satellites in orbit by 2050. How would this cost, what's called the levelized cost of energy, would it compare with intermittent sources like solar and wind, or another baseload source like nuclear fission power? So what they showed was that there was a wide spread between the 2 studies, and also depending on the assumption on how quickly the technology was going to mature and what your risk level was as an investor. It could be as cheap as 50 euros per megawatt hour, which is definitely comparable with intermittent wind and solar today and in the future. Or it could be as bad as 200 euro per megawatt hour in the worst case, which is worse than all of the others, but still in family with nuclear power. And this was telling us that if we fall somewhere in this range, we have something that can be definitely competitive in the future, certainly with nuclear or with fossil fuels and carbon capture. But even with solar and wind, we're trying to complement those sources, which are going to be scaled up, but they need to be complemented, backed up by a reliable continuous source as well. So there's still a place for sources of energy like nuclear power or space-based solar because of their unique characteristics and their different characteristics to the intermittent sources. The wide range of prices, of course, told us that we don't understand the issue well enough. So there's a lot more work that needs to be done, not just on system studies, but on technology as well, to really understand if the assumptions that we've taken for the cost benefits are the correct ones. And that's really the purpose of our Solaris initiative, as I'll describe in a minute. So coming back to the potential scale of the impact. So these studies also looked at how we could scale up space-based solar power towards 2050 if we had the first prototype station at the gigawatt scale available by 2040. So then using that last decade before 2050 to scale up the systems into many tens of satellites for Europe to provide a good fraction of Europe's energy needs. And what they found was that aiming for something like 600 terawatt hours per year, which is about 10% of Europe's future electricity, clean electricity needs, you'd need something like 50 solar power satellites, each producing gigawatt scale of power into the grid. And if each of these satellites were to displace coal power stations, and recall that that's what we're trying to do here, we're trying to shut down fossil fuel power stations sooner than they otherwise would be if we were relying on the other low carbon green sources with the challenges that they have. And looking around Europe, especially countries like Germany, Poland, and others, where there's a huge amount of coal and gas still being used, they have their challenges to get off the last elements of these fossil fuel sources, even once they've scaled up solar and wind and nuclear to the extent that they can. But if we can do that with space-based solar power, we could be saving something like 600 megatons of CO2 emissions per year by providing just this 10% of Europe's clean energy needs by 2050. So it's a huge impact, and this is the important aspect and the motivating aspect we have at ESA to look at this further, because this is far greater than any impact that other space capabilities can make towards resolving the climate crisis that is available today or being worked on today. So we would argue that there is nothing else that we can do in the next 30 years credibly with space technology that can have as much impact to really address the climate crisis as space-based solar power has. So we do need to understand, we do need to answer the question, can this be done or not? Because the energy sector can see the value if it can be done. So is space-based solar power safe? Naturally, that's an important aspect for all of us to consider. Of course, the public will be interested to know that we've done our due diligence. So one of the key aspects is to ensure that the power density of the power that we're beaming down is low enough that it will be meeting safety regulations, and we are deliberately reducing that to levels that are less than a quarter that of natural sunlight, even, so around 200 watts per square meter. The wavelength in the gigahertz range for the wireless power beaming is known to be non-ionizing. It's similar to Wi-Fi and mobile phones. And we can ensure through safety systems like retrodirective beams that come up from the receiver to the satellite that will help ensure that the satellite's always pointing and switched on only when the satellite's pointing at the receiver itself. Now, there's a whole load of other risks, not just technological, that are associated with space-based solar power that have been identified over the last 40 years by people who worked on it, which I won't go into today. Many big challenges. But the important thing is, despite 4 decades of study and all of these risks, we can see how these risks can eventually be overcome. There are no clear showstoppers that tell us that this is a no-go for this reason or that reason. And that gives us a lot of confidence that it's worth drilling deeper down and understanding just how far we can go with this. Now, we're not alone on this topic. Of course, others around the world are working on it, especially in the US and in China. China have a declared program, a national goal to have a gigawatt scale commercial plant by 2050 in orbit. They have some very substantial ground test facilities already operational, and they plan to put a demonstrator in orbit by 2028 to show how power can be beamed from space to ground. In the US, there are significant activities by the US military, the Air Force, and the Navy. The Air Force Research Laboratory is planning to do a demonstrator in 2025 of space-to-ground power beaming. And Caltech, you may have seen in the news a few weeks ago, announced successful in-space power beaming technology level demonstration that they've done just this year, and also detected some of the power that came from space down onto the ground as well. They're privately funded by donations. But there are other government activities and private activities going on around the world. And in Japan, it's been a part of their basic space policy for a long time, where they've done a steady, low-level technology development work, but are also coming to do their first space-to-ground power demonstration in 2025. So there's a lot of activity, but Europe needs to step up. And this is why we put forward the Solaris proposal at the end of last year to the ESA Ministerial, where we got support for further studies and technology development in a dedicated initiative called Solaris for the next 3 years, up to the end of 2025, to look at all the benefits and feasibility costs and risks in more detail, to raise the awareness amongst all the key stakeholders, especially the energy sector and national governments, who need to be convinced about this as a potential future technology so that they can become prepared to take up the mantle from the government and the institutional side, who can do the R&D. But once this becomes a full development program, this is far too big for ESA, and even the EU is not going to be the people who will deploy this and sell the energy to customers. This will be the private sector eventually. But there's definitely a role for the public sector to start with, eventually transferring over to the energy sector later. We need to establish opportunities for international cooperation, because there are many rules and regulations that need to be established as well internationally to make this work. And we would like to prepare a full development program in Europe by 2025 for a decision at that time whether or not Europe should go ahead with space-based solar power development. So Solaris is about studies and key technology development to really provide hard numbers to many of the assumptions we've taken on paper that make this look promising, but we now need to ground that in reality with technology developments as well as environmental health and safety studies to show that this can be done safely for the Earth environment. Now, when could this be ready? If we go down the nominal path that we see in Europe, this is how it would look. We would complete Solaris by the end of 2025 and hopefully be able to have enough information to make a decision on the next steps. And if a decision was made to go ahead with the full program, we would see a first subscale demonstrator being done by Europe in 2030 at the megawatt scale. And then if that works, scale that up to a pilot plant at the 100 megawatt scale, eventually moving towards the multi-gigawatt by the end of the next decade. Why do we need to do it by then? Of course, we want to help with net zero, so we don't have a lot of time to scale this up. So that's why that drives the need to have that first demonstration no later than the end of the next decade. And this potentially could be accelerated even into a decadal moonshot-like approach if there really was political will and funding to put to that. So just coming to the end here, just to note that we have been talking not just to people in the space sector about this, who have been aware of this technology for a long time, particularly the energy sector, who have been completely unaware of this topic. And it's been totally new to everyone we've been speaking to, from oil and gas, from electricity utilities, the IEA, and others. But after an hour of conversation, after a presentation just like what you've seen today, we have convinced everyone. There hasn't been a single person out of the more than 100 different bilaterals we've had in the last almost 2 years with the energy sector. There hasn't been a single person from the energy sector who said that this is not of any use, that we've got all the solutions, so we don't need this, don't bother. Instead, they've all asked us, when can this be ready? For them, this is like fusion, but fusion that is going to be ready sooner and more likely to be available. So they recognize the value, they recognize the urgency. They don't know whether it's possible, but they look to us in the space industry to show the path to feasibility so that they can then take this up and deploy it at scale once it's ready to do so. So just as a final note before closing, I just want to say that we've just finished a recent study, because the moon was mentioned, looking at how we can use lunar resources for building space-based solar power satellites for the Earth. And why would we want to do that? If this was to be deployed at a large scale, and I'm talking about even beyond 2050, as our energy needs grow around the world, continue to grow, we'll need to deploy more and more stations. The environmental cost of launching thousands of satellites, thousands of launches from the Earth into space to put all of this hardware starts to become quite significant. And if there's a way that we can reduce that environmental impact, then it's certainly something we should be looking into. And this study that we've just completed, which we'll be releasing the results from very soon, has shown that there is a path to industrializing the moon and using lunar resources to build much of the hardware of solar power satellites that are then launched from the lunar surface to Earth orbit and assembled there for providing energy to the Earth in a more sustainable way in the long term. So this gives a really visionary path to why we really should explore the moon and industrialize it for the benefit of the Earth. And I hope it's something that you'll find interesting when you see the results of this. So take-home messages are the challenge to get to net zero extremely great here on Earth with the tools that we have. The recent studies from ESA have shown that orbital solar or energy from space could help with displacing fossil fuel sources. Some limited R&D is going on around the world, but given the potential of space-based solar power, we think a lot more R&D should be done, not just in Europe, but all around the world to really make this happen or to understand whether it is feasible. And that window of opportunity, of course, is closing fast for this to help with the climate crisis. So we need to act now. Thank you very much. Sorry if I went on a bit long there.
So thank you, Dr. Sanjay Vijendran, for that very enlightening and very inspirational talk, I think. So I'm seeing lots of nodding heads around. I think everybody's inspired now. We've got a few minutes for questions. I'll take them from the floor here if anybody has any questions on the floor. Yes, sir, you want to take the microphone? You should just press the, yeah.
Yes. So thanks for this speech. This is essentially my master thesis, so I'm very excited. I have a question because my master thesis is about the economic feasibility of such a system. And you said some ideas of what could be done. I would add to that it might be interesting to make the processes of manufacturing satellites faster and more efficient. Also would help to develop such a system faster.
Yes, so you mean the industrialization of satellite manufacturing, yes, using consumer electronics approaches. Indeed, this is what we're already seeing with things like Starlink and OneWeb, where the industry is applying those principles coming from car manufacturing, consumer electronics manufacturing to satellite hardware, and that's only going to accelerate, I believe, and is absolutely key that is optimized to the extent possible for something like this, because we'll be, a single satellite will need, as I said, a million such solar panels, and we'll be wanting to build at least 5 of this per year in Europe. So it's going to need to be done at a very large scale, and it's a fantastic industrial opportunity for Europe as well, in terms of scaling up high-tech manufacturing across Europe in this area of space-based solar power.
Thank you. From the floor, yes. Take that one, sir.
Hi, this is Leon from SpaceTech. I wonder how the first space demonstrator could look like. So what would be your focus on this when having the opportunity to launch a spacecraft to, test
so
it?
This is still to be looked at in more detail during our running system studies that we have ongoing. So what I didn't mention is that we're running already now within the Solaris initiative 2 pre-phase A system studies on commercial scale solar power satellites, because Europe has not looked at the technical design of these power plants for over 20 years. So we want to have an up-to-date look at that. And we will be concluding these studies at the end of this year. But the last work package is going to give us the first concepts on what should a subscale demonstrator look like, particularly in terms of dimensions and scale. What is the relevant scale of demonstration for the key principles and the technologies that we will need to be able to convince the big stakeholders, particularly the energy sector, that this is now shown to be feasible, but we do need to then scale up. So currently in our roadmap, you might have seen we're thinking of something of the order of megawatt scale, which is already pretty large. But if we want to have to avoid in-space assembly, for example, in 2030, which might be challenging to already have available by then, we could imagine trying to fill up a Starship launcher in terms of total mass, so something like 100 tons worth of mass into orbit, and achieve hundreds of kilowatts or a megawatt scale demonstrator. To make this a really significant demonstrator compared to, say, what the US and Japan are planning to do in the mid-2020s, but also show to the energy sector that, hey, I can deliver a megawatt of power continuously 24/7 to a receiver on the ground. That starts to become very interesting to them compared to, if you just showed a kilowatt of power transmission. So right now, that's the scale we're thinking about. But as I said, the system studies will tell us what should this be, what should the demonstrator really look like to also be achievable in the 2030 timeframe. I hope that answers your question. But the key thing is to show end-to-end that we can go from sunlight to power into the grid safely and accurately.
Yes, thank you.
So yes.
Yes, I have two questions. The first one, you presented also this other alternative technique with mirrors and satellites in LEO. Will this also be covered by Solaris studies? And that's what's my first question. And the second one is, are there any significant technical differences in the solutions that are studied by US, China, Japan, Europe? Or is there a general consensus, I don't know, on the type of, on the range of frequencies, on the receiver, the receiver side? I don't know if there are any big technical differences between the different options. Thanks.
Sure. So on the first question, yes, we're studying with these two parallel contracts I mentioned that we're doing on the system studies right now. One of them, led by Thales Alenia, Italy, is focusing on the microwave power transmission aspect. So that's the gigawatt scale radio frequency in the gigahertz range that you've heard about. The other one, which is led by Arthur D. Little, a management consultancy in Belgium, together with other partners, they are looking at the reflected system concept only. So by the end of this year, we will have a view of what is it really going to take to do both of these power transmission technologies. And we're expecting the reflected one, of course, to be much easier to implement because there's no new technologies involved there. Apart from the large-scale in-orbit assembly, having lightweight mirrors, this was already shown by the Russians. In fact, in the 1990s, they did a demonstration of space mirrors at some tens of meters scale. So we expect that to be easier and quicker to implement. It does have the limitation that light would still be blocked by clouds. So it's not a 24/7 power source in the same way that the microwave transmission is, but because it's easier, it may have niche applications at a smaller scale that are commercially viable in a shorter time frame and demonstrate some of the key aspects that are needed for the longer term 24/7 microwave source. Particularly the heavy lift launcher, low-cost launchers will still be needed, and the lightweight structures as well as the in-orbit assembly would still be needed. So all of these are needed for the long-term goal in any case. This is why we're looking at both of these options, but which way we go for a demonstrator is still to be decided. In terms of the differences for the microwave approach, depending on the different countries that are working on this, the differences are not very large in terms of the technologies, the solar cells, the RF conversion is similar types of devices. The range of frequencies are anywhere between 2 and 10 gigahertz, and that's because that's the window of transparency of the Earth's atmosphere. So that's pretty much fixed by nature. So the big differences are really at the system level. Do you have a bunch of mirrors that reflect onto a solar panel system that one of the architectures have, or do you have direct capture of the sunlight without having mirrors in the way as well? Do you have a helical shape, or do you have some kind of umbrella shape? These are more the differences between the different architectures that are being looked at around the world.
Thank you.
Sir, yes.
Hi, Dr. Sanjay. Thank you for that presentation. It was very interesting. My question is, what is your take on the, for example, serviceability and maintenance of these very large space structures on the long term? Because such a thing will take quite a few years to be built and assembled, but at the same time, it will start to wear out in space. What is your take on this?
Yes, so indeed, we're talking about operating these stations similarly to other solar farms or other power stations. So we're looking at 25, 30 years as a nominal lifetime. So we don't expect that we would be able to have such a structure in space that didn't need some form of maintenance over that time. So again, here, space-based solar power is requiring a fundamental paradigm shift in our industry's thinking of designing things for maintenance, and much further than like the Hubble Space Telescope. So using that fleet of robotics that is there for the assembly as the maintenance crew as well during the lifetime to replace parts, damaged parts from orbital debris, from wearing out solar panels, and even consider essentially keeping a permanent structure in space that continually gets replenished with new parts, and all parts get recycled. But when we think about the end of life here, thousands of ton structure, this is not something to be burned up in the atmosphere, nor is it something to be left in graveyard orbits. So we are going right in with our contractors and saying this has to be part of ESA's zero debris policy. Nothing is to be left behind. Think about a circular economy from the beginning. So recyclability in space is going to be part of the design and the consideration as well, and all of the technologies needed for that as well. So I think it's unavoidable that we go that way, but this application provides the opportunity to develop those capabilities even further than all of the other applications.
Thank you. Is there any more from the floor? No. Anything online, Jose? Okay, so I'd like to thank Dr. Sanjay Vijendran for his very interesting talk today, the keynote, and thank you again.
Thank you very much, and please follow us on LinkedIn. If you are using LinkedIn, we have a page, ESA Solaris, where we share our information on the latest on that, and help spread the word. Thank you very much.
Okay, so let me just do this for everybody. And everybody who has been very patient online and here in the room, we have a few minutes now just to stretch your legs, grab a coffee, have a comfort break. And the next presenter will start at 10:55 sharp. Okay, our next presenter today is Mr. Mike Snead. Mike Snead is an aerospace engineer focusing on space solar power generated astroelectricity and astrologistics required to undertake building the space and solar power systems. He's a registered professional engineer and an associate fellow of the American Institute of Aeronautics and Astronautics. Mr. Snead worked for nearly 40 years as a civilian employee of the US Air Force. During that time, he worked on the Air Force Trans-Atmospheric Vehicle Studies, the National Aerospace Plane Program, and the Delta Clipper, an experimental or DCX program, all focused on achieving fully reusable aircraft-like human space access. Currently, Mr. Snead advocates for an American and worldwide transition to sustainable energy, primarily using space solar power generated astroelectricity.
I'm going to talk about sustainably powering the world with space solar power and how to get started with building the astrologistics capabilities needed to jumpstart the spacefaring industrial revolution required to make space solar power a reality. Beginning nearly 12,000 years ago, the start of agriculture fundamentally advanced our ancestors' food energy security. Anthropologist Leslie White concluded from his studies of ancient cultures that agriculture succeeded because those technologies harnessed solar energy in a new way and new form. Agriculture also succeeded because it substantially increased the amount of useful energy produced per unit of human effort and the fact that it could be used globally. The invention of the steam engine, using another form of solar energy, fossil carbon fuels, began the industrial age. Steam-powered industries further advanced human productivity, enabling the emergence of a prosperous middle class. Currently, fossil carbon fuels supply around 80% of the energy we consume. Everyone understands that this is not a sustainable solution, with affordable supplies likely not lasting until the end of the century. Also, non-sustainable fossil fuels cannot provide the world overall with equitable access to affordable energy and consequently the opportunity to achieve a middle-class standard of living. The Universal Declaration of Human Rights identifies freedom from want as an aspiration that should be available to everyone, everywhere. To achieve global freedom from want, the United Nations has identified these 17 Sustainable Development Goals, including affordable and clean energy. My analysis shows that the best path forward to achieve the needed global affordable and clean energy solution is to, once again, harness solar energy in a new way and new form. This needed solution is space solar power generated astroelectricity. I am going to explain why space solar power is the world's only practicable solution for achieving global sustainable development with clean energy, and how we can jumpstart the needed new spacefaring age to transition the world to abundant astroelectricity by the end of this century. I will start with explaining how we can transition from fossil carbon fuels to reliable clean energy. The clean energy transition model I use is intended to provide an orderly and largely transparent transition to clean energy. It begins with replacing fossil carbon fuels with primary sources of clean electrical power. When using baseload primary electricity sources, some of the baseload electricity can be passed directly to the end users, just as is done today. However, most of the baseload primary electricity, as well as all intermittent primary electricity such as from wind power, will be used to produce clean hydrogen and extract carbon dioxide from the atmosphere. The hydrogen and CO2 will then be combined at greened refineries to yield clean carbon fuels and industrial feedstocks. Some of the clean fuels will then be used by electric utilities to generate the additional clean electricity needed to fully meet end user needs. This approach will enable building a renewable energy infrastructure supplying clean electricity, clean fuels, and clean industrial feedstocks to enable true global sustainable development. Next, I estimate how much clean energy is needed per person. These are the relative per person energy use values for the United States, the European Union, and the world expressed using the EU value as the reference baseline. I use the EU per person energy use as the goal for the world to achieve with clean energy. To report how much energy is currently used per person, the energy unit called the barrel of oil equivalent, or BOE, is used, as most of the energy now used is fossil carbon fuels. In 2019, prior to the start of the pandemic, the EU averaged 22.3 BOE of total energy used per person, broken down into the electricity and fuels used as shown. The equivalent amount of primary clean electrical energy needed per person to replace the use of fossil carbon fuels can be estimated using the clean energy model. The first step is to eliminate the energy options that are not sufficiently scalable to meet world clean energy needs. These are the 4 remaining options. 2 are baseload, and 2 are intermittent primary sources of electrical power. For many reasons, I do not believe that a substantial expansion of nuclear fission power is likely. So this is eliminated as a possible, scalable solution. This leaves 2 intermittent terrestrial options, wind power and ground solar power, and the baseload option of space solar power. Using the clean energy model, these are the estimates of the equivalent EU 2019 total primary clean electrical energy needed per person for the baseload and intermittent cases. For the baseload case, about 60,000 kilowatt hours of total primary clean electrical energy would be needed per person. This equates to a continuous supply of 7 kilowatts. For the intermittent case, about 80,000 kilowatt hours of total primary clean electrical energy is needed per person, which equates to a continuous supply of 9 kilowatts. For perspective, the baseload case requires the primary clean electrical power per person needed to operate 7 microwave ovens continuously, while the intermittent case requires power for 9 ovens continuously. Now let's estimate how much total clean electrical energy the world will need in 2100. For this discussion, the electrical energy unit used will be the gigawatt. Note that it takes 1 million kilowatts to equal 1 gigawatt. Thus, 1 million people, each requiring 9 kilowatts of continuous electrical power, will require 9 gigawatts of total continuous power. For perspective, the Hoover Dam can produce up to 2 gigawatts. Thus, 1 million people, using intermittent wind power, for example, would need the equivalent continuous output of 4.5 Hoover Dams. I assume a world population of 10 billion in 2100. When using intermittent wind or ground solar power, the world will need the equivalent of 90,000 gigawatts of continuous primary clean electrical power, or the equivalent of 45,000 Hoover Dams operating continuously. Can wind and ground solar power practically meet our clean energy needs? This is how much land is needed to supply an equivalent continuous gigawatt of primary green electrical power when using wind or ground solar power. In 2020, the EU had a population of 450 million. To go clean, it would have needed the equivalent of 2,000 Hoover Dams operating continuously. This requires nearly 4 million square kilometers of wind farms or over 500,000 square kilometers of solar farms. The global 2100 wind power solution would require nearly 3 Africas covered in wind farms, while the global ground solar power solution would require 1.5 Australias covered in solar farms. This means that neither wind nor ground solar power can provide practicable solutions for the EU or the world to go clean. We are left with only the global space solar power option. Now let's look at the baseload space solar power solution. The baseload solution requires the equivalent of 70,000 gigawatts of continuous primary electrical power. I assume that astroelectricity will supply 80% or 56,000 gigawatts to replace the use of fossil carbon fuels. In the 1970s and 1980s, NASA and the U.S. Department of Energy defined a baseline space solar power system for planning purposes, delivering 5 gigawatts of astro-electricity. This is the design of a conceptual space solar power platform located in geostationary Earth orbit, developed by NASA about 30 years ago. I use it just to explain how space solar power works. The platform collects about 26 gigawatts of sunlight to deliver 5 gigawatts of astro-electricity. The end-to-end efficiency is expected to be in the range of 20%. Each platform will be about the size of Manhattan Island and have a mass of upwards of 50,000 tons. I call the ground station for receiving the transmitted astro-electricity an astro-electric plant. This is the layout of the baseline 5 gigawatt astro-electric plant. When located at 35 degrees latitude, such as in southern Spain, the entire plant requires 209 square kilometers or 81 square miles. The green oval is the receiving antenna. It will look like a solar farm. Supplying 80% of the world's total energy in 2100 will require about 11,000 astro-electric plants. These plants would require about 2.3 million square kilometers. This equates to a total square of land about 1,500 kilometers on each side. When using space solar power platforms located in geostationary Earth orbit, the white band represents the possible locations on the ground where the astro-electric plants could be built. Note that if an astro-electric plant would be built on the equator, with its space solar power platform directly overhead, the receiving antenna would be circular. Otherwise, the shape of the receiving antenna will be elliptical. The blue box represents the 2.3 million square kilometers of needed land. With the ability to locate astro-electric plants over most of the world, this means that the global energy supply will be decentralized, while the production of clean fuels means that all of the world can be supplied with clean energy by pipeline and ocean tanker. If ground solar farms are built on the entire footprint of the astro-electric plants, integrated with the receiving antennas for the transmitted astro-electricity, these solar farms would provide the remaining 20% needed for a 100% clean energy solution. Space solar power generated astro-electricity has these advantages. To be clear, this means that at around 11,000 locations spread around the world, the equivalent of about 3 Hoover dams will be built to provide the abundant clean energy needed to achieve the UN Sustainable Development Goals. This global supply of astro-electricity means that at thousands of locations all around the world, we will build and rebuild sustainable cities and towns to enable the world to proudly enter the 22nd century at peace with global middle-class prosperity. Now, what does this mean for humanity's spacefaring future? This space solar power solution will need roughly 560 million tons of installed equipment in geostationary Earth orbit. This means that the geospace solar power platforms will need to be manufactured in space using primarily lunar and asteroidal resources. To achieve this clean energy solution, we now need to initiate a new era of human civilization, the spacefaring age, where a spacefaring industrial revolution will be undertaken to permanently settle the central solar system to build the space solar power systems needed to power our terrestrial civilization with clean energy and make it fully sustainable and prosperous. To get this spacefaring industrial revolution underway, we now need to build a robust astrologistics infrastructure enabling commercial human operations throughout the Earth-Moon system. From our logistics experience with the International Space Station, we know that we need larger and more capable in-space astrologistics capabilities. I propose commercializing the cargo version of the Space Launch System and use this to build the initial astrologistics infrastructure in low Earth orbit. A space base and space dock would be the first facility to be built in low Earth orbit to provide the initial astrologistics port of call for transporting passengers and cargo to LEO. This space base and space dock would require only 6 SLS cargo missions to build. The crew size would be about 25. To enable routine maintenance and cargo handling operations, each space base would have 2 space hangars. The main hangar deck would be 10 meters wide by 30 meters long. This would enable smaller vehicles and payloads to be serviced within the space hangar without needing to go EVA. The space dock would be about 250 meters in length. It would be used to assemble large facilities such as a space habitat. Only 8 SLS cargo missions would be needed to assemble this 100-person space habitat. By rotating the habitat, up to Mars-level artificial gravity can be produced. With this habitat's hub and spoke design, it has over 2,000 square meters of floor area. The space dock would also be used to assemble and dock large spaceships. This conceptual spaceship design draws on work done at NASA Glenn using LOX augmented nuclear thermal propulsion. Assembly of the spaceship starts with the delivery of a missionized space hangar. The other components would be delivered using partially and fully reusable spaceflight systems. With nuclear thermal propulsion, the spaceship would be able to conduct round-trip missions throughout the Earth-Moon system, providing access to GEO, the Lagrangian orbits, and lunar orbit. The spaceship's crew size would be about 12, along with additional mission specialists and passengers. Space tugs and lunar landers would be carried inside the spaceship's space hangar. Here, the spaceship is passing a 300-person space habitat. The travel time to the moon may only be about 24 hours. The spaceship will deliver cargo and passengers and conduct astrologistics support operations throughout the Earth-Moon system before returning to its space dock in low Earth orbit. Utilization of the European Space Agency's spaceport in French Guiana to launch the commercialized SOS would enable space bases and space habitats to be built in equatorial low Earth orbit, providing a key astrologistics gateway to the entire Earth-Moon system and beyond. Thank you for this opportunity to highlight the growing importance of space solar power to achieving a peaceful, sustainable, and prosperous future for humanity.
So thank you, Mike, for that very entertaining vision of space-based power and beyond. So our next presenter today. So Dr. Larson was asking if I take questions for Mike. But in fact, Mike has kindly offered to be with us, hopefully for the panel at the end of the day, obviously depending on the time. So I think yes, potentially is the answer to that. And I'm sure he'd be more than willing to have a discussion offline about it as well. He's very, very, very open gentleman. So moving on to our next presenter today, it's Mr. James Cornish. So he's a self-declared space geek. James leads the civil and commercial space business at the Fraser Nash Consultancy. So you might have seen one of James's reports presented by Sanjay earlier on today. With 10 years of system engineering experience from across the energy industry, James has supported several significant energy projects in the UK, as well as supporting R&D into renewable and nuclear energy sources. James is actively involved in the UK space-based solar power community, supervising the delivery of several space-based solar power projects, as well as co-chairing the Space Energy Initiatives International Working Group. So I believe we should have James online. James, if you'd like to take the screen. Did you want to drive your slide yourself, or did you want me to drive for you?
Morning, John. Yeah, no, I'm happy to drive myself.
Perfect. Over to you then. Thank you.
Excellent. Just 1 second. I'm doing the same. I've clicked a button and lost your screen. Can you see and hear me?
Loud and clear, 5 by 5.
Excellent, thank you, and thank you for inviting me to speak. Yeah, so I'm James Cornish. I'm business manager for civil and commercial space here at Fraser Nash. And what I want to spend the next 20 minutes talking about is giving you an overview, particularly from the economic case for Europe for space-based solar power. So Fraser Nash did some work recently for the European Space Agency looking at the cost-benefit analysis for space-based solar power. So how are we going to do that? Well, firstly, I'll give you a bit of an overview of the study context and what its ambitions were. We'll talk a bit about the net zero challenge, and then look at the sort of costs and assumptions behind developing a space-based solar power system. And then we'll look at actually how does this stack up against other renewable technologies, and then dive a bit more into sort of the cost-benefit case and the difference between public and private partnership and risk profile. So this study was undertaken by Fraser Nash and our partners London Economics, or both companies based in the UK. So the study objectives was to consider the strategic and economic and societal environmental costs and benefits of developing space-based solar power. So our methodology, the study was based on a space-based solar power concept called Cassiopeia. Cassiopeia is being developed by a company called IECL, Ian Cash, in the UK. And there are a variety of different concepts of scale available, not quite the size of what the previous presenter was talking about, but ranging from megawatts into the low gigawatt size energy production. So we undertook a technical feasibility of Cassiopeia. Now, I'm not going to dive too much into that because I'm sure there's going to be lots of presenters today talking about the technical aspects. And what I'm going to focus on is really the economic aspects. So having completed technical feasibility, we then had a number of industrial engagements for our workshops, talking with the representatives from the energy industry, and we undertook a cost and economic modelling to understand actually what the key drivers were and sensitivities were in terms of the economic and costs for space-based solar power. And then we've done additional work focusing on the 5 highest carbon emitters for countries across Europe, so Germany, the UK, Poland, Italy, and France. So the net zero challenge, as the previous presenter set out, we have a serious challenge on our hands. We not only need to decarbonize our existing electricity production, but we also need to increase the volume of our existing electricity production for a number of different reasons. Firstly, because of population growth, both internationally and in Europe. But we also need to decarbonize many areas that currently use other fuels, such as oil, for power. So powering electric cars. And Grids have been making this transition. The UK, for example, has made a significant transition to using lower carbon, so gas, and also increasing amounts of wind technology. And we are going to rely on renewables and nuclear to do a large portion of this. However, they can't get us to net zero by 2050 alone for a variety of different reasons. We do have this gap. In reality, our future grids are going to need every possible renewable technology or low carbon technology we can get our hands on to achieve net zero. And space-based solar power can be part of that path of achieving net zero. And two of the great things of space-based solar power is it offers, firstly, baseload power, so very high capacity factor, equivalent or actually surpassing nuclear in terms of baseload power. It is also has a really interesting characteristic. It's dispatchable, so you can send power to different locations within a country or even within on a continent without having to have lots of expensive infrastructure in place. So that gives you lots of people in the industry get quite excited by this, because it gives you lots of interesting capabilities and also allows you to solve where you have peaks in load without significant investment in assets, which for a lot of the time will just be sat there not operating. It can also reduce, because it is baseload, it can also reduce the impact of moving to a highly renewable powered system where your network is highly dependent on intermittent renewables, and actually can overall reduce the costs of the overall system. So from our experience over the last 24 months, we know that energy is not only just about being zero carbon, but also being secure and affordable. And there's been a whole, with the Ukraine war and the impact on energy prices, there's been a massive impact in terms of the energy affordability for energy in Europe. And majority of governments across Europe have had to implement various schemes to ensure that the likes of you and I can still afford our energy and are not going cold in the middle of winters. So it's incredibly important that the energy that our future energy mix is not only zero carbon, but is also secure and is affordable. So the cost to develop a space-based solar power system. As I said, our study was based on the Cassiopeia concept, which is, for reference, is about 1.44 gigawatt system. It is approximately 2,000 tons in a geosynchronous or MEO orbit, depending on exactly what concept you're looking at. And we've made a number of assumptions in terms of the cost modeling that we've undertaken for this. For example, we are assuming completely autonomous assembly and operation, so no humans involved. We're assuming launches using equivalent of SpaceX's Starship, so that next generation fully reusable large launch vehicle. So over a 30-year operational life, we'd expect total cost for first of a kind system to be in the region of about 13 billion euros, with that falling to a tenth of the kind to in the region of about 9 billion euros. And if you look at most recent studies on space-based solar power, they would generally set out a 4-year program. Total timeline does vary, but the first phase is typically focused on ground-based trials. So this is a technology de-risking phase where you can demonstrate some of the key underlying technologies, such as wireless power beaming, being able to achieve that long distance and at high power, and also the autonomous assembly of structures. And understanding how you're going to do that assembly, but using a terrestrial analog. The next phase, phase 2, is about being able to demonstrate power beaming, high power over long distances from orbit. So this would be typically a single launch atop of potentially a sort of Falcon Heavy vehicle in the sort of tens of tons, but wouldn't require any assembly, likely to be in a MEO orbit, for example, and beaming low megawatt power back to Earth. And that's really interesting because not only is this a technology demonstrator, but this also has a potential market in the energy industry. Now, the energy you produce, the cost of the energy per megawatt hour you produce from this vehicle is going to be far higher than for baseload generation. However, it could be, there is a market for supplying hard to reach places where if you, for example, are trying to power a remote military base and you're having to run tankers for many, many miles over hostile terrain, then actually you're paying, orders of magnitude above you would for if you were just plugging in your iPhone to recharge it in from your home in terms of the cost of the power. So there is actually potential market, smaller significantly, but there is still a potential market to be able to commercialize that product at the end of that second phase. The third phase is then actually demonstrating this on a bigger scale, and really key is demonstrating the autonomous assembly in orbit. So multiple launches, producing into the sort of high megawatts, hundreds of megawatts power. And at that point, again, you can start supplying into the commercial market in terms of energy, and you're sort of at a similar size to some of your smaller combined gas and steam plants and some of your smaller wind power plants. And then phase 4 is actually the production of the first of a kind hypermodular gigawatt power generation. I should say, if you'd like to find out more about the Cassiopeia concept, there's a fantastic talk by Ian Cash, the inventor from IECL in Cambridge on YouTube. So just Google Cambridge and Ian Cash at Space-Based Solar Power and you will find it. So comparing with other renewable technologies, and I'm going to add a caveat here. There are various methodologies for comparing the cost of individual generation sources, and there are tweaks and ways of doing it to try and make it easier to compare them or more accurate to compare them. So, but it really does depend on the total cost. Very much depends on the specific setup for your particular generation network. So your power grid. So the more renewables they have, the more backup. So it really depends on the individuals. But we do use this tool called value adjusted levelized cost of electricity, which seeks to take into account factors such as intermittency, carbon production, and then various other things. So we can make a fair comparison between different technologies. So the key takeaway from the study is that actually space-based solar power on a value adjusted levelized cost of electricity basis is more competitive compared to existing carbon intensive sources of power such as coal, oil, and gas. And actually, if you look at the hurdle rate, which is the cost of financing, represents the cost of financing for power systems or for generation systems, if that is reduced to about 10%, then space-based solar power becomes competitive with other renewable technologies such as wind and solar, and also other things such as nuclear. So the study we undertook looked at all the different elements in terms of cost and actually the benefits that space-based solar power would bring. So that includes, in terms of the benefits, actually avoiding the use of wind and solar in terms of their ground usage, so that land can be used for other things such as agriculture, avoiding the social costs of carbon dioxide emissions, also the spillover benefits in R&D. When we talk about space-based solar power in the UK, a lot of the time we talk about no regret investments. These are technologies which will be required for the space economy, whether space-based solar power becomes a reality or not. And there are also lots of spillover benefits for the terrestrial economy as well. We also factored in the sort of opportunity cost of land. So as the previous presenter set out, you do need rectennas which are reasonable size, and where you put them is up for debate, whether it's land or sea, but looking at and also the overall cost. So our results show there's a positive result in terms of space-based solar power for our cost benefit analysis, with 183 billion positive value for Europe. Now, it's important to understand some of the sensitivities, and I'll talk about this shortly. So, having taken that base scenario, which was based on the rollout timeline that I put forward and those costs, we took that base scenario and compared a number of different scenarios, so various sensitivities. So what's the impact of reducing the benefit you get from decarbonizing? What happens if we decarbonize faster, so we can actually roll out nuclear and other renewable technologies faster, reducing the social benefit that you achieve from space-based solar power? What happens if we double the costs of space-based solar power? There is still a lot of technology development that needs to be undertaken, and still quite a lot of uncertainty in terms of the scope, that cost. So in most of the scenarios that we considered, space-based solar power still provides an overall net benefit to Europe. The only scenario where there really was a negative benefit to Europe was where actually you doubled the costs of space-based solar power. So that's both the capex, the opex, and the development. So final piece is on, okay, well, we're talking about a multi-billion euro investment here. Typically in the energy industry, projects beyond about €1 billion, or slightly more than €1 billion, won't happen without some kind of public support. So the largest renewable projects, so that's wind farms or solar plants, typically in an individual phase won't be more than about 1 billion. And when I say individual phase, I mean what you do before you can actually start generating electricity and therefore generating revenue and return for clients. And that's why, particularly in the nuclear sector, where you're looking at projects where the typical cost of a large conventional nuclear plant is anything between 20 to 30 billion euros for 2 to 3 gigawatts worth of power, there's usually some form of government support, whether it be through a government developer directly developing the plant, or whether it be through some kind of government financing scheme. So our base scenario considered a 20% hurdle rate for space-based solar power, which, comparing to other sources, so renewables typically around about 5%, nuclear is around about 10%. And the model we've used is sort of suggests that actually to make space-based solar power a reality, there needs to be significant public funding to de-risk space-based solar power to make it a reality. And that public funding is demonstrating, really focused on demonstrating some of the key technologies, helping advance the technology readiness of these technologies, and reducing the risk profile to a point where private sector investors can come on and see a high probability of return in terms of their investment. So just to summarize, so SBSP is a renewable baseload energy source, which really could provide Europe energy independence and help achieve net zero by 2050. Development costs for the Cassiopeia concept are in the sort of teens of billions, but reducing, so comparable to nuclear, but again for the same kind of generation that you're looking for. Space-based solar power will be more competitive than energy other sources once maturity has been achieved. And the great thing that I think the work we've demonstrated is that actually looking at the whole, because there is a lot of uncertainty in terms of the development of these technologies, but the case is robust in terms of a number of different future scenarios for developing space-based public power. But it does require public funding and public backing to make it happen. If you'd like to find out more about the cost-benefit study that the Fraser Nash has undertaken, and also the other independent study undertaken by Royal and Berger, I've included the links in the presentation to those studies, and also the Space Energy Initiative, as well as being chair of the International Working Group. I'm also membership secretary, so if you're interested in joining the Space Energy Initiative, which is based in the UK and brings together government, government, industry, and academia to try and advance space-based solar power, then please do drop me an email. Thank you very much.
Thank you, James. So I'm wondering if there's any questions from the floor here today for James? Any burning questions? Looking around, nothing from the floor. Jose, was there any questions online? Did you spot anything?
Pass that to him later.
So I didn't catch that.
Only a question from Mike, but we'll pass it to him later.
No, we need for James right now, so the other questions can come later. Okay, so okay, that's not going to work. Boom, there we go. It's finally working. Let's see if I can keep it going that way the rest of the day. So our next esteemed speaker is Dr. Namrata Goswami. Dr. Goswami is an independent scholar on space policy and great power politics. She's a professor at the Thunderbird School of Global Management, Arizona State University, and part of their Executive Masters in Global Management, Space Policy, Leadership and Finance. She's a consultant for Space Fund Intelligence and was a Fulbright Senior Fellowship awardee. She was awarded the Minerva Grant by the Office of the US Secretary of Defense to study great power competition in outer space. Her co-authored book, Scramble for the Skies, The Great Power Competition to Control the Resources of Outer Space, and she's an author and co-author of a number of other publications. She has published widely in various media outlets such as The Diplomat, The Economic Times, Washington Post, and many others. She's currently working on 2 academic book projects, one on China's grand strategy and notions of territoriality, another on space power theory and practice. So without further ado, we'd like welcome to the stage Dr. Namrata Goswami. So Dr. Goswami, would you like to switch on your video and he says confidently.
Great.
Okay, can you see that online?
Yes, I can see it, and well, sorry for that, and thank you for having me today. So what I'm going to do is I'm going to talk a little bit about space-based solar power, but also from a policy side, because I work on space policy and international relations. And the key question that we need to think through when we talk about space-based solar power is that while those who understand the technology and those of us who are actually involved in space get it, but what the challenge I have faced as a person talking to, say, the American public or populations in India or China, is that the space-based solar power, the potential of it, as we heard from Sanjay and the presentation before me, the impact of it is not really understood globally and widely. And that's why there is, you see a lack of momentum in terms of support, despite the fact that at the leadership level, there is a deep level of understanding. I would also say that I testified for the US-China Economic and Security Review Commission on China's space program. And when I talked about China's space solar power program, the question that was put to me was that, what is this? What is this technology? It sounds like science fiction to us. And this was in 2019 by US senators and representatives. So it's a very important challenge we have as to how do we actually bring public awareness, which was also the point of the last presenter in the last slide. Next slide, please. So what I do in terms of looking at a particular case study, and for today, it's a case study of space-based solar power, is to look at where exactly this particular concept is in terms of public policy process. Because the one thing that we recognize that today there is investment in space-based solar power in some countries. And because of that, especially because of what China has announced, there is the rise of geopolitical momentum. And then again, I thought the last presenter's slide on why is this a critical technology in terms of renewable capability is also what Europe is facing in terms of the Russian invasion of Ukraine. Today, I am actually in Provence, France, and I sometimes wonder when I look around at the people as to whether they're thinking, in terms of long-term access to renewable technology? And do they know what space-based solar power is? So the interesting thing when you look at the concept of space-based solar power is that it is still at the problem identification agenda setting stage across several countries and societies. So it has not yet made it to the policy formulation stage, which is really critical when you think about a particular technology. So, and it is interesting because for a technology like space-based solar power, which requires enormous level of funding, especially at the research level, it is critical that state agencies support this particular effort in collaboration with, say, universities, which is what the United Kingdom is actually doing to an extent, and which China has actually operationalized since 2013. So when you look at the policy formulation stage, there are a few countries that are already formulating policy. One is, of course, China. The second is Japan. The third is the United Kingdom. And then you have very advanced thinking in terms of policy formulation and space solar power in Japan. And recently, South Korea is starting to show interest, and Australia has also announced a low-level program. So in terms of policy adoption, policy implementation, the country which is the lead nation in space, which is the United States, there seems to be a lack of national level policy when it comes to space-based solar power, despite the fact that there has been several presentations and advocacy groups that are talking about space-based solar power and pushing for it. Next slide, please. So I don't want to go into the basics of space-based solar power, but this is something that I recognize is not easily translated into policy conversation. So when I talk about, for example, what those who study this technology and are building the products tell us, that this is how space-based solar power is going to be activated, where you build very large-scale satellites. The Chinese concept is about 10,000 tons. And then you actually beam it through laser and microwave to rectangles or receiving ground stations. The first question I get from the audience, I recently also gave a TED talk and talked about it a bit. And so the first question I got is this going to be dangerous? And so how will it affect the transmission? And so these are the basic questions that need to be answered if you want to have funding and public awareness in terms of how this particular technology works. Next slide. So where do countries stand? So based on that, based on the fact that there are certain countries that have adopted it, I think one of the most important lesson that I learned from China, where I conducted fieldwork and asked questions on whether space-based solar power was a technology they were thinking about, and this was in 2017-18. And then you know that in 2019, China announced a national level program. So what was insightful for me was that in speaking to my Chinese colleagues from the China National Space Administration or from Chinese space agencies, as well as academia, the concept of space-based solar power was viewed as a strategic technology. And there was grand strategic thinking. And by that, I mean, the conversation was about not just how the technology is going to be developed, but how the technology is going to affect China's standing in the world by 2050. So those who understood the technology, for example, Wang Shishi, the founder of the Long March rockets and a deep thinker in China who pushed for this within China Academy of Space Technology, he pointed out that this is a technology that is going to change the game of energy. And it's really important that at the comprehensive level of national power, China needs to start thinking about space-based solar power as a vision for economic independence and renewable technology, as well as connecting it to the concept of net zero and climate change. And we see that if you think about the cycle I put forward to you, once around 2010, when they commissioned a study to actually see whether this is feasible, by 2013, they took a decision that this is a feasible technology and we need to now start building it. And so based on that, they have policy direction at the level of the State Council, as well as the China National Space Administration, that committed to space-based solar power as a technology they want to scale up by 2050. And then what is very important is that they are connecting it to long-term strategic goal. Now, the United States, in comparison, does not have that kind of grand strategic thinking when it comes to space-based solar power. It's very surprising to me because under the current administration of Biden, there is a huge commitment to renewable technology. There is the commitment to continuing some of the programs of the Trump administration, for example, the Artemis lunar program, without really committing to the concept of space-based solar power. And why that is important, because if you listen to some of the presentations, including the excellent presentation yesterday, Lunar Spark, we realized that space-based solar power can be actually used for lunar missions as well. Now, India, which is another major spacefaring nation, just today successfully launched their Chandrayaan-3 lunar mission. I was just watching the launch, happened a few minutes ago. What is critical is that at the leadership level, there is an understanding of the importance of space-based solar power. For example, India's former president, Abdul Kalam, very insistently pushed for it. He attended the International Space Development Conference in 2013 and gave a full speech on why space-based solar power is the technology that nations like India need to invest on, given the fact that there is growing population and the globe, because the population of Earth will become 9 billion by 2050, and fossil fuel and ground solar will not do it because of the challenges that have been presented to this forum before me. So there was push at the leadership level. But then when I did fieldwork in India and asked this question to Indian Space Research Organization thinkers as to whether they have a program on space-based solar power or are thinking of it, the answer was no. And that's again very surprising because India does have a big investment on ground solar. And so what I would argue is that the lack of such program is not because scientists do not understand the critical importance of the technology. I think the biggest concern is risk funding, as well as the lack of societal push for this particular technology because of lack of awareness. Next slide, please. So case study, if you think about the case studies of the United States, as I mentioned, the US does not have a national level space-based solar power program, despite the fact that there has been several congressional meetings, there has been policy advocacy, there has been research and finding from the Pentagon that space-based solar power could be a very critical technology for the US military to support bases that are outside of reach in terms of logistics, as well as there has been studies that this is deeply impactful in terms of renewable technology. There are very few limited programs. One is, of course, the Air Force Research Laboratory, SPIDER, which you must have heard. And then the US Naval Research Laboratory also has a program. And one of the interesting insights that came to me in the last few months is that Caltech actually succeeded in launching its space solar power project, as you know. And what the Caltech team basically put out in their website is that they were able to not just transmit electricity in space through wireless beaming, but also they detected technology on their ground receiving stations. Now, why is this critical? This is critical because several US public media, for example, CNBC, CNN started talking about space-based solar power. I was in a recent interview on CNN where they asked me about China's space solar program and how actually the US stands to that regard. So even a small demonstration of capability where societies can actually then understand what this means in space and space to Earth can actually inform public opinion, but then the challenge is to scale it up. Next slide, please. So as I mentioned, even the National Space Council that was reconstituted, and one of the biggest focus of the National Space Council under Vice President Kamala Harris is to look at renewable capabilities, but space-based solar power is not mentioned. NASA is actually undertaking a feasibility study on space-based solar power, but unfortunately the study is 8 months late and we haven't seen it being published as yet. So we need to wait and see what they conclude in terms of how important this particular technology is. Next slide, please. I think China's space-based solar program is extremely exciting. And what I find exciting, a person studying China's grand strategy and space policy, is that they also give you continuous updates in terms of their space-based solar power program. So in 2022, the China National Space Administration, they actually told you that there will be numerous launches of the Long March 9 rocket, which is their reusable rocket, their rocket that they want to make reusable by 2030, that is going to be used for their space-based solar power construction, especially in space. And then they also want to do a small-scale electricity generation test in 2036. In fact, this was revised in 2015. The earlier date was 2028. And now they're saying that they are planning to do this by 2036 and a larger megawatt level power generation by 2030. The expectation, again, they put out that expectation, is that they will be able to have commercial gigawatt level power generation by 2050. Next slide, please. So this is what they put out. I'm sure many of you have seen this. This was publicly available, put out by the China Academy of Space Technology and the China National Space Administration, where they tell you how they are going to actually accomplish this. And the one thing that from a policy side, we need to keep in mind when we think about China is that sometimes there are arguments that what China puts out in terms of space goals could be propaganda as well. But in my research, where I looked at China's space program since it started to where it is today, including their lunar and space solar power program, what I noticed is that once it has crossed that particular level of just being media articles to becoming very critical projects under their space state-funded policy making bodies, they are very serious about their accomplishments, and also they have reached some level of confidence in terms of the feasibility of their technology. Next slide, please. So again, this is interesting because again, this year they put out their Long March 9 goals, which is their heavy lift rocket, which is going to be reusable. And the designer of the program put out this particular mission statement. And if you can see, the third mission is, the fourth mission is actually constructing orbital solar power plants with 10,000 megawatt capacity. And they actually tell you what they're going to do in terms of how many launches will be required to build this particular structure, quite a lot. Recently, they also announced that they will first start by experimenting in space wireless transmission in low Earth orbit through their Tiangong space station. And once they accomplish that, they're going to scale it up to GEO. So, and what is good about China's space-based solar power program is that they have university collaboration. So Zhejiang University, as you know, has built a structure to wirelessly beam space sort of electricity on Earth. And they want to now scale it up to do it as a demonstration in space by 2026. Next slide, please. Japan. So if you look at Japan, Japan actually is one of the first countries to showcase limited scale wireless transmission of capability. So today it's a national legislation requirement that Japan should invest in this capability. So there is a public-private partnership that led by the Japanese space agency JAXA that will actually demonstrate a first satellite transmission in 2025. And they tell you what they're going to do, basically a demonstration of capability. And very similar to the United Kingdom and China, they're connecting it to their climate change and renewable energy. Now, the difference between Japan, China, and the US is that for China and Japan, these are national level space goals. For the United States, it's not. Next slide, please. South Korea also recently has become interested in space-based solar power. So the Korea Electrical Research Institute is investing in wireless beaming of technology. And as you know, this year, they launched their own indigenous rocket, which is the KSLV-2 Nuri. And so what they're arguing is that they're going to build an entire ecosystem where they're going to demonstrate this particular capability in the next few years. South Korea's space-based solar power is not yet at the policy formulation level, but they are starting to do studies in problem identification, by which I mean identification of the requirement of a particular technology and base level technology demonstration. Next slide. Now, Australia recently also established space-based solar power alpha, demonstration of capability. John Mankins, who is a well-known name in the United States in terms of space-based solar power investment, is a part of the project. However, I will qualify that by saying that with the change of administration last year, I was in Australia actually last year, and so there was a lot of interest from the former administration in terms of looking at space, investing in space-based solar power, building Australia into this very viable commercial space industry. But with the change of government, the investments in space has been scaled back. So that's why I argue that sometimes there has to be a societal effort in some countries that has to go beyond the state. State funding is really critical to scale up the technology, but if it doesn't happen, there has to be a commercial level effort. Next slide, please. I think the United Kingdom is an extremely critical case study. For example, as you know, the United Kingdom has developed the Space Energy Initiative, and several departments are involved. For example, the Department of International Trade and Department of Business. And there is Ian Cash that leads the effort in Cambridge, is a part of this particular effort. And recently, the United Kingdom signed understanding with Saudi Arabia on an initiative of space-based solar power. The Saudi, what they're looking for is to develop their Neom City project. And the idea is that they will utilize their about $3.4 billion in looking at a feasibility study to see if they can use space-based solar power to fund their particular city, especially because Saudi analysis is that fossil fuel is not the future for the Middle East. And so there is an interest there, and there is also an interest from the United Arab Emirates. Next slide, please. I think we have already had a great presentation from the European Space Agency. So in my policy graph, I think the European Space Agency now is moving to the policy formulation stage. So the feasibility studies have been done. They had done consultancy with two outside consultants to say what the cost benefit of this particular study is. They have a project looking at the feasibility of a commercial level demonstration by 2050. The idea is 50 gigawatt, which will contribute to about 15% of the European market. And so they also have ministerial level support. So they could be a very good case study for other regions. For example, I also teach at the African Space Leadership Institute, and students who are actually representation from the different space agencies are showing interest in terms of space-based solar power and wanting to establish space startups through the African Space Agency. So the European Space Agency, by demonstration of capability and successful beaming of power from space, could provide a great case study for other regions to pick this up. Next slide, please. So finally, before I stop, I would say that if I look at interest level, not even at problem identification, but before that, it hasn't even entered the policy cycle. I think India does have interest in renewable capability. And I would say that watch India in the next few years, because I was absolutely surprised by the Indian space policy document that came out this year. India as a country has been very hesitant to talk about space resources. They wanted to focus a lot on traditional goals like satellite launches, a reusable rocket technology. But today, India's space policy document has a very interesting paragraph, which is missed by this policy community. In that particular paragraph, India has taken a stand on the rights of Indian citizens and non-governmental entities to develop space resources, like asteroid resources, and to actually own it. So given the fact that there is already a push for great commercialization of space, I would say that there are advocacy groups within India talking about space-based solar power beaming. For example, Rebeam is a space startup that is investing in wireless transmission of technology. When I was there in 2018, they actually demonstrated that capability to me, where they wirelessly lighted 2 LED bulbs. So it's already there, the ground-based interest. So I would say that in the next few years, India would become a critical player in space-based solar power as well. The other country to watch is the United Arab Emirates. I think they will also come up with a national level space-based solar power program, given the focus on renewable technologies in their 2030 national space document. And then the African agency, if you look at the African Space Agency's vision, they want to support the renewable development of energy across Africa by 2063. And they're starting to talk about space-based solar power. And so public awareness is not there to the level that it might be there, for example, in China today, but there is the start of the conversation. So that itself is a wonderful thing. So I'll end by saying that there are certain things that space-based solar power technology requires to scale it up. One is, of course, the entire launch system. So why is it become so important and suddenly relevant? It's because we have reusable rocket technology. The biggest challenge for space-based solar power was the launch costs to build such large satellites. So if Starship is successful and it's reusable, the ability to build such structures is going to go absolutely up. The second reason why this becomes so suddenly important, and also there's a lot of policy conversation, is because of what China is doing and China's adoption of a national space level policy, and also what European Space Agency has done. A lot of conversations in the US is today led and informed by what ESA has announced in terms of its Solaris project. Finally, I'll say that we still have challenges in terms of an inability to explain to the larger electorate, if I may, or larger population as to why this technology is so critical. Because when I speak to audiences across the world, there is a deep understanding that climate change is one of the biggest challenges that humanity will face. But the technologies that they understand are ground solar, wind, and nuclear. Nuclear to a less degree is supported because of what has happened in Fukushima, but then the awareness of space-based solar power is not yet there in especially majority countries in the world. So I think a UN-led effort would be very important in public awareness, but also national level public awareness. So I'm going to stop there and thank you for having me.
Thank you, Dr. Namrata. So I'm just trying to get your slides back here for a second. I'm wondering if there's any questions from the floor. Okay, good. Is there any questions from the floor for Dr. Goswami? Yes, sir. If you press the microphone, you can speak.
I was just wondering, you mentioned that the UK signed a project or a contract with the United Arab Emirates for the NEOM project. Is it possible to elaborate a little bit on this?
Yeah, absolutely. So this particular conversation between the UK and Saudi Arabia has been going on for some time, and they had secretary level meetings. And very recently, in the last few months, they committed to collaborate in investing in a feasibility study through a UK private commercial firm. And so what is interesting is that there is the government level coming together of focusing on space-based solar power as a feasibility study. So they have not yet committed fully to whether they will invest in this. So the funding that they have agreed to is about $4.3 billion for the first study. $4.3 million, sorry, for the first study. And then based on that, they will come to the conclusion whether the Saudi Arabia will support the United Kingdom's effort at the national level to establish space-based solar power as a technology for net zero emission. So the idea is that NEOM is a project in Saudi Arabia that is as part of their 2030 national level agenda to build alternative sources and build smart cities that are basically use energy from renewable capabilities. And so one of the technology that they are wanting to learn and invest in is space-based solar power. And so it's at the very beginning stages, and that's where both countries are today.
Thank you.
Okay, sorry. Any more questions from the floor? Anything online, Jose? I had one question myself for you. While you were talking, I was trying to make some notes here. I was thinking, do we have a cultural problem here? Because when I look at what China's doing, and their roadmap looked very similar to the one that that James presented in many ways, with this megawatt, you know, for the demonstrator, and then scaling up to the gigawatt. But I wonder whether maybe, you know, in the West we have a leadership thing, no, where if it's not a policy, it's very national. We've got some bigger projects such as, I don't know, the GNSS or Galileo. We've got connectivity, GovSatcom. They're big projects for Europe. But when I look at China, you know, they put a policy in place and they go for it, and they really, you know, they put a lot of. You look at their version of ISS. It's this one. It's this one. Their version of ISS, and they're really catching up and almost taking the lead on a lot of activities now. I don't know what your spin on that is. If in the West we really need to do something similar on a multinational stage with the US, with Europe, to be able to be in the game in 2040, 2050 with China. What's your view on that?
Oh, great question. So I do a lot of work on that, actually. So I think the success of China in terms of not just space, but other technologies as well, is that they have taken 3 very critical grand strategic choices. And I use the word grand strategy because China basically has been informed by an important study that Deng Xiaoping commissioned actually in 1986 called the Comprehensive National Power Study, in which they identified strategic technology, science and technology, space, as well as some other technologies as very critical for China's development to become a lead developed nation by 2049, which is the 100th year anniversary. So fast forward to say 2010, when they took up the study for space-based solar power, the important thing is that, as you mentioned, in China, once a particular study is conducted, the feasibility study is done, it's then funded through their China National Development and Reform Commission. And so space and technologies connected to space are included as key critical infrastructure. So space-based solar power will form a part of that thinking as well. And today it has the sanction from the highest level, which is President Xi Jinping. So very, very different from how policy would be adopted, for example, in a democratic Western nation, where it tends to be more bottom up. But I would say that, having said that, I would argue that at times, when you think about strategic technologies, it is probably important that, for example, in regard to a technology like space-based solar power, once the key level democratic elected leaders are convinced that this is a technology that is feasible, that is cost effective, because they really care about costs, because there are questions asked, unlike China, where you can fund through the Communist Party of China, State Council funded the 5-year plans. If top leaders are convinced, then I think you can first demonstrate the capability, and then you can have the population excited about it. I will tell you, because this is the case with, say, the Apollo lunar program, a very expensive program, but it had a wide-scale support after John F. Kennedy gave that very critical speech as to why the United States needs to go to the moon and why it's important for US leadership, right? And so with space-based solar power, while we need that level of public awareness today, you cannot have the Cold War kind of rhetoric today. You need to explain the technology. But once NASA and the National Space Council, or there is a congressional level legislative measure that mandates the investment in space-based solar power as a key technology, and shows that this can be scaled and commercially available by 2050, I think the population will start supporting it. Because when I gave my TED Talk in Montgomery, Alabama, in the Rosa Parks Museum, I was surprised at how much after my talk, the local people came up to me and were extremely convinced as to why space is such a critical dimension of our lives today. And they started asking me the question as to why the United States has not declared space a critical infrastructure. So public awareness, the ability to explain the technology to the people, and to convince policymakers that this is an important key technology is the challenge of today. I think the physics supports it. Now it's the time to do the advocacy and actual policy funded programs.
Thank you. I do have more follow-up questions, but I think maybe we can take that for the panel later on today. Yeah. So thank you very much, Dr. Goswami. It's already on. It's already on. So thank you again for your time.
All right, can you hear me?
Yes, Peter, I'll just give you an introduction while you're just setting up there. Feel free to take the screen at any time just to get your slides running while I'm talking and introducing you here.
Sounds good.
So, Peter Garettson is a senior fellow in defense studies with the American Foreign Policy Council and co-director of its Space Policy Initiative and host of the Space Strategy podcast. For those who like to run when you're out in the morning in your car, you can listen to his podcast. He was previously the director of Air University's Space Horizons Task Force, an Air Force think tank for space, and was a founder and deputy director of the US Space Force's Shriver Scholars Strategy Seminar, America's premier military space strategy program. He is the co-author of Scramble for the Skies, the Great Power Competition to Control the Resources of Space, and his new book, available in all good bookshops, The Next Space Race, A Blueprint for American Primacy. So, Mr. Garettson, please, the floor is yours.
Thank you. Let me try your suggestion of doing the entire screen. Is that working for you guys? Are you able to see my slides?
We see you and me at the moment. I see a web browser at the moment.
Let's see if it's caught up.
Oh, there we go. Yes, yes, indeed, it works.
All right, wonderful. All right, so what I'm going to try to do today is I'm sort of a visual person. So when I try to understand the scale of things, I like to put things in a visual context. So I want to talk a bit about the scale and opportunity of space-based solar power. And I want to start off by cautioning that, abandon all hope, ye who enter here who fear scale, because SSP is of a scale not for the faint of heart. And really, when you talk about anything energy related, it's just on a completely different scale than anything space people are used to thinking about. So let me just start with the vision. The vision is terawatts of green 24-hour renewable energy to displace coal and other fossil fuels on a scale and time scale relevant for climate action. And so what you see on the left is an image showing resources from the moon to build solar power satellites. And on the right, it's showing what a fully developed ring of geostationary solar power satellites that are providing a significant fraction of global energy might look like. We're not going to build just one of these, we're going to build thousands. So my presentation is going to talk a little bit about projections, the scale of the market opportunity, the scale of a single solar power satellite, the scale of the global energy grid compared to the scale of the current industry, and then the potential to scale rockets and lunar mining, and then some remaining challenges. So why bother with this? Well, first of all, governments are motivated by certain things. And so today we know that Europe via ESA Solaris, the UK, China, Japan, and the USA are all spending what I would say exploratory dollars on space solar power. And if engineering to cost problems can be solved, space solar power offers a path to global civilization level scale. So we're not talking about something that levels off in scale at some percentage of global energy. We're talking about something that easily can accommodate 6 to 7 times the total energy demand of our civilization in 2100. Now, governments are motivated to undertake big investments by security, of which climate change and energy sovereignty appear to be very important to Europe right now, as well as to economic growth and competitiveness. And generally speaking, GDP growth tracks exactly with energy growth, as does increasing prosperity and jobs. Now, of course, there's this problem of climate change that we want to limit global carbon. And in order to do that, we're going to need to bring online something in the neighborhood of 40 terawatts of carbon neutral generation in order to meet our characteristics. And, you know, there's potentially huge GDP impact if we do nothing. So, you know, folks talk about a 4% impact to GDP if we increase by 2%, up to an 18% for no mitigation to a 3.2 increase. And if you look at, you know, what the United States has said, for example, and I mean, the United States energy is in some ways, you know, comparable to all of Europe. They're expecting that to transition, they're going to annually need to provide between 58 and 167 gigawatts of new energy plus 3 to 64 gigawatts of storage per year, which is quite large. And why would you be interested in space solar power? Well, because it's on the order of 60 times less carbon intensive than coal, even considering the manufacture and rocket launch. So you can see here from Asakura, Collins, Nomura, Hayashi, and Yoshida, they had compared that a solar power satellite produced on the order of 20 grams of carbon per kilowatt hour, which was lower than even nuclear. And if you did it in a bootstrapping manner where you use the SPS to power what you needed for the subsequent ones, it drops that in half. So, you know, much, much better than up to 111 times less carbon intensive than coal, even considering manufacture and rocket launch. And then, you know, it's been considered by the the International Association, Academy of Astronautics, that, you know, this could, in the end, result in something on the order of 5 million new jobs, and that each SPS, you know, might have on the order of 50,000 direct and indirect jobs. So there's a large potential for this to be a driver of employment. So let's talk about the scale of global energy growth, global energy electricity, and global energy infrastructure spending. So here are a list of you know, nations that show both their installed capacity in megawatts as well as their actual generation. On the right, you can sort of see, you know, how big China is and compared to everybody else and where Germany and France are. But on the left, I also have the total world capacity and the actual generation. And, you know, what I think is very, very important to foot stomp here is that if you look at the difference, we have 7.5 terawatts of generation, but we only produce 23.3 trillion watt hours. And why is that? It's because we have a global capacity factor of only 0.35%, meaning that most of the time, those power plants, you know, about 70% of the time, those power plants are offline. If power plants were 24 hours, you would actually only require 2.6 terawatts of 24-hour power, as space solar power provides. And so what I've put down here in these bold numbers is, you know, what this would actually require. So if you look at Germany, right, Germany has 250,385 installed megawatts of power. But really, it only, you know, if you could power it with solar power satellites, you'd only require 63,600 megawatts. You can see that, you know, partially because of their large commitment to renewables, which are terribly intermittent, they have a pretty low capacity factor. And even France, that has a higher capacity factor of 0.42, you know, really, you know, has way more capacity than they need for something with space solar power. So it's important to realize that we have to spend more than double what we have on our energy just because of the low capacity factor of rotating machinery. And then, you know, transition is really big money. So according to IRENA, global investment in energy transition last year reached $1.3 trillion. And I'll put that in perspective in a moment. But they're saying that yearly investments have to more than quadruple to 5 trillion in order to stay on the 1.5 degree pathway, and that a total of 44 trillion is required by 2030. And that we're going to need to reallocate, as we heard before, like 80% of the total energy spending is still on fossil fuels. And so, they're recommending 1 trillion be moved over to transition technologies. And then the UN level climate champions estimated that we would need on the order of 125 trillion by 2050 to rapidly transition the energy system, or nearly 6 billion a year. And McKinsey, which came out a year later, said we'd need to be spending 9 trillion per annum with a total of 275 trillion by 2050. And this is in my opinion, just a horrific misuse of capital, because for 275 trillion, that is enough to build 55 terawatts of space solar power in orbit, which today our entire energy system, all of it, is only 18 terawatts. So, I think space solar power could do better. And that's assuming, very close to what you heard the earlier speakers talk about $10 billion per solar power satellite. So electricity growth has averaged 2.5% from 2010 to 2019, and it is expected to grow very significantly, from 27 petawatt hours to 90 petawatt hours by 2050. So, despite all of our efforts, there are just too many people joining the developed world, and we're just going to need more energy generation. And to put this in perspective, right, that was at 2.5% actual growth. This author, do the math, put it on a exponential scale and said, if we continue growing at 2.3%, over, multiple centuries and thousands of years, where do we get? And what's really kind of shocking is if you consider, growing at our current rate, in about 300 years, you would need to cover the entire land surface of planet Earth with solar power, farms. And then, if you continued to, 400 years, you have to cover the entire surface of the Earth. And then, if we continue to expand, if humanity lives and continues expanding, by 1,400 years, we'll need to encase the sun in a Dyson sphere to meet our energy needs. Right now, though, energy has reached 13% of global GDP. That is astounding. Global GDP is about $105 trillion. And so energy would be, nearly $14 trillion. And our current energy investments per year of all kinds are about 2.4 trillion. And so, let's put that sort of in context. So world energy expenditures for space programs in total, everybody, United States, China, all of Europe put together, all of Europe looks like it's about 21 billion, comes to $103 billion, right? And then within the entire space industry, satellite manufacturing is maybe, somewhere on the order of 16 billion. So, if we look at that, I put this giant block as the total GDP of the world of, roughly 100 trillion. And if you look at this, like manufacturing is about 16% of it, agriculture about 4%, internet, communications, technologies about 15%, healthcare about 10%, transportation about 9%. And on the bottom, you can see, 1.5 rows are global energy, about 13-ish%. And then of that, about 1/5 of that today is electricity. Of course, everybody would prefer that more of global energy is electricity because it's so clean and versatile. And then above that, you can see, we're spending somewhere in the order of 2.4 trillion on energy infrastructure and 1.3 trillion on energy transition. And we need to be spending, like 5 times that much, in order about 5 trillion to stay on the pathway. And just, to put this in perspective, this tiny little black area right here, that's half of 1 square, is basically the total size of the total space economy. And of that, this little teeny upright rectangle, that's about, a quarter of that is the total government budget of all countries on space technology. And this tiny, tiny little square is satellite manufacturing. And of that, maybe like 0.3 billion or 250 million is currently spent on space photovoltaics. So that's just to give you an idea of where we need to scale. So here again is the total government space spending compared to the space economy, the European electricity bill, the global spending on infrastructure, and then the total amount of spent on energy. So it's just really important to realize that we're talking about, a market that is 140 times larger than everything that is being spent governmentally on space. Now, we've got a demand for power that is going to be moving, from right around a megawatt a year up to eventually like 5-ish megawatts, not including space solar power. And if you look at Starlink, Starlink, each satellite is about 5 kilowatts. They're about 4,000. They're now at, the sort of collectively, that's 20 megawatts, which is about 200 times ISS. So let's talk about where we are today relative to a single power satellite. So you can see Paul Jaffe has PRAM-FX, which was the one that the Navy launched on the X-37. It's a little larger than a dinner plate. You can see the Space Solar Power Demonstrator one that Caltech has on orbit now. And then you can see Spider Arachne and the Arachne payload on the bottom right, which is, it looks like about 2 dinner tables in size. And this is pretty much the pinnacle of where we are on actual space solar power technology. We are nowhere close to a megawatt. Now, this is what big solar is today. So what you see here are the IROSA arrays that were put on the International Space Station. Each one can generate only 31 kilowatts of peak energy. They weigh about 325 kilograms or 95 watts per kilogram. They cost about 35 million each, or about $108,000 per kilogram. And I'll come back to that later. This is a very interesting, this is AST Space Mobile's Blue Walker 3. It is solar panels on one side and RF on the other. It's essentially a component of a solar power satellite, which is quite large and interesting. You can see it wrapped up, all folded up. And then this is what China is talking about for, what they want to do as their 2035 pilot plant in the megawatt class. So, they want to be able to collect 24 megawatts. You can see that in comparison to, the ISS, what a multiplier that is. You can see that their mass that they're shooting for is about very close to the ISS, 300 metric tons. But this is going to be, 820 meters by 150 meters. So it's going to be significant in size. And so I've tried to actually put this into scale on the right. So you can see their 2028 demo is smaller than the ISS, and then their megawatt demo at the top is quite substantially larger. And then, like, here it is again to scale. So, ISS at 240 kilowatts, the Chinese demo of first 400 kilowatts, and then 24 megawatts, and then their operational design of a megawatt delivered and about 10,000 metric tons. Now, what I will say that's really impressive about the Chinese program is that everything is on a clear, critical path to get there. Everything makes sense as to what they're doing in order to retire risk for where they're going. But if you look at this in terms of those IROSAs I showed you, their 2028 demo is essentially 13 of those IROSAs. Their 2035 megawatt class is going to be about 774, which would be about, that's like, let's say, a couple a couple Starship class launches. And then, you would need on the order of 250,000 such modules for the full design. And to put this sort of in another perspective, up here, this tiny dot at the top is like a geocomsat, and this next larger, dot, here is about, what the ISS is. It's about twice that. And then if you look at the Starlink constellation, it's actually about 2 of these bars here. And then if you look at what you'd need for a gigawatt class SPS, we're talking this first cube. And if you wanted to, power like 10% of the UK or Spain or Italy, you would need to have about, 10 of those. And then if you wanted to, have, either 10% of Europe, or you wanted to have all of, say, the UK, Italy, or France, you're talking about something on the order of this big square. And then to really be relevant at the terawatts, at the global scale, the terawatt scale, you're talking about this giant cube on the right, which is approximately the generating capacity, of the USA or Europe, about 1/7 of all of our current generating capacity and about 1/18 of our total primary energy. So again, the vision is to build thousands of these in geostationary orbit on a time scale that's relevant. So is this possible? Well, I think so, actually, and help is coming. So if you look at what contributes to cost, it's principally launch cost and satellite cost and the per unit mass and the lifetime. And so much has changed. These are Paul Jaffe's slides that, we can expect, on the order of a 20% reduction in satellite costs, and perhaps as much as a 50% increase in power mass ratio. What he's showing here is an earlier model of one of the Caltech, which was something on the order of I think, 2 kilowatts per kilogram. And even with no reduction in launch cost, his numbers were that you could get to 10 cents a kilowatt hour, and globally, we're like 14 to 18%. Now, Starlink, I think, is a really interesting test case for this, because each satellite that you see on the left is about 5 kilowatts. And when you stack 60 of them together, you've got about 1/3 of a megawatt. Falcon 9 can deliver, 60 at a time, and Starship can deliver like 430 of these, or 2.3 megawatts. And you can see that, quite amazingly, for those of us who grew up in the pre-Starlink era, SpaceX was adding a megawatt every 3 months from 2019 to 2021, and then increased. And so if you look at like how the doubling rate is, we are like doubling the number of satellites currently at every 2 years. And we have, doubled the energy on orbit in the last year. So if that doubling continues, that would be a big deal. And let's look at this is the scale of difference between the highest power object in space, the International Space Station, and the amount of power on Starlink. And you can see that that's actually less of a scale change than going from Starlink to a solar power satellite like SPS Alpha that you saw earlier, that's like a 2 gigawatt satellite. So I think it's important to realize that we've already seen a scale change more massive than is required to go ahead. And then, help from Mars is coming, because Elon wants very badly to have a logistics system capable of emplacing a city on Mars. He is building something quite spectacular. He wants to be able to have a fleet of starships that is going to be able to enable this. And that fleet of starships is going to be able to do other things. So if you look at SpaceX launch history, they're also on an exponential curve. And the largest object ever in space has been the International Space Station till date at about 450 metric tons. And everything that's in space, all of it, is 18,000 metric tons that humanity has put there. That's not even 1/5 of an aircraft carrier in size. And a solar power satellite like SPS Alpha is on the order of 8,000 metric tons. And one Starship if it meets Elon's goal of launching 3 times a day, every day a year, could put 100,000 metric tons or essentially an aircraft carrier worth of size into space every year. And so then Elon tweeted out, he says, this is at the top left, if we build as many Starships as we have built Falcons, that's 100 vehicles, and each does 100 tons to orbit, that's a capacity of 10 million metric tons of payload to orbit per year. So let's consider what that would mean. It'll take me a moment to explain this chart. So at the top, you've got electric capacity, generation capacity, then you've got actual consumption, global consumption, and then you've got carbon output, and I've circled the world, right? So we have globally 7.2 terawatts of energy that results because of the low capacity factor in about 24 trillion kilowatt hours. And then we produce 36 gigatons of carbon. Now, if we had 10 Starships a year, that would give us 1 million metric tons of upmass, which would give us essentially 88 gigawatts per year up. But if we did what Elon is suggesting and had 100 Starships and 1 million metric tons, that would allow us to put up nearly a terawatt, 0.8 terawatts or 888 gigawatts per year. And that would mean that we would be adding, because it's 24-hour power, 7.78 terawatts per year, and we would be subtracting 7.78 gigatons of carbon. And as a percentage, that means that if you had such a system, every year you could remove 12% of global generation capacity. You could remove over 30% of our actual consumption needs, and you would be removing 20%, a fifth of our carbon emissions every year. So it would essentially take less than 3 years to solve climate change entirely if you had 100 Starships launching. Now let's look at scale by itself. So 100 times reduction is possible in 3.5 solar cells at the megawatt scale. So they said that we were producing on the order of 182 kilowatts per year, and that if you went to 50 megawatts, you would drop from $50 a watt to $0.5 a watt. And they didn't even assess what was possible above the gigawatt scale. So this is a chart from John Mankin showing the industrial learning curve that as you build more identical units, the cost of individual units drops. And so if you look at one-of-a-kind type of systems, they're $40,000 to $200,000. And as you come down, to 300, you're at like 4,000, and then even lower, you're at 1,000. And so, if you look at that same IROSA was 108,000, coming down to, one Starship full of them, about 300 of them, that's 9.7 megawatts. And if you did 3 Starships, that you could do 24 megawatts for just 330 million, which is quite startling. And we've known for a while that launch costs come down with volume. It was predicted that as you launch, they'd come down. And in point of fact, if you look at what was predicted for, the 60 launch rate, we're very close, right there with where we are with Falcon 9 and Falcon Heavy, and about to go way lower. And this is potentially the largest upmass. This is actually a chart from Ivan Becky showing that this green line is the total upmass required from space solar power. And then, you could imagine you would want to be launching equatorially from the sites that are there, because you want, you'd want to launch first to LEO or MEO and then to GEO. And then the final thing you get is help from Luna. So there is this idea that you could send a small seed to the moon and then construct from lunar materials solar power satellites, has been evaluated before. It's great to hear that ESA is evaluating it again. A very interesting paper on lunar self-replication suggested that once you put down a lightweight seed factory, you might be able to, double and double and double in order to fulfill global energy demand in a year or certainly less than 5 years. And so the last thing I'll just say is the remaining problems, right? These are all just technical engineer to cost and scale problems, but these are all truly engineering problems. The remaining problems really depend on human will and lie in the realm of politics and persuasion, and they include, can we get the frequency allocated that we need, because it's very similar to wireless frequencies. There is plenty of money, obviously, for energy projects at scale. And as I said, 275 trillion by 2050, would build you an entire 55 terawatts of energy. And even at the lower, levels, you could easily be doing, 658 at the 7.6, at the 5 trillion that they say. And then finally, you've just got a question about whether or not the Not in My Backyard or NIMBY for launch and rectenna siting is going to get in the way. All right, and that's the end of my slides.
Thank you, Peter. So, very, very interesting presentation there, Peter. Any questions from the floor? I've got to say, I noted here, you said it's we've got the money, but you're talking trillions, no? In terms of we've got the money to push out. Is it 7 trillion? I was trying to make a note, but you were too quick for me. Your slides went far too quick for me. But did I see 7 trillion a year we needed to pump out to get the return? Which for me is, wow. I mean, people talk billions and it's difficult, but trillions? Can you just maybe explain why? I guess when you look at the scale of that size of what we're using on agriculture and all these other areas, it's small in scale, but how do you see we can, using the arguments you presented today, how do you see we can get that money, get access to that money? Because I don't know if you know how it works in ESA, where we, every 2 years we're sat there for lobbying for 6 months and trying to get buy-in from all the delegates, and that's for our 18 billion. So I don't know how we get 7 trillion a year. Do you have any ideas on how we get that buy-in?
So first of all, what I'm pointing out is that the world is saying that they're going to spend, that we are spending 2.6 trillion in energy infrastructure, period, already, and that we need to be spending on the order of 5 trillion just in energy technologies aboard. So someone's going to get that money. My argument, is that it would be much better spent on space solar power because your capacity factor is so high, it's so flexible, and so scalable, and that for the amount that they're projecting that is going to be needed to be spent, we could meet that goal many times over with space solar power. Now, that is not the cost of a developmental system, right? I concur, with what others have said, that the cost to get to the first full-scale system is likely $13 billion, of which a small fraction of that is appropriate for public monies. So we don't, financing a public power plant wouldn't be something on an ESA budget, and that's like a $10 billion project. But to retire the risk and showcase that it can, and develop the technologies, I would guess that would be sort of in the $2 to $10 billion over a decade time frame, which I think is still significant for for government budgets, but is not appropriate. These larger numbers are numbers that are allocated by capital markets because there's an existing consumer demand.
Thank you. So that was my question. Yes.
Yes, it's a great presentation, definitely on a high level. Amazing. One question is how really lunar or the moon can support in this activity. I see more challenges, engineering challenges mainly to manufacture something on the moon, launch it from the moon, bring it to GEO, especially when seeing the drop of launch costs from the Earth. So what's the concept behind, or how real are activities going on there?
So, obviously there is a significant step in generating manufacturing and launch capabilities from the moon, that you're correct. So I think that the first generation of solar power satellites, would certainly come, from the Earth. But I probably almost as soon as the first ones are being built and the market is proved, the advantages of the moon are really substantial. So, it is, several multiple times less energy to get off the lunar surface into GEO than to get from the Earth's surface to GEO. And it requires no rocket fuel at all if you use electromagnetic launch. And we know from past NASA-sponsored studies that you can build a lunar power satellite that is like 99%, certainly upwards of 95% lunar material. And so, to the extent that you obviate the need for that mining and processing and launch on Earth, you're also subtracting those carbon costs. So the concept, essentially would be that, you go to the moon with robots that can print copies of themselves. They mine the lunar dust for the materials you want. They probably send, that refined material to geostationary orbit, where you've got 3D printers that are printing at least the structure. There are ideas for lunar cells. There are ideas for concentrated solar thermal power satellites using lunar materials. But you would essentially be launching, to geostationary orbit, either directly or via L2, via a catapult, an electromagnetic catapult. And that requires an amazingly less amount of energy. And since you're transporting, ultimately millions of metric tons, that ends up being advantageous both in terms of energy return, as well as in terms of climate impact.
Okay, thank you.
So, is there any more questions from the floor? I can't see anybody with a hand up. Oh, yes, there's one there from Marek.
All right. This is Matt Krieger from Switzerland. I have one question on your assumption of economy of scale. I'm an expert in economy of scale in the semiconductor industry, and I think there the automation is mainly the driver for economy of scale. So the more equipment you have, the cheaper is the production, for example, of production equipment, and then non-recurrent engineering goes to zero. But if you do that with gallium arsenide, I have a question mark. First of all, I'm not sure if $50 per watt is realistic for current manufacturing costs, but you claim 0.5 for gallium arsenide, which is 2 orders of magnitude. And I would like to remind you that gallium is a very rare metal. And even China has recently actually restricted export for today's current consumption. And we would need a lot more gallium. So are you sure that gallium is not a critical cost element in economy of scale as a material cost? Because this is maybe a constant in the equation and not scalable. This is a question. I'm not saying this is true. It's a question.
Yeah, I mean, of course, what I was showing you, was the analysis of the United States National Renewable Energy Laboratory, and not my own analysis. So I don't know what their assumptions were in terms of scale and limit of gallium arsenide, or what else they thought, might be a replacement material. I would say though that I don't think that this is there are such a diversity of design ideas for solar power satellites that range all kinds of different from solar photovoltaic of a number of different varieties of solar photovoltaics to solar thermal. And the point I was trying to make here was not that 3.5s themselves were necessarily the right architectural answer. The point I was trying to make was that when most people try to think about the costs of solar power satellites, they tend to think linearly and just add things up at current prices rather than realize how scale truly changes your fixed costs or changes the cost per unit of what you're doing. And so that's the larger message I'm trying to provide, is that you cannot assume that the cost of something like, for instance, IROSA is going to be the same at the gigawatt scale that it is at the kilowatt scale. We have very solid understanding of manufacturing curves and how parallelizing operations and reducing those non-recurrent costs drives down the individual price and thus the total system price.
We can discuss also in the panel tonight, because I have some inputs in my talk this afternoon that are complementary. So let's stop here. Okay, thanks.
Thanks, Matthias. Thanks, Peter. So thanks again to Peter. Much appreciated. Very, very nice presentation there. So thank you, Peter. And for those online in presence, we're going to have a break for lunch. I'm getting hungry myself. So if you could be back 5 to 1, if possible, to just before 1 o'clock, because we want to kick off at 1 o'clock sharp. Okay. Sorry, 2 o'clock even. Sorry, can't time travel yet. So just before 2, we want to kick off at 2 o'clock sharp. Thank you, everyone. Okay, everybody. Thank you. Can you hear me online, Jose? Okay. So thank you, everybody. Welcome to our afternoon session. I hope you had a good lunch and you're all raring to go, recharged for the afternoon session. So if you'd like to take your seats, please, and remember to switch your mute off your phone and any speakers on your laptop switched off when you're in the auditorium, please. So very pleased to welcome our next guests. We've got Mr. Arthur Woods, who's the CEO of Astrostrom from Germany. He's a Swiss independent researcher, an astronautical artist with 2 art in space projects that have been successfully flown on the Russia Mir space station. The Cosmic Answer sculpture in 1993 and the Ars et Astra, the first art exhibition in Earth orbit in 1995 during the Earth Mir 95 mission. His work has been exhibited in a number of international space and art exhibitions. Arthur has co-managed several studies for the European Space Agency and the International Academy of Astronautics, of which he is a full member. Currently the co-chair of the Moon Village Association's Cultural Considerations Working Group, he was fortunate enough to grow up in the vicinity of the Kennedy Space Center in Florida, and between 1959 and 1970, he worked at the Space Center in 67-68 during the Apollo program. He's co-author of The Space Option and Greater Earth Concepts. In addition, we have Mr. Andreas Vogler. Andreas is a Swiss architect who works in the field of aerospace art and architecture. His speciality is design-driven system innovation in various fields of technology, and this encompasses architecture, transportation design, robotics, and specific to space, including designs for habitats, manned rovers for the Moon and Mars, as well as inflatables. As scientific assistant at the Technological University Munich in 1999, he participated in zero-gravity flights with NASA Houston and with his students, testing equipment for the ISS. Like Arthur, he is one of the few pioneering artists to have successfully realized an artwork designed for the microgravity environment of a space habitat. Atlas Coelestis 0G, which was sent to the ISS ION on the STS-134 in 2011. He has an extensive portfolio, and both Andreas and Arthur have recently completed the ESA OSIP study, the Greater Earth Lunar Power Station, and it's part of the Solaris promotional video, which I trust, that they're going to show us today as well. So, guys, over to you.
Well, I'm going to try to share my screen here. Share. Okay.
That's looking really good, our end. We can see your screen with your slide deck, and it's full screen now.
Okay. Well, thank you very much for the introduction and for the opportunity to be here. It's fantastic. Great presentations this morning, and I'm sure there's going to be more great presentations today, later on today, because this is a really important topic. And a big thank you to Sanjay for the little introduction he gave this morning. That was unexpected, so we're really happy to be here. Anyway, the topic of our presentation, Greater Earth Energy Synergies. This is a result of our Greater Earth Lunar Power Station study we've just recently completed for the European Space Agency. And the goal is solar power satellites built mostly from lunar materials that are robotically assembled in lunar orbit. And besides Andreas, we had Patrick Collins on the study team and Dmitry Kastrovics, who is our animator. He's responsible for the graphics like the one you see right now. And later on, we'll show some video. So let's go here. I'm not getting my go. Okay. Back in 2022, early 2022, ESA made a call for clean energy, new ideas for solar power from space, and out of 85 submissions, they selected 17 and funded 13, including our project, which is, we're very happy to have been able to do this. And our concept is a lunar power station providing power to the lunar surface, and it also has a habitat which gives it a human dimension to it. So just a call out to Mike Snead. The name of our company is called Astrostrom. That's German for astroelectricity. So he was inspiring us to go this way. So we're spreading the idea of, in the German part of the world, it was something that's very easy to understand. And just a few words about the Greater Earth concept. It's actually a new perception of our planet based on Earth's true cosmic dimensions, its gravitational influence, which extends out 1.5 million kilometers from the center of Earth, and it creates a sphere about 3 million kilometers in diameter, and through this sphere, 55,000 times as much solar energy passes through the sphere than falls on the surface of Earth. And it has also occasional passing asteroids and the moon, which is very important. Now, this is marked by our technology today at L1 and L2. At L2, you know, we have the James Webb Telescope looking out into the cosmos, soon to be joined by the Euclid. And at L1, we have the Discover satellite, the Deep Space Climate Observatory, and the EPIC camera, which is taking a picture of the Earth every 2 hours. And the picture you see behind here is actually a picture from the EPIC camera, and it introduces what we're talking about today. Now, we all know that climate emergency is a very big issue, but it's also coupled, interconnected with the energy quadrilemma, okay? And that's 4 aspects of energy: the affordability, security, sustainability, and accessibility. And I will touch on these 4 aspects in our, not specifically, but throughout the presentation, we will address these 4 aspects. Well, speaking of the fossil fuels, this is a chart from BP done in 2020, and it shows you that fossil fuels are actually very finite. And actually, these numbers would be less now because it's 3 years later. And of course, there's technology to extend this, but we know that the fossil fuels at one day are finite, and actually, they're too valuable to be used for energy. Now, this is another picture about fossil fuels, which shows you from 1800 to 2021. And as you see, this very interesting corner here, that since Sputnik in 1957, you see this incredible increase in the use of fossil fuels. Now, this shows you how dramatic the situation is, but if you look at it from a slightly different perspective, maybe it was fossil fuels that has enabled, the fossil age has enabled the space age. And indeed, if we look at the graph from another perspective, these are the objects in orbit right now. And right now, it's approximately 12,000 objects in orbit as of 2022, which shows you what's happening in space. Now, as mentioned earlier by our colleague from Fraser-Nash, ESA did 2 cost-benefit studies this morning and this past year, and we had a report about the one from Fraser-Nash this morning who looked at the Cassiopeia concept, and Roland Berger and OHB, they assessed John Mankin's SBS Alpha. Now, we've looked at the Cassiopeia concept basically because it has less mass to orbit, so it's more interesting. It's 2,500 metric tons as opposed to 7,500 tons for SBS Alpha. But as they reported, they have their 10th system could be deployed for a cost of about $7.6 billion. And this is very interesting. It makes it very competitive with nuclear power, which today in Europe costs about $9 billion per gigawatt to build. Well, 54 SBSs, which they're predicting that could supply some significant energy by 2050. This would cost about $418 billion, but the key thing in this graph here is the 134,514 metric tons for launching these 54 SPSs into geostationary orbit. Now, underneath you see how many launches this would require based on the scenario, 86 to 119 Starship launches per SPS. Well, Elon Musk last year gave a presentation about Starship, and Peter said something about this in his presentation earlier. And he said in that presentation that to date, 15,517 metric tons have been launched into orbit since 1957. So that graph we can go back to. Anyway, he said that the total mass per one Starship launching 3 times a week after 1 year would be about equivalent, 15,500 metric tons. And actually, the total mass of 10 Starships launching 3 times a day actually would hit 15,000 every 5 days. Now, this is that 54 SPSs that we showed in the previous slide, and here's the amount of mass that they would take to get into space. And this last one here is also from Musk. This is how much he wants to launch into space in order to develop his Mars city. So more than 1 million metric tons into space. So, well, what if we could reduce the amount of mass into orbit by 80%? So if 80% could come from somewhere else other than Earth, this would be a very big advantage for all of these programs. So where is that other space, that other place? Well, actually, Kraft Erica told us about it in 1984, and he said if man wanted to become a spacefaring species, he would have given man a moon. Show a little video.
Welcome to the Greater Earth Lunar Power Station. We are going to the moon to build components for solar power satellites from lunar materials, which could help mitigate the launch bottleneck and the environmental impact of launching many solar power satellites from the surface of Earth. This is a multi-trillion euro opportunity which addresses the climate and energy crises on Earth. Can you think of a better reason to go to the moon?
Well, I hope you enjoyed that. You might have recognized some of those images. They've showed up in the Solaris video. And now I'm going to turn over to Andreas to talk about the system architecture that we've investigated. And just a small word on the video. All of the things in the video that you saw have been researched in the study that we did. And so these were just ways to make them visual. Okay, Andreas?
Yeah, okay, thank you, Arthur. Fantastic. We basically have been looking on what it takes to start the fabrication on the moon. And obviously, all of you know all the studies done in the 70s and so on. And we had a relook onto that with much lower launch costs and robotics technology. And our kind of setup is to use small robots which are scalable, but also have a crew of people, basically not to have 100% automation, but maybe have a 90% automation and people for troubleshoot technology. So in that way, we think we are very flexible. And obviously, we would start mining, processing, and fabrication. First, we need energy. So we set up PVs, but then the plan is to start to produce PV panels on the moon to create more energy, and eventually also make structural elements to build a power satellite at EML1 of the Earth's moon system, to even send more energy down to the moon to scale up production even more, and to eventually be able to build more power satellites, which can then be sent to GEO in Earth. And obviously also we need a transportation system for that. And many studies in the 70s actually, or one study really, has been proposing the mass driver as a catapult to shoot up material to L2, not to L1, because it could hit Earth if it goes wrong. So we studied that intensively, and many papers writing about that, and we basically came to the conclusion that the lunar space elevator may be a more interesting choice for setting up a transportation system between Earth and the moon. Next slide, please. So we thought, what does it need to have a really continuous logistics between the Earth's orbits and the moon? And we really came up that we kind of need, as a base, standard interface cargo containers, which we just can change with robotic arms. So we would need reusable heavy lift launches to set up the system initially. Maybe stay with the other slide, Arthur, we come to that. But we would install a cargo relay station at the equatorial orbit around Earth, so we could later use small rockets, be launched every 90 minutes basically, to reach that station, where of cargo containers could go on a cislunar cargo shuttle, which would go to L1. And from L1, we have a lunar landing gantry allowing soft landing, basically, of larger materials, everything in the region of 10 tons. So 10 tons to LEO would result in 10 tons soft landing on the moon. And while this system is developing, we could start building up a space elevator deployed from L1, and basically then be scaled up to transport more and more cargo into this system, and having the rocket just as backups. Next one. So basically there's, at the moment we know Europe sadly doesn't have its own access to space. There's this study running, Protein, looking at the new reusable heavy lift launch system. So this is work. Actually, yes, we need rockets to start anything in space. Next one. But the future could be
a combination with rockets and the space elevator. And a lunar space elevator, other than an Earth space elevator, is actually interesting because it could be built today with existing materials such as Dyneema or Cylon. So we don't need carbon nanotubes. Obviously, the stronger the better, but we could start with Cylon production. And we think it's well worth to study that system more deeply, how it can be scaled up and be expanded to really make a logistic axis between the moon and Earth. Next one. Arthur, I'll leave to you.
Okay. I will pick up as the three key technologies, the lunar space elevator, Andreas just described, and we have two other key technologies that we have discovered and investigated for our concept. One is lunar basalt, and the other is lunar solar cells. Now, this is obviously very important, how to develop photovoltaics on the lunar surface, and we were looking at this technology that's being developed in Vienna by Crystal Solid GmbH, monograin layer photovoltaics, and it's a different concept than the traditional photovoltaics. You have little crystals that are in themselves, little solar cells in and of themselves. Now, this is what their fabrication facility looks like right now, and if you could just imagine this being packaged into kind of a container and sent to the moon, we could this is our idea of modularity, something like this. Now, in Tallinn Technical University, a team working with ESA is investigating the development of lunar MGLs, monograin layer things from pyrite. And this is a picture of one that they fabricated. And as you see, it's obviously very lightweight. It's very flexible. And the advantage of this kind of technology over other kind of wafer technologies is that this could be manufactured at any size and any shape, and it doesn't really matter, and it can be really interconnected. So this is very, very interesting for us, and it's at the very beginning of the technology, but the outlook is very positive. Like I said, this is being looked at also being sponsored by the European Space Agency, this research. Now, the other one is that from the Institute for Textile Technique in Aachen, they're looking also at basalt, and this is a screenshot from one of their videos where they could make moon fiber. Now, basalt can be used for all kinds of purposes. It could be extruded, it could be made into fibers. And here, this is their fiber concept. And if you look down here, they actually say you could create within 1 hour 180 kilometers of moon fiber. Now, moon fiber actually has a very high tensile strength, so possibly, potentially, this could be applied to our lunar space elevator at some point. So, the next video.
Mining the moon, beneficiation, processing, fabrication and transportation of the components for the Greater Earth Lunar Power Station.
So, Andreas, you want to give?
Go ahead. Our time is running out, I think.
Yep.
Just go ahead, Arthur.
Okay, well, just a couple of concepts, these modular factory concepts that you saw in the video here, doing mining, beneficiation, processing, fabrication, transportation, and infrastructure. Like I said, all of these things we looked at very intensely, and that's how they've entered into our video presentation. So I'm going to move on to the business case, okay? And actually, as Peter said earlier this morning, it's really, really big what we're talking about. And Europe's net zero energy transition, this was published by Bloomberg last year. They estimate that it is a 5 trillion investment opportunity to reach net zero. Now, this is what electricity production in Europe looks like right now. As you see, we have it. This is based on the latest statistics we got from BP, average over 3 years. And if you combine fossil fuels, hydroelectric, nuclear, you have 75% of baseload power. Now, the International Energy Agency has done in their outlook in 2022, they're predicting the electricity projections, and they think very, very minimally 75% increase will happen by 2050, all the way up to 150% increase to reach the net zero emissions. Well, we've looked at this, and we're taking kind of a more conservative approach. We're looking at 103%. And what we wanted to do is if space-based solar power could provide the same amount of electricity to Europe that nuclear power does today. And it's like 22% right now, but we look to the future, and here we have space-based solar power providing 11% in this case. But this is very interesting. In this case, fossil fuels, hydroelectric, nuclear, and space-based solar power only provide 34% baseload power. So you see the real actually, one of these energy dilemma aspects right here. How do we provide more baseload power? So this is a very, 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 very big challenge for all of us. So anyway, as we said that 78 SPSs built from lunar materials, or not only, but also from the Earth, would provide this amount of power. And you'll see in the next slide about how we look at it from a profit motivation. And this is our concept, LCOE, of a levelized cost of electricity for a similar space power satellite as Cassiopeia, but built with lunar materials and over a 30-year operational lifetime. And we're launching 400 metric tons of hardware to the Lagrange point, Earth-Moon Lagrange point 1. That's going to cost about 1.1 billion. The rectane on the land is 1.5 billion. Anyway, we come to a total cost of 5.6 billion for the SPS if we build it from lunar materials. Now, that's also 3.6 billion for the actual hardware and getting into space. Now, this gives us a pretty interesting levelized cost of electricity at 74 euros per megawatt hour, which is very, very competitive. And we're basing kind of a profit motive on the wholesale cost of electricity at about 15 cents per kilowatt hour. So that gives us a 17.7 billion net profit for one SBS. And if we go back to this slide, if we would have 78 of these, that would give us 1.4 trillion over 30 years. So now this is supplying 11% of energy here. Launches from Earth only production would require 6,708 launches to get the 78 SPSs up there. And if we need about 467 launches to install our operations on the moon, and afterwards we would have maybe 2,184 launches to reach that 78 level. Now, I think the number on the left is probably too low, and the number on the right is probably too high, but that's going to be looked at in the future. Anyway, just an overview of what this would cost. In our estimates, we think of an infrastructure investment of 99 billion euros. Included in this is 16 billion for SPS development, and that can be for lunar and or terrestrial SPS. So that's a number that was put out by Fraser Nash that they think it would take to do the first SPS. We earmarked 10 billion for a reusable heavy lift launcher. Now, Ariane 6 cost about $4.5 billion, and so we think 10 billion, if we have an accelerated program, is realistic. And then for our lunar space elevator, we're looking at 11 billion. Even though the original one could be, according to Charles Radley and Eugene Eubanks, the first preliminary elevator could be deployed for about 2 billion. So we have 43 billion for the lunar operations that you saw in the videos, and for low Earth operations, 11 billion and 8 billion for the human crew operations. Now, if we compare that with Earth launch, we come out with our initial investment costs at 99 billion compared to the 16 billion. We come up to a break even after about 20 SPSs. Well, how to do that? We're proposing it's going to need an international, multinational organization to underwrite the risk, and we call it the Greater Earth Energy Organization. And we set it up on an idea that we have anchor stakeholders, which would be basically countries who need energy, and they also profit from energy sales and taxes. And the way we set this up is we use population divided by the per capita, so you have a prorated national contribution that is actually fair for everybody, and so the more countries that are involved, the less contribution per country. And just to say that the 99 billion is 2% of the estimated 5 trillion European energy transition expected costs. And so how this would happen is in the first 2 years, we would look to raise 10 million to set up this organization. The organization would become operational with about 100 million budget in 25 and 26. And then after that, it would be providing 10 billion a year to underwrite and to de-risk this project and to make it happen. So we actually have a plan we're not going to go into here. This is our roadmap of how we can develop and realize solar power satellites from lunar materials. But I think the next slide, which Andreas is going to explain, is much more interesting, and it's about a flywheel effect. So I'm going to turn that over to Andreas.
Yes, but I'm going to be short on that because our time is over. Maybe some of you have heard of the flywheel effect. It's often named with Amazon, who started in the 1990s selling books over the internet, and today is one of the biggest merchandise platforms, cloud computing and whatever, because they always reuse their potential. And we think that with the current energy market on Earth, we would have an initial driver to really start a lunar economy, which would lower thresholds basically for everything, because with mining producing propellant, you lower transportation costs, you lower the market entry for other startups, you can produce power satellites, you produce more energy on the moon, you can do more production, you can deliver power satellites to the Earth, sell the energy, you have more space investments, and eventually with the L1 harbor you create, you can take off to Mars or even deep space exploration. So one thing will benefit the other one, and really we have a big economy rolling, driven by today's terrestrial energy market situation.
So I'll leave it at that. Thank you very much for your attention. Sorry if we went over our time. We tried not to.
So thank you, gentlemen. You're not much over your time, so I'm not too worried. Thank you. Unlike a couple of years ago, we were quite a long way over time. Was there any questions from the floor?
I have a question. Thank you for the presentation. One of the things, so I really liked your concept and your renderings, but can you tell us a little bit more on how you plan to tackle the challenge of lunar dust?
Yes, actually, we don't think it's such a challenge. Obviously, we need to understand more, but we know that the Chinese did some tests and measured how much dust is grounded on a platform which they measured, and it actually wasn't so much. We were expecting much more because of sunrise and sunset electrostatical movement of dusts. But else, everything which is on the wheels and running, obviously we would sinter roads, we would have cleaning robots, and we just would try to keep everything as dust-free as possible. Obviously, gears have to be developed which are dust-proof, but similar gears are existing in today's mining industry. There will be challenges, but we think the dust problem may not be so severe as we think today.
Thank you, Andrea. Any more from the floor? No. So thank you again for your time, gentlemen. Very, very nice demo slides. Vision.
Thank you very much. Bye.
Thanks. So we have the pleasure of now introducing Dr. Piotr Marek Kaminski, and he's a scientist at the Central Research and Technology Department of Airbus, where he works on the post-next generation antenna systems for aerospace applications. He is presently one of the leading members of the team developing power beaming technology at Airbus, and he's concretely developing these in a lab. As a person, he is passionate about new ideas in technologies and is motivated by the impossible problems. So very nice. Previously, he worked at the Radar Technology Department of the TNO in The Hague and holds a PhD and MSc in Electrical Engineering from the Technical University of Denmark. He originally comes from Lodz, Poland, if I said that right, where he completed his bachelor studies, and he's worked and lived in 6 countries. So we're fortunate to have Piotr with us today. Fantastic. So over to you, sir. Thank you.
Okay, let me share my screen with you. Okay. Okay, so my name is Piotr Kaminski, as I said, and I come from Airbus Central Research and Technology Department, and this is where we basically this department leads the development of power beaming technology at Airbus. And before I go to my presentation, I want to show you one more video. Closer to okay. Before I go to my presentation, I want to show you one more video. Hope you will be not bored by this. And this video was published to somehow raise public awareness of our demonstration that we had last year in September in Munich. One second. Okay. So how this future is going to look like? And this is the first slide. So maybe like the first. So the first difference that I noticed compared to other presentations was that my presentation is entitled Power Beaming. So we don't, let's say, generally at Airbus, we don't focus on space-based solar power, which is like the end goal towards which we aim and which motivates all the studies. But we focus more on the development of the power beaming technology. And you can use it for many other applications, like ground to ground, ground to air, air to ground, and all the others. And we hope to develop it step by step. And the holy grail is the space-based solar power, but there will be many other applications on the way. So, but anyway, in the future, in 2050 or 2060, you can imagine many of these large space-based solar power plants orbiting around the Earth. Some of them will be beaming energy to the Earth's surface in a confined beam to some large antennas receiving on the surface of receiving power on the surface of the Earth. However, this energy could also be redirected to other places where it's needed. You could use it also to power aircrafts, as you could see on the video. You could use it, what's quite important, you could use it to extend the range of drones, for instance, and usually they have very limited weight that they can carry. And so if you are able to beam them, beam power to them, then you could extend the range, you could add some other applications to them. This could really improve the applications of some of these drones. And you could imagine that we could be able to create like a network of energy in space. We could relay this energy from where it's needed to any other place. And this is quite, let's say, interesting for Airbus, because Airbus is working on these flying objects, flying platforms, and bringing this energy utilities to the third dimension, which is air, away from the Earth's surface, is quite interesting, let's say, for us. But how are we going, let's say, to achieve this? So last year in September, we had this quite successful power beaming demonstration, end-to-end demonstration, where we captured sun's energy with solar panels. Then this was transferred to the transmitting antenna array. But before that, this power had to be converted to the RF energy. And this is usually done with radio frequency amplifiers. And actually, they constitute a bottleneck for efficiency of the system, because most of them were designed for wireless communication applications or for radio applications. And so you had to make a trade-off between the efficiency and the bandwidth. In our case, we don't need bandwidth. Yes, you can use a single frequency to transmit this energy. That's why there is also a lot of room to re-optimize these amplifiers in the future and tailor them specifically for this application. But anyway, let's say afterwards, the energy is converted from DC energy to RF energy, then you can feed it to the antenna array. And the antenna array also works in a bit different way than all the others. It focuses the beam, yes? So it's not spreading the energy as all the other antennas for wireless communication or for wireless communication. It's focuses the beam, keeps the beam confined in sort of a pipe, you can imagine. And we can have a 95% efficiency, beam collection efficiency, when it goes from the transmitting antenna array aperture to the receiving antenna array aperture. And then on the other side, it's received by the rectenna, by the receiving antenna, which is called rectenna, and it's called rectenna because we have rectifiers integrated with the antenna, which rectify the RF power and convert to the DC power, which can be subsequently fed to the network. And also during the demonstration, we have used this power to power the fridge, in which we had non-alcoholic drinks inside for the audience to enjoy it. But we could also we also had an electrolyzer connected there because and this is actually quite important for Airbus because you might imagine, you probably know that we have this project where we work on green hydrogen airplanes, but it's actually really green only when the hydrogen is also produced with renewable energy sources. So this could be a technology that could provide a way to generate this green hydrogen. And of course, you could use it to power up the cities of the future, as already some countries are already investigating. However, we will not be able to do this alone. Maybe before I go to this one. So this demonstration was in cooperation with an external company, but it was also like very inefficient, very heavy, and very bulky. So basically, you cannot bring this up in air or to space. That's why we have started our own internal development, funded by Airbus internal funds, where we work on an improved demonstrator already now from the beginning of this year. And we want to increase the efficiency of the systems by several times. We want to beam the power of hundreds of meters, and we will beam like several kilowatts of power. And what's most important, we will also make it fly. So this will be a flying demo. It will be ground to air, and we'll also try to do it air to ground. And I will tell you a bit more about this on the next slide. But this is the first step, and we will not be able to, let's say, bring this technology to space if there is no contribution from the government, and if there is no external funding. And this was already mentioned by the previous speakers, that the public involvement is quite important for this project. And here you can see all the publicity that we got, let's say, after our demonstration in September. So some of my colleagues gave all this, gave all the interviews to all these newspapers and TV stations, trying to spread the word and disseminate the knowledge about the power beam technology. And it's, let's say, quite important to get the public aware and familiar with the technology, that is completely safe for them, so they don't have to be worried about this. But it also gives us quite important, let's say, leverage when we talk to some regulators and like regulators, governments, and also energy sector companies. Yeah. But as I mentioned, the Airbus approach is to do it step by step. Yes, so we don't aim to develop the space-based solar power straight away. We want to go first from ground to ground demonstrations to ground to air. For instance, to power some of the drones or hubs even, to extend the range and beam some kilowatts of power there. Afterwards, we can use it, for instance, to assist flying taxis and also use it to extend the range and reduce the weight of the batteries that they carry. You can imagine also powering some of the satellites. Maybe the airplane of the future could also be powered, or at least assisted in the takeoff, because in the takeoff it takes 15 to 20% of energy. If you can beam power to the airplane when it's taking off, you could save quite a significant amount of energy on that. And only after, let's say, the technology matures and is efficient enough and lightweight enough to bring it to space, only then we would be ready to work on this kind of projects. And this, let's say, all of this, we believe that all of these projects have to be done, let's say, in collaboration with external partners. That's why we are trying to keep the energy sector involved from the beginning. And we are already now in talks with some companies like Siemens and Total, with whom we discuss all the use cases. And also the other smaller companies like SMEs and startups, they are very much needed, let's say, to accelerate this technology. So I will not go into details here, but as I mentioned, at the Central Research and Technology Department of Airbus, at the beginning of this year, we started this project on the power beaming technology from ground to air. This is just an artistic impression of the technology, but the real demonstration is going to take place next year, at the end of next year, or the beginning of 2025. So most likely, I think you will hear about this again in the news, as you have heard about the previous one. But as I said, we are aiming to bring the efficiency up of the system quite significantly to the level of, let's say, 40% or so. We will beam several kilowatts of energy over the distance of several hundreds of meters and to the receiving antenna, which is also going to fly on the height of few hundred meters. So you can imagine that there are many technical difficulties that we are facing, but the project is already on the way, and this is the first step, let's say, to bring it to the air, and then we will work on the next steps and hand it over to other divisions of Airbus. But in the meantime, let's say we have very close discussions also, as I mentioned, with Siemens and Energy. We are basically having weekly updates, monthly updates with them. And they are providing some use cases for us, advising us on how to integrate the system in the grid, about some potential difficulties that we might face in the future, and all the other things that you can imagine, let's say. And recently, there was also a strong interest expressed by NATO in this technology, because you could also use it to power remotely forward operating military bases, and to provide power to the areas where you cannot access, but the power is very much needed. And this could be very useful in this case also. So let's say we are in discussions with all these partners. We are working on this demonstration that's going to happen next year already. And as far as I am aware, we are the only ones working on the real demonstration of this technology in Europe. Yes, so we are not only doing the paper studies, as most of the companies in Europe do it right now, but we also work on the demonstration of the technology that's going to happen next year. Okay, so that's it from me. If you have any questions, you can ask me. If you have any technical questions, I can also answer them about the technology. So yeah.
Okay. So we'll first take some questions from the floor. Sir, yes?
Thank you for your presentation. I have a question on the air balloon picture. Is it something you bring the panels with the balloon system, or is it just for demonstration on the slide?
Initially it was just an artistic impression, let's say. Yeah. But we want to lift direct receiving antennas somehow, and we want to keep it stable in air, let's say, more or less.
Okay.
So the balloon might be there in the first demonstration, yes. Yeah.
Okay. Thank you.
Yeah. Yes. Yeah.
Around the efficiency, you mentioned 95%.
Beam collection efficiency.
Beam collection efficiency. So on the receiver end.
So this is between what is at the output of the transmitting antenna array and what is picked up by the receiving antenna array. So basically, what is not lost in the transmission.
Okay. And do you have an idea about also the conversion efficiency? What you need to convert the electron. So you need to convert it to the electromagnetic wave, and then you need to convert it again to electricity.
Yes.
I assume there will be a small loss as well, or.
Usually for receiving antenna arrays, it's easier, I would say. The efficiencies are higher. You can expect something on the order of 70–80%. But it's more difficult on the transmitting antenna array side, mostly because of the amplifiers, yes. But this is also one of the reasons why the frequencies that are used are usually not too high, because for high frequency amplifiers, the efficiency drops off quite quickly. So usually people talk about this 2.4, 5.8 gigahertz. And there, as I said, there is a lot of room for improvement, because all the amplifiers were developed for wireless communication and radar purposes when you need this big bandwidth to transmit data. Here we need only a single frequency. So in principle, you could redesign and re-optimize these technologies specifically for this application where we need a single frequency, and you could bring this efficiency up quite significantly probably. Right now, let's say what you can expect is around, let's say up to 60%, I would say.
Okay, thank you.
I think you're second. I think it was somebody. Oh.
Okay, efficiency was one of the questions. The other thing is when beaming power to airplanes or anything up in the air, you need at least to have one big aperture, right? So what does it mean for the, I assume the big ground aperture when beaming power to a aircraft?
Yes, yeah.
And what?
I mean, so then if you beam, okay, let's take the case of beaming power to the aircraft.
Yeah.
So then, I mean, you can either do it from space or from ground, yes? From space, it might be easier because it's closer, and then the transmitting antenna aperture is smaller, yes? Because the size of the transmitting antenna aperture scales with the distance over which you transmit, like generally speaking for this technology. Because you want, and this is because you want to keep your beam confined. Otherwise, it will start spreading and you will start having beam collection, like losses in your beam collection efficiency and so on. And then there is a trade-off, yes, between the size of the receiving antenna aperture and the size of the transmitting antenna aperture. If you make your transmitting antenna aperture big enough, then you can focus your beam quite strongly, and then you don't need a big receiving antenna aperture, yes? So in principle, you could do this. Yeah, in principle, you could do this. But this is one of the, let's say, visions that we have. I think more likely is that we can use it, for instance, to assist in the takeoff, for instance. Yeah.
Okay. Thank you.
Could I ask Ed to ask his questions directly, because I can't read that well?
Okay.
Can you hear me?
Loud and clear.
All right. I just was curious, for terrestrial applications, I mean, one of the trade-offs you've got is you go to higher frequencies, you're able to get much smaller spot size unless you use, like you said, focusing. How did you guys do the trade-offs between using lasers versus using microwaves for these different applications you've shown?
One second. So the question is why don't we use lasers or?
Yeah, I mean, for example, there's a lot of other projects that are looking at terrestrial power beaming networks for drones and things like that, especially in the US, that lasers are the favored way to get the high power density that allows you to hit that spot size, allows you to have more compact systems. When you guys did the trade-off as you're looking to this path to microwaves, why did you look at lasers and look at microwaves? And what were the trade-offs you considered?
I think most of the studies in the US are done for military applications, I guess. And then you don't care that much about efficiency, probably. While
yeah, you're right. It's generally power availability, but you know that is the path they're heading down.
Yeah. Yes. I mean, okay. Let's say right now at Airbus we are focusing on the energy sector applications. Let's say to transmit power. So we strive for the highest possible efficiency, and then there is. I mean, you have very low efficiencies for lasers. I know that you can scale down your aperture and so on. And it's let's say it looks very nice on paper, but the efficiency is not there. So let's say we don't.
Yeah. Thanks.
Thank you. Is there any more from the floor here? No, online, Jose? So again, thank you, Piotr. Much appreciated. So, okay, so this time I'd like to welcome in person again Dr. Vivek Babu, and he's a distinguished researcher and engineer, currently serving as the head of aerospace at Sol Technologies. He's at the forefront of developing perovskite solar cells for space applications. It's a project that involves collaborations with universities, companies, and space agencies. Dr. Babu's work focuses on the potential of perovskite, I'll get it right eventually, cells in low Earth orbit, and the process transfer from lab to fab at Sol Technologies. His expertise in the field of perovskite technology is well established, and he has a successful track record of managing projects that utilize perovskite technology in various applications, including Internet of Things and building integrated photovoltaics. His work in the field has led to significant advancements in perovskite solar cell research, with his contributions helping to push the technology to the forefront of emerging thin-film solar cell research. So, warm welcome to you, sir. I'll just start your presentation here, and we'll take the screen. There. And I need to share first before I do that. Video. With sound. Okay, let me do this. Okay, and here we go. Over to you.
Thank you.
And you got you can use this as well.
Oh, okay.
You wait. Thank you.
Thank you. Good afternoon, everyone. So my name is Vivek Babu, and I'm head of aerospace at Saulet Technologies, a company in Poland, and we are working on perovskite-based solar cells. So first of all, I would like to thank you for inviting me to the SpaceTech Alumni Symposium, where I to share my thoughts on the potential of perovskite solar cells for the space application. Space exploration has always been a testament to humanity's unending curiosity. We have hosted several missions, such as the JUICE mission, where we observe the planet Jupiter and its icy moons, and the James Webb Space Telescope, which is a huge infrared observatory orbiting the sun, which all gives answers to our questions of existence of universe and the history of solar system. So to power up all these missions, we need solar energy. And we know that sun is one of the largest solar energy in the space. And we can use the photovoltaics to convert all this energy to utilizing for electricity. To go a bit back on the history, like the first ever solar powered satellite is Vanguard 1, which was launched in the year 1958. And after the launches of Sputnik 1, Sputnik 2, and the Explorer 1. It consisted of 6 silicon solar cells harvested a power of 1 watt, and an interesting fact, it is still over there. And then going back to the future, like 1962, Mariner 2 was launched, which is the first successful interplanetary spacecraft, which is a flight to Venus. And it has a solar panel covering 5 meters to over 0.76 meters with 2 solar wings. And in the year 1998, we established the International Space Station, which is the largest solar array in space, consisting of 262,400 solar cells generating up to 250 kilowatt of power, with a total area of 3,360 meters square, with a power density of 75 watts per meter square. And then this year, 2023, we launched the JUICE mission to collect the data from Jupiter and the icy moons, which consists of a total of 85 meters square solar panel array. And this is one of the first ever built on the interplanetary mission. It consists of total 23,000 solar cells with the 2 solar wings. Now, I like to give an aspect of the record cell efficiencies of photovoltaic technology. As you can see, this is a chart I took from NREL with the cell efficiencies and the timeline over the year. So as a single junction with a single absorber layer, gallium arsenide-based cells have a record efficiency of 29.1, with silicon heterojunction have an efficiency of 26.81, and perovskite is quite close to silicon with 26%, and CIGS with 23.6%. And if you see the timeline, you can see the perovskite solar cells were like 10 years back was 3%, and it has exponentially increased like to 26 in a very short period of time. However, in the case of other photovoltaics, it took over 50 years for the development. And the case of multi-junction, gallium arsenide, 3 absorber layer, triple junction have an efficiency of 39.46. And recently, perovskite with a tandem with silicon, it got an efficiency of 33.7%. It's just to give an overview about the record cell efficiencies in photovoltaics. So now I like to talk a bit more about perovskite and what is unique properties to that. So perovskites are any class of material that has the crystal structure of calcium titanate, or it makes it forms of ABX3, where A and B are the cations of different sizes, and X is an anion, as you can see in this figure, in this picture. And then it has really amazing semiconducting properties, such as its high absorption coefficient, as you can see over the figure over there, when it's compared to other photovoltaic technology. And one of the main reasons for its high absorption coefficient is its optical transition. As in the case of perovskite, it has a direct-to-direct band gap, like optical transition. As in the case of silicon, it's indirect band gap, and a lot of energies are lost as phonons. And this is one of the reasons which have a high optical absorption coefficient, where perovskite only need like a thin layer to efficiently absorb the photons and convert to charge carriers. And another interesting factor is that we can tune the composition of perovskite, like changing the halides, and cations, and we can change the band gap where we can really fine tune which spectrum it need to be absorbed. That's why in this figure you can see a lot of colored perovskites. And another interesting feature is the solution processability. So we can mix the salts like the organic salt with the halide salt, mixes together in a polaric solvent, and then we can use any kind of solution processing technique such as spray coating by slot die coating or by inkjet printing. That's what we do at Saulet Technologies. As you can see, this is an inkjet printing process that we do. The perovskites are getting crystallized at room temperature with this brown, forming its dark brown shapes. And by utilizing this, the advantage of the processing, we can form different shapes and sizes out of it. And since it can be crystallized at room temperature, we can have it in a low-cost production. So just to give an overview about Saulet Technologies, it's a company in Poland pioneering research and producing new generation perovskite solar cells by inkjet printing technique on a ultra-thin flexible films. The company was founded in 2014 by Olga Malinkiewicz with two business partners, Artur Kupchunas and Piotr Krish. And now Saulet Technologies is a team of nearly 80 scientists, engineers from different parts of the world. So currently we have an R&D facility in Wrocław, and a kilometer away from the R&D, we have our first pilot line, which is an area of 5,000 meters square, which have a nominal capacity of 40,000 meters square per year that we can produce. And we can have a perovskite module with an area of 1 meter square. So this is just the production line facility, some pictures over there. So we have already been into the terrestrial market. The first one is on the Internet of Things, of powering up perovskite with the electronic shelf label, where we can change the dynamic pricing of it, and it is powered by perovskite solar cells. And then we also been explored more onto the automotive sector to powering up electric cars using like integrating onto the surface or through the roof. And another area that we explored is building integrated photovoltaics or building applied, where we can harvest the energy from the roofs or from the building walls. So back to the space application side, one of the interesting value proposition by inkjet printing on ultra-thin flexible film is its high specific power, which is like the power to the mass ratio. And this is a graph showing the specific power to the power conversion efficiency. And as you can see with here, like the 3-5 cells, even though it has a really high efficiency, the specific power is lower because of the processing. And since perovskite can be fabricated onto very thin film, like 10 microns, 20 microns, it can have a really high specific power. Another interesting factor is its flexible integration. As I said, like again, since it is on ultra thin films, it can be easily integrated to any curved surfaces. And another factor also, we can, since it is on the plastic foil, we can do some post-processing steps to cut out certain parts, and we can utilize the maximum area in the case of a CubeSat mission, like not covering up the sensors or anything. I also have like a demonstrator here of a perovskite module. As you can see, this is like fabricated from our line, and this is like super flexible, like bendable, and also the LED strip is shining from this light from this room. So if I cover it, and it's still working. So this is like, you can see how flexible it is. So we know that the space environment are super harsh. Like one of the main reasons for the solar cells that can get degraded is by ionic radiation, like electron, proton, or from the UV radiation as well. The atomic oxygen that can also result in changing degradation of the material properties. Also extreme thermal cycling ranging from -175 degrees to +130 degrees Celsius. Also like vacuum can cause outgassing of certain polymer materials. So, and also mechanical damages that can be caused by micro meteorites or debris, and also during the launch, like vibration or acoustic shocks. Also keep it in mind about the on ground in the storage position before the launch, it can also get reacted by humidity, moisture, etc. So this is one of the interesting work that have been done by NASA, where they tested the perovskite solar cells in the International Space Station, collaborated by NREL. And this is done on part of the MISE project. And they tested like the basic methyl ammonium lead iodide based perovskites, which was left over like 10 months in the LEO orbit. And then they showed the results, which shows that it was quite stable after the flight. And one of the thing got degraded is the borosilicate glass through the radiation, but we know that with Syrian dope we can mitigate this effect. And with this all of these features, like they also did another launch 2021, trying out the hybrid perovskite with the full device stack, which is quite interesting and showing the potential of this technology for space exploration. And in the case of our solar cells, we work on single junction solar cells. So it's just like one absorber layer. And we work on with the space grading materials, encapsulation. So far we have efficiency of 15% on the flexible foils. And with that, we have a specific power of 1300 watts per kilogram. And since we work on flexible foils, we can also bend these modules like to a bending radius less than 3 millimeter. And this is the panel size showing 8 centimeter to 4. We also did a lot of radiation testing. One is proton radiation that we collaborated with JAXA, and shows also like with 100 kilo electron volt, it shows its stability. And we did electron radiation, gamma X-rays, all shows promising results. With the neutron radiation, we collaborated with University of Rome, Tor Vergata, and it was quite interesting to see the potential of perovskite that getting resistive to the radiation aspects. However, there were certain concerns with the thermal stability. But in the standard, like methyl ammonium lead iodide based perovskite, it can be degraded but by elevated temperatures. But as I was mentioning before, we can play around with the cations and the halides, like its mixture of alloys. So we can improve its thermal stability by engineering on the crystal structure. And by that, like there is a work shows with the CCM lead iodide bromide based perovskite, which has a stability over 200 degrees Celsius. And in Saule, we also did thermal cycling with the following the IEC standards from -40 to +85 degrees, and it shows promising results. So with all this taking into account, we are planning a launch to LEO in the end of this year. And we partner with Satra, who is our satellite provider. It's also a Polish company. And with Astronica, so the Polish company helped us with the mechanical testing. And with University of Rome, Tor Vergata, we did the fabrication of those devices. In the mission, we want to collect the data in situ, like basically the sun intensity, the temperature, all those data to see in situ measurements. And this is a picture of our devices where we tested different architectures, different perovskite crystals, materials, everything. And then we have a payload where we can put 8 slots where we can test which one is the best performing or the best stable one. And one of now the most interesting topic with the space-based solar power of collecting the power in the space and then distributing to the Earth. So this the ESA specification. We got like the efficiency of 36% with a cell cost of €1 per watt and an array production capacity of 2 kilometers square per year. And with the state of the art, we already have like 29,000 like watts per kilogram with a efficiency with the tandem architecture of perovskite silicon have a 33.7%. And with Saule's current situation, we have a specific power of 1300 watts per kilogram with an efficiency of 15%. And the cell cost, which was calculated, like very estimated, is €5 per watt. And with the current pilot line production capacity, we have 40,000 meters square per year. And in the future, we are also building up a new production line with a capacity of 700,000 meters square per year. So this is quite interesting. And in that case, we also collaborated with Astronica, it's a company in Poland. They have a space heritage on design, development, and production of space mechanisms. And the idea is to have like solar rollout arrays with it. And it's very much like we also designed a possible configuration for the SBSP concept. where we had a solar array which is rolling out of 10 meter to 3 meter with the help of like metallic or CFRP booms, and can have a generation of 6,300 watts to around 8,400 watts, assuming the suboptimal efficiency of 15%. When we have the full deployed stack of 48 modules, we can have a power of 352.8 kilowatt. And by having this as 18 packets in a cylindrical shape, we can have in a gigawatt scale with 864 modules. By this, we believe that, like previously with the kilowatt, megawatt power stations, now with the future of gigawatts, and we believe perovskite could take a huge role in this and pushing to the future of. By this, thank you so much for listening to my presentation. Yeah.
So, is there any questions from the floor? I'm expecting a couple, actually, from the floor.
Of course. You mentioned that you achieved a 15% efficiency with a single junction. Are you aiming for multi-junction as well?
Yes, we are also working on multiple tandem architectures, but for the moment, the importance is to really test these materials for the space condition. But in parallel, we are working on tandem, but more for the terrestrial. But we can also, like, over the time, we can also test the tandem architectures as well for perovskite tandem as well.
Okay.
Since I told you, like the perovskite, we can play around with the chemistry and we can select the spectrum that it can absorb. So as in that, we can have the perovskite, we can absorb in the high energy spectral region and also low energy, and we can just combine as tandem. So we are working on that, yeah.
And what efficiencies do you think you can achieve?
But on the flexible foil, so far the record on small areas are 20 to 23%. Okay. Yeah.
So those 23% are for broadband spectrum?
It's for the record efficiencies on the small single areas, but is the record one in our lab we have around 19%.
For monochromatic.
Yeah, for a single junction, exactly.
Okay.
And
90%. Okay.
Yeah, exactly.
All right, thank you.
I just got, and can you print this? It's a basic print approach. Can you print it on every kind of material?
Yes.
You have it on plastic foils now, but it would be probably interesting to print it on structures for space.
Yes, so we can, like in the lab scale, people print on the glass, but we can also print on the plastics, also any kind of flexible substrate, just need to have like a primer coater, and then we can do with the help of, you can also be on the fabrics, on the paper, but to have like a primer polymer coating, and then you can do by some metal oxide with like sputtering, and then you have already the layers that you can deposit it directly.
Interesting, thank you.
Have you printed in a vacuum?
Sorry?
Have you printed in a vacuum?
So that's actually quite interesting thing, and we wanted to really do one of the projects that we are planning to really see if we can do it in the vacuum printing. There's a lot of challenges where we need to control how the droplets can fall, but we haven't tried yet, but this is something in our mind to do.
And what's the temperature range you can print in?
The temperature range we can print, we haven't tested like what temperature ranges we can print, but it's quite interesting that one topic that we want to try is how we can print in the space environment.
Okay, thank you.
Thank you.
Sorry. Any more from the floor? No? I did have one question for you. I don't know if you saw the discussion earlier on. Peter was explaining to get the scale, we needed orders of magnitude in terms of industrialization. And then there was discussion about reducing the price from the material, I think, with Matthias. I don't know if you picked up on that. What was your view on that? Do you have a position maybe?
Yeah, actually.
Because you build this, no? So
yeah. So as I was telling, like the process is very simple. It's not even complicated like when we do with the epitaxial growth of gallium arsenide or silicon. It's very simple that you if I say we can also do it in an office inkjet printer, that you just put the solution, you print it onto the foil, it just crystallizes at room temperature. So you guys can imagine what kind of complicated tools that you need to do this. So it's so you can see the operational cost is like bare minimum, and the rest is all about like how we enter with the market and things. So it's very, very potential, and like, yeah.
One last question from me. So one of the challenges is obviously the rare materials that go into the product. And it's not clear to me what rare materials you've got and how that could drive the price, you know?
Yeah, I mean, perovskite is very abundant in the earth. So it's like around 30% covering minerals. So it's easy available and it's easy to do.
Okay, so thank you again.
Thank you so much.
Thank you. So, another exciting session ahead of you. So here we have Dr. Matthias Krieger. He has a master's degree from the Swiss Federal Institute of Technology in Zurich and a PhD from EPFL Lausanne in Switzerland. He also has a degree in strategic marketing from University of St. Gallen, HSG. Matthias has over 20 years experience in business development in semiconductors, industrial automation, PV, terrestrial, solar, and precision optics. He founded and is the current CEO of Chrysol AG, founded in 2009 in Switzerland. I guess I need to switch you. Yeah. Got them. Oh, that was a different slide there. And I just need to share this screen. You've got animations, no?
No.
And you should be good to go. Perfect. And then you can just do that. Okay. Okay, sorry, I'll just don't know how I did that. Share the top one. Ah, my bad. Yeah, good.
Okay, so can you hear me? It's okay? And you can see my slides. Okay, thanks a lot, first of all, to ESA to the invitation, because I'm currently unemployed, so I'm actually preparing for a new venture soon. And this is a startup that I created many years ago. So it's actually a bit of a historic mixture of what you've just heard. It's an interesting, actually, direct comparison to the proposal with perovskite. So I think it's up to the audience to judge what is the better solution. There's a very long story behind this. And I am not a great visionary. Actually, I'm a hardcore technology expert, and I prefer to get things done. In my first job, I was in the semiconductor industry, and I was actually responsible for very high-speed die attach processes, which I implemented with advanced concepts, and they're still running 24 hours a day around the world. And I'm pretty proud of that. So I know how to get things done. And sometimes you need visionary approaches, but you also think on the way there, sometimes you need to do what is feasible and available today. Okay, so the company I talk about today is called Chrysol. It's like IKEA. IKEA is very, very primitive. It's only a combination of my name and solar. It's quite simple, Krieger and solar. But that was the only name available for the domain that I needed to register for the website. That's a simple explanation. Now, next slide is this one. The right one? This doesn't move forward. This should move forward. No, it's not working.
No, it's not working.
So where should I click now? If I go to the next slide.
The right one.
Oh, the right one. Okay.
Right is forward and left is back.
Okay, thanks. All right, so what is the purpose of this company? I'm not the only one, but I try to become a leading supplier for space applications that require highest power, and highest, I mean, not just a few kilowatts. If you talk about gigawatts, you should remember that the global space photovoltaic market, the annual market is around 2 megawatts, which is essentially nothing if you talk about energy industry. So you need to raise the manufacturing capacity by 3 orders of magnitude, which is really quite dramatic.
I would actually also like to enable disruptive high power applications by offering a very fast scalability, as you just heard also by perovskite, so there will be a head-to-head race between those two technologies. And I would like to eliminate launch costs from the critical path of all the space missions. So because I think if it's too heavy, space costs, launch costs become a very critical factor. Okay, so where's the problem today? The best state-of-the-art PV power, as you all know, are triple junction gallium arsenide modules. And as I mentioned this morning, gallium is a very rare metal, and China is the leading producer of gallium at the moment and has recently restricted the export of gallium to the rest of the world. So I think before you start to claim you can reduce the manufacturing cost by 2 orders of magnitude using gallium, I think you should explain where you get the gallium from. Okay, this is my personal opinion, but I think we can discuss this in the panel discussion. Gallium arsenide triple junction have very high efficiency, which I know, and I agree. It's very close to the physical limits. I think it's approaching 40%, which is the best you can get. But etching down of a crystalline wafer to reduce the weight has very severe physical limitations. I did my PhD in basic research in gallium arsenide heterostructures, so I know what I'm talking about. These wafers are extremely brittle. If you look at them too long, they break. And if you want to make a square kilometer size photovoltaic area with gallium arsenide, to me, it's just a nightmare to think about. I would much prefer something which cannot be broken. Alternative concepts like high power density, like stretched lens arrays or Fresnel lens, they have some design restrictions. I will talk about that in the next slides. So this is what you all know. If you have a crystalline wafer, if you have some meteorites hitting them, this is what you end up with. And pretty often this is a catastrophic failure. So you cannot just avoid a short circuit, even maybe of the entire module if you have an impact like that. What I propose later will eliminate this sensitivity altogether. So this is how it looks today. Now, what is the solution that I propose? In contrast to what we just heard in perovskite, actually, I propose to work with very mature, really mature technologies from consumer electronics. Amorphous silicon, I know, has a smaller areal efficiency, but is extremely robust mass production technology. It's a basic technology used for covering LCD television screens. So this flat panel display it's been deposited with exactly the same technology. So there is several, probably 100 square kilometers annual production area already installed worldwide in production. This is in production. This technology is more than 30 years old, very mature. What I would also propose, and this is actually the core of my startup, I prepared a legal joint venture with a very crucial NASA supplier in the US. So I actually propose a European-US joint venture. And this partner in the US is the only manufacturer of space-rated, optically transparent polyamide materials. This is a transparent film, which is space-rated by NASA for 20 years of stable operation in space. It's a fantastic material. It's transparent. And the aim is to replace the cover glass altogether with a foil. So you actually do not need any cover glass at all for the solar cells. So this is how it looks. This is actually a solar sail. Not a solar cell, a solar sail. It sounds the same. It's a solar sail. It's covered with aluminum. And it has a total area of about 400 square meters. And the total weight, including the carbon fiber deposit mechanism, including the engines, motors, the total weight is about 24 kilograms. I would propose to actually replace these aluminum foils with the thin film solar cells at the same weight. So in the end, you have a 400 square meter photovoltaic power array with a total photovoltaic power of 40 to almost 50 kilowatts at the weight of 24 kilograms. So the specific power will be at least 1,500 watts per kilogram, probably 2,000. With old technology, very old technology. So this is how it looks, a thin film structure. As I guess you know, you need to pattern these materials from the substrate. You have a film, you have a TCO, then you have a amorphous silicon photovoltaic cell. And the mass production technology is actually an industrial laser patterning step. The reason I'm here today is I participate in my former employer CSM, which is the technology provider for an OSIP program. So ESA has launched an open call for space solar power, as Arthur Woods also said. He participated as well. I participated in this, and I won one of the only 4 early technology development projects, which is a proof of concept to demonstrate the industrial manufacturing process step. And this is currently ongoing, but it's about to be finished in the next 2 to 3 weeks. And the reason I'm proud today is I can guarantee you today the industrial manufacturing process works one-to-one on this polymer without destroying it, even if it's only 20 microns in thickness. This is, in my view, a dramatic breakthrough for mass production. It actually works. You can really take an industrial mass production process and just copy them to this material, and it works. All you have to do is remove it from the cover glass after the production. This is what you can achieve. State of the art, I think, is around 200 for gallium arsenide watts per kilogram. In my proposed concept, 1,300 up to 3,000. If you can add a bit of concentrator, for example, external mirrors, you can probably reach about 3,000 watts per kilogram at the module level. The stowing density is at least 500 watts, kilowatts per meter cube, and the cost is significantly below 10 euros per watt, probably down to €1 per watt, I think should be feasible. So where did it all begin? I'm not going to go to the history, but actually it's quite an old story. It's almost 15 years old. This is a paper that was published by EPFL in Switzerland. And at that time, I was key account manager at Irving Solar. And I was responsible for the total cost of ownership model for large factories, PV factories using thin film technologies. I was the only one in the world who had access to the complete calculations, about 400 parameters for the industrial value chain. And I had contact to the guys at EPFL, and they gave me some figures, and I contacted the partners in the US. This is how the cells looked at that time. And then I put them in my model, and I almost fell off my chair. I still remember, because my model predicted the manufacturing cost to be lower than $2 or $3 per watt at mass production for a final photovoltaic module. That's 15 years ago. And I thought, this is quite good. If this is possible, then we should actually industrialize the process, because it's a straightforward process. However, there were a lot of political frictions, and I will not go into this. So it took me hard thinking for many years. And just to give you a few examples as to where I was involved, and this at that time was under NDA. I participated under NDA with the Pentagon in 2007. Actually, I was one of the initiators of the first look advanced study of space solar power by the Pentagon, by NSSO, National Space Security Office. This was actually also into a white paper by the Obama-Biden transition team. So I know that Barack Obama and Joe Biden, I think you know the name, know since 2008 what we're actually doing here. And at that time, it was confidential information. So we were actually quite optimistic that this could be moving forward. But that was just before the financial crisis. And that was a really, really dramatic halt to the innovation for more than a decade. Nothing happened afterwards. But I was actually involved at that time already with the US. Since then, have good relationships with US partners. And now, many years later, I try to propose something today, which is actually a very mature technology. And I know it's open for debate, but in my view, we're at the same tipping point as we had 70 years ago before we built the first nuclear power plant. If you think today about the safety discussions about nuclear power, do you think it would be allowed to build a nuclear power plant at a technology level of 1950 today? Not really. I don't think they would allow. At that time, they just did it because it was the first idea that worked, and they just did it. And I think we have the same problem here with space solar power. Should we keep raising the bar for requirements and specifications until we just never reach any goal at all? Or should we start working with what we have today? That's the question. Because this, what I propose here, is an industrial technology which is in production since 30 years, and it works. Okay, so where can we create advantages in space? Before you go to solar power satellites, I also tried to find niche markets, and I think there are two essentially pretty interesting niche markets in space. One is high performance, high power geostationary satellites with more than 50 kilowatts arrays, because this is much higher than current state of the art. And I'm in contact with some leading satellite builders in Europe, and they have expressed great interest, but this is of course still expression of interest and nothing concrete. But this of course would benefit the 5G, for example, infrastructure with high power satellites with much cheaper and much smaller, lighter weight photovoltaic arrays. A more interesting option is actually the Mars missions. I'm collaborating with a German startup called Neutron Star Systems. This is a leading startup from the University of Stuttgart, and they make superconducting coils and for high efficiency ion propulsion. And the combination of this with this PV array would let actually payload benefits for a Mars mission for almost 2 tons, which is quite expensive. So within 1 or 2 Mars missions, this entire development would be depreciated. Now, I make a small digression on concentrated photovoltaics because I know many of the promoters of space solar power satellites, they prefer either gallium arsenide or concentrated photovoltaics. But I just give you a very simple calculations. What would actually happen if you take concentrated lenses like this, put them in an array, they have a finite spacing. And then what happens if you use just standard, for example, glass, you need a hemispheric lens, then you can generate maybe up to 40% efficiency with the gallium arsenide cell, but you cannot arbitrarily move these cells closer than maybe a millimeter because of electrical connectivity issues. So I calculated what this yields, and this is quite interesting. Of course, you can get higher aerial efficiency the closer you move these cells together, but the specific power is actually constant. And it's very hard to go beyond 170 or 180 watts per kilogram, no matter how you do it. I can give you the Excel sheet with the calculations. You can do it yourself. But if you want to reach 2,000 watts per kilogram with an array of lenses, just because of the mass of the lens alone, this is probably not possible. And there's an additional challenge for space solar power, which I'm a bit afraid is not a good idea. That's the sensitivity to optical alignment. So if you have an optical high concentration lens, the angular aperture needs to be stable within 0.1 degrees. And an amorphous silicon cell is completely robust. It's even better under diffuse illumination than under perpendicular illumination. So even if you have some slight instability, it has no impact on the power. So this is something you should think about as well. If you talk about Fresnel lens array, same thing. If you calculate, for example, 1,300 watts per kilogram feasibility with enough aerial power density, you would arrive at a Fresnel lens thickness of a maximum 170 microns. And I'm not sure if this is actually realistic to manufacture a large area. This is extremely thin. But please do the calculations yourself and tell me whether you get the same results. This is an overview on the table of the performance. Of course, I don't have a lot of actual data on perovskite. I'm actually observing the perovskite development with curiosity as well. I think the efficiency is promising. The cost, I would say, as well. But from what I know so far from scientific publications, the space reliability is not yet where it should be. And it takes quite a number of years to actually convince the space community to have a reliable material for long term, 20 years, for example, use in space. I will not go into detail. This is, I think, you know what we are doing now. My early technology development project was chosen as one of 4 of the Solaris program. It's about to be finished in the next 2 to 3 weeks. And what I can tell you today, I cannot show you any results yet, but my colleagues at CSM tell me that everything as I proposed is working. So the process is stable and is reproducible on the polymer without actually destroying the polymer. And at least at the cell sheet level, we reach already in the lab 2,500 watts per kilogram. And if we increase the efficiency to 8%, it would be 6,000 watts per kilogram on the sheet level. And at array level, that would be about 2,000 watts per kilogram. Now, I also studied some markets. This is just for your side information. You can look in the slides. I'm not going to go into details. I'd like to found first space niche applications, and that seems to be pretty difficult because the only big space niche now is the constellation satellite from Starlink. I did some business calculations on the economic benefits of these cells. They're quite substantial, but you'd have to convince Elon Musk to invest in this technology. And at the moment, I don't really feel like negotiating that. This is a highly integrated concept with a fully integrated supply chain in the US. Okay, this is the competitive situation. You know that as well. Most leading suppliers are 3-5 triple junction. Then in Switzerland, there's this Fleesom is TUGraz. My company is not yet manufacturing yet. This is just a legal joint venture. Riga Solar in the US is producing crystalline flexible solar cells, etched down, and Celestial as well. I do not have any actual data on the perovskite, but we can discuss this later and see whether we got in the same direction. This is a roadmap, and I just give you the order of magnitude. Even if we started today, it would take 6 to 7 years, in my view, to have a reliable megawatt scale annual production, because I think this is pretty ambitious to go to gigawatts with a new technology. So I'd be curious to see that, but I will not make any claims in that direction. I've worked in the team of Oerlikon Solar more than 15 years ago, and they did exactly the same on glass. So I know what that takes. It took a team of 40 people for about 5 to 6 years to go to pilot line level, and this is a pretty demanding development. Okay, this is a potential benefit for Mars missions that I just showed you before. And actually the calculations are based on a paper published by NASA below. And I see that just using ultra lightweight photovoltaics with high efficiency ion propulsion would give payload benefits of about 2,000 to 4,000 kilograms. And since it costs quite a lot of money to put payload directly on Mars, this has a value of about $70 million for one Mars mission. So even if it put us just on one Mars mission, you could depreciate the industrialization in one project. Now, as a final slide, this is actually what it takes. What we currently do at CSM is I call it a space power pixel. We actually manufacture a pixel of a screen with a thin film technology based on a polymer. And if this process, the serial interconnection, is demonstrated, which I believe is feasible, the next step is just to make a screen instead of a pixel. And this is just copy, paste, using a different production equipment, using established technology. So I think this is a straightforward process. And I can prove in a few weeks that this is absolutely technically feasible. So if you master a single pixel in production, you can actually scale to gigawatt within a matter of plannable years with existing infrastructure worldwide. It's pretty ambitious, but I think it can be done. Now, I'm not going to go into details how the business structure will look, because this would have to be ultimately funded and customers in place. And these are the steps that need to be taken. The first one on the column left is about to be finished. This is the ESA project, which is currently ongoing. Will be finished in about 2 or 3 weeks. It's what's yet needs to be developed is the electrical contact integration on thin films. I propose to also consider potentially high temperature superconducting contacts to actually have higher efficiency. This is a bit of research to be done. The rest is industrial upscaling with existing production equipment. And to end the talk, actually, I just give 2 statements of crazy entrepreneurs. Steve Jobs, of course, you know, I mean, what he said once about 20 years ago, the people are crazy enough to think they can change the world are the ones who do, because who else could do it if not the ones who actually claim? So sometimes you have to be a bit too crazy. And I still think some of my friends call me crazy, but compared to other things I heard today, I consider myself still a realist. But because what I do is actually I propose something which has been done for 30 years. I just propose to go for combined mass production, which is still a challenge. So right.
So, thank you so much. Do we have any questions? Do we have any questions for Matthias from the floor? Go for it.
Yes, of course. So for the space business, you assume you could transfer could change the business in that way that the solar panels will be getting bigger and bigger, but more powerful.
Well, it's not the aim to have bigger areas, of course not. No. It's actually a penalty you have to pay. That's because every other aspect is far superior to everything that you know. I mean, I can manufacture probably 2 orders of magnitude cheaper than state of the art, quite sure. I think I can guarantee that. I can give specific power at least an order of magnitude beyond state of the art. I have excellent deployability because it's like an umbrella. I forgot to mention one additional property of this foil, which is excellent. It is very stable to micrometeorite penetration because it has a self-healing effect. So if you have like a small hole by a microgravity, it will just like melt, and it's like local welding, and it will not rip. So for small meteorites, these cellars cannot be destroyed, which is really quite unique. I mean, if you have that as a crystalline wafer, I think it's not that easy. So this is something I forgot to mention. Very robust to micrometeorites, yes. But area will be bigger. And the question is whether solar wind becomes a challenge for stability of large structure. That is something I cannot answer. Yeah, it's potentially a challenge. Yes, I agree. So it has to be studied by I would say, system architecture guys. Yes.
This would have been the resulting question.
Yes.
Another question. You showed the physical limits of other technologies.
Yeah.
Is there a physical limit of efficiency with your technology that you're proposing?
Probably. I was at Oerlikon when we actually tried to commercialize tandem micromorph systems, and that's a tandem cell, a double junction, a microcrystalline silicon, and amorphous silicon. And this, I think, is reached the physical limit of silicon-based thin film technologies around 12 to 13% efficiency. I think it's not possible to get much better than that. But the cost of manufacturing and the availability of raw materials is really absolutely, it's a no-brainer because it's a standard technology for consumer electronics. So the material abundance is absolutely is not an issue. And don't forget, you need a lot of manufacturing equipment to go for gigawatt. And these equipment actually do exist already on the market. Yeah. So this is a pretty strong point. For the short term, I think this is more realistic. For the long term, I think we need to be more visionary with new technologies. I agree. Yeah.
Okay, thank you.
Okay.
One question on the efficiency stability as a function of temperature. Can you tell us more about it?
I could, but some of it is confidential. I think as part of this project that ESA will get the results. Is deliverable is a detailed report on the temperature and other stabilities, and this report will be delivered to ESA. I'm not sure if I can talk about that because I'm no longer associated, so I would have to ask ESA, or you have to ask ESA whether they tell you. Sorry, maybe not. Okay.
Wrong department in ESA.
Yes. Sorry about that.
That's fine. Is there any more from the floor? Okay, perfect timing. Thank you, Matthias. Thanks a lot. Much appreciated. And with that, we're going to take a comfort break. I think you'll be pleased to hear. And we'll be back on the hour. We'll be starting again on the hour. It'll be 4 o'clock. So, great. He's the co-founder and Paraloon Chief Executive Officer. He completed his master's studies in aeronautical engineering with a specialization in mechanical engineering at the University of Brugge Ostend in Ostend, Belgium. He worked as a mechanical engineer at ESA in Estec here and gained experience in the development of photovoltaic systems for the ExoMars test rover. He has worked for the Swiss company Swisspop Technologies as a structural design engineer in the development of hyperloop structures and was a mechanical and robotics engineer for 2 years or more than 2 years at CERN. There he gained experience with vacuum testing and radiation exposure of services. Finally, and not least, he hopes to make a contribution to the space-based solar power movement with Paraloon. So, again, another person who's kindly come to the office with us today. Welcome to Robin. Please, Robin, take the floor. Thank you.
Thank you for the help.
Yay.
Okay. Here we go. Good afternoon, ladies and gentlemen. My name is Robin Nelen, and today I'm delighted to be able to present to you the Paraloon project on behalf of the Paraloon team. Paraloon was born during a space entrepreneurship course organized by the European Institute of Innovation and Sustainability in collaboration with Airbus, who has been presenting before. Since Airbus is willing to propel their planes with hydrogen in the near future, they challenge us to find new, renewable green energy sources to manufacture hydrogen. Airbus itself was testing a facility to beam energy wirelessly and create hydrogen on the receiver end at that point in time, as we just saw in his presentation. Today, there is a growing demand for clean renewable energy, generation for space, Moon, and Mars. Increasing costs, environmental impact, and geopolitical dependencies of fossil energies are problems which can be solved by space-based solar power. Space-based solar. Okay. It's just there's some delay. Okay. Space-based solar power for Earth in orbit and planetary usage may, oh my God, may hand the solution to these problems. Our team aspires to create a lightweight, inflatable, polymeric concentrator photovoltaic system or paraloon balloon structure for the collection of light and heat. Electromagnetic energy beaming could send the energy anywhere. The project could support ESA Solaris program on the long run. In orbit around Earth, 1.35 kilowatts a square meter is available in the form of sunlight. Today's solar technology is able to collect 330 watts a square meter in space. To generate 1 kilowatt of electricity, one requires a panel of 3 square meters. If one can collect 1.35 square meters into a focal surface by using a concentrator and convert it to electricity with a new thermal photovoltaic technologies, which converts both heat and light to electricity and has been proven to have an efficiency of 40%, then 1.6 kilowatts can be produced with the paraloon technology. Furthermore, the reflector or lens will be created from lightweight, inflatable polymeric materials, such as mylar, and therefore it would have less mass at launch, which results in fuel savings, a smaller bounding box, which results in more room for the payload of the customer, and would have a higher energy output per square meter. To build towards this space-based solar power dream, one should start small. First, we started to heat up water and small objects in the garden. Okay. We started to heat water and small objects in the garden. For example, there will be a video on the site. This moldy mandarin was heated up to 99 degrees at 10 a.m. in the morning in my garden. As I was tasked later on to do labs with my students at school, I decided to work around renewable energy. The paraloon team helped me to think about this test setup in last semester. We have been converting a large satellite antenna with aluminum foil, and the students have been creating their own temperature measurements with a PT100 and Arduino. The students learned a lot from this project, in line with their curriculum goals, and seem very enthusiastic about the project. From August onwards, Paraloon will be supported by ESA Big Belgium and will provide us with the opportunity to create simulations regarding technology and provide guidance to perform the technology towards a usable product. Next up, first, there is a small delay. Was the video visible? Didn't play. Okay. 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 Next up, the first team. First, the team will develop a concentrator photovoltaics on Earth with an inflatable polymeric structure and efficient photovoltaic technology. 2 prototypes shall be created, 1 lens and 1 reflector. CAD and simulation models shall be ready at the end of 2023, together with the first cheap prototype made from second-hand materials, which will be used for validation of the computer models. And of course, to learn our lessons in practice. In autumn 2024, the technical design shall be assembled and tested on conversion efficiency and validation for space environments. At the end of the incubation program, our team would be very happy with receiving TRL5 or TRL6. By the end of 2024, the final Paraloon prototype design 1 could be ready. The prototype 2 could be tested in space in 2025. This summer, our team will start in the lab, and eventually we could provide the system for usage on Earth in 2025. In 2026, Paraloon could deliver the first system to space mission and space constellations. Later, Paraloon satellites could be created to beam energy to Earth along with the Solaris program. Hopefully, around 2040, a Paraloon satellite network could beam energy to any place on Earth. Sorry. Inflatable structures. Inflatable structures such as a reflector, truss, and ring have been studied and used in space in the past. For example, reflector constructions and rigidation technologies have been tested in space before by Goodyear in the 60s and ESA in the 80s. NASA worked in collaboration with a company Larson on solar cell and inflatable antennas, which was tested on the Spartan 207 mission flown by the Space Shuttle in 1996. According to the final mission report, despite some problems at the deployment phase, the mission was successful and gave a great deal of information about inflating large structures in space. Then DARPA and Ball Aerospace developed a telescope with a diameter of 20 meters called MOIR for monitoring the ground on Earth. It was tested on Earth and planned to be deployed in space. It will be a lightweight space telescope based on inflatable structures. Nowadays, Beetlesat, a technology startup, produced successfully tested small inflatable Ka-band antennas for satellite communications. It seems that the wheel doesn't need to be reinvented, and a lot of lessons can be learned from the past. Thermal photovoltaics, as presented hopefully soon on the left, is a very upcoming recent technology which converts heat to electricity without having moving parts. The thermal photovoltaic cell will absorb sunlight, from which it converts it to infrared radiation, from infrared radiation to visible light, and emits it to a usable wavelength for photovoltaic cells. Thermal photovoltaics have been studied in labs around the world these days, for example, in the Fraunhofer Institute in Germany, and also in the National Renewable Energy Laboratory in the US. The TPV technology could be a game changer for energy generation in general, and for collecting energy from concentrated sunlight on Earth and in space. On the picture on the right, one can observe a Fresnel's lens focusing solar energy on top of a small selective absorber. The component transforms the thermal energy towards visible light, which can be converted to electrical energy. As you might notice, big cooling fans are placed below the unit that converts the energy towards electricity. This might be an issue for satellites because they can only be cooled by thermal radiation. A possible solution for this can be found on the next slide. The biggest issue that we might face will be the thermal challenge. Since thermal energy is collected, the satellite needs to find an equilibrium on the long term. The reflective surface is not heating up because the inbound radiation is reflected for 98%. The backside of this surface could be used to radiate leftover energy back into deep space. The ESA BIG Belgium program can support us with solving this thermal problem by providing us guidance and budget for software licenses to perform thermal simulations and create a digital model. Solving the heat problem will be the first step in the incubation program. If our test setup shows positive results, it could be used not only for space, but for applications on Earth as well. In the energy sector, in refugee camps, campsites, in emergency situations, or for research in remote places, for example, the North or South Pole. There, there are several opportunities to provide power on Earth. Nevertheless, for bigger amounts of energy at a constant rate and even on a cloudy day, the space-based application could provide energy 24/7 a day on a later stage. If this concept could bring more energy to satellites and space endeavors with a smaller cost in a small and with a smaller bounding box at launch, it could open unknown doors in the future. Okay. During this challenge-based course, a team was formed. During this challenge-based course, a team was formed. From right to left, one can find Marcin Sribitsky, Philip Jimmer, Roxana Dimitru, Paolo Lucente, and myself. All team members have relevant experience for the project, and without them, I wouldn't even be here today. Thank you for your time and interest. I hope to speak with you regarding this idea during the network sessions, and I always like to welcome enthusiastic people and organizations to build towards this dream. It would be wonderful if Paraloon could support ESA Solaris program one day. Teamwork makes the dream work.
Thank you, Robin. Stay. Thank you, Robin. Very interesting. So something a bit different from the rest of the day there. I'm wondering if there's any questions from the floor. Looking around. No, please.
Do you foresee any issues with concentrating so much energy in a single spot?
Yes, there will be probably a lot of issues, and this is what we would like to investigate in the incubation program. Yeah, this will be an issue. Yeah, but yeah, also a challenge, I guess. I hope so.
Anybody online, Jose? Okay, I do have one question.
Yeah, also to go further on this question, so we have this idea of also using the back surface, as I presented in this one slide, to radiate energy back into space. So yeah, we hope that this also can solve the problem.
Thank you. I've got one question. We've seen in the last few discussions on the technical side about this, I think Mateus called it a solar sail. And it looked very interesting that you've got this concept of this almost half a balloon in space, no? Have you thought about how you keep that structure stable, solid? Because if you keep it solid, it sounds to me like there's a potential dual use there, no? One for the reflector, another for the solar collector. I know, my stupidness here, but I mean, have you thought about the rigidity aspect of the Paraloon concept itself?
No, we didn't think about it yet. That's also why we would like to make prototypes, and this is also why we would like to start the incubation program. So, yeah, first we just had a second-hand dish to make some test setups and learn some basic lessons. And now, since we will be into the incubation program, we would like to put this model into the simulation software and also make some test setups. So this would be the dream of our team in the next 1 or 2 years.
I actually have a question that's my own question for once. I noticed you were using an inflatable structure as a reflector.
Yes.
But have you considered any more thought about actually concentrating on more the idea of the inflatable structures? Because we've seen a lot of presentations today about using different substrates for the photovoltaics or the solar collectors. And I'm thinking more towards like how something like the Bigelow inflatable infrastructure, I hope it's big, I'll maybe get the name wrong. The inflatable habitat allowed them to reduce the size for the launch of a structure. and seeing the inflatable structure, I'm thinking we have to build huge structures, and we've seen all these robots building massive metal trusses. Could that be a different direction that may be a bit more challenging or interesting for Paraloon rather than concentrating on a reflector?
Yeah, this could be this could be an option. Although I think, like, if you need to have robots to manufacture all these solar cells, it's going to be a very complex endeavor. And I think if we can make it more simple by just inflating a big reflector, which in the end, what we all would like to do is get a certain amount of energy from the sun and transform it into electricity. That's what we want to do. I was thinking, yeah, if we will build like very, very big solar panels in space with robots, etc., I think it's very challenging, and it's a very nice goal as well. But I think maybe this way it could be more simple, or this could be a different way which can be explored. I'm not sure, but yeah, if you can just expand the surface with inflation, it makes life easy, I think. But yeah, it's just the idea that
maybe it's something you to investigate when you go back to the company again.
Yeah. Okay.
Thank you, Jose. Thank you, Robin.
Oh, I have one question here. How do you deal with micrometeorite damage?
Good question. We've been thinking about it. At CERN, I was working with materials, polymer materials, and these polymer materials, they got more brittle, but also harder due to radiation. We did some radiation tests for that, and I believe that maybe due to this due to the radiation hardening of the material, so we could first inflate the structure, and due to the radiation hardening, we hope that it can maintain its shape. So this was one of the ideas. This was actually the idea. Yeah. Does that answer your question?
Yes, thank you.
Okay.
Okay, so thank you again, Robin.
Thank you.
Right, so our next presenter, it's not you, is Dr. Edward Tate. You're next, after this. And he's the CTO and co-founder of Virtus Solis Technologies, which is commercializing space-based solar power. Dr. Tate received his master's from Stanford and PhD from the University of Michigan. He is a prolific inventor with more than 40 issued patents and with more than 30 years of experience with transportation and energy systems. Since founding Virtus Solis, the team developed in-house simulations to predict the beam characteristics of kilometre-scale power satellites with billions of antennas. He is collaborating with the University of Bristol on an open-source SBSP simulator, which is planned for release next year. In 2022, they were among the winners of the Level 2 Stage 1 NASA What on the Moon challenge, in which they designed a solution to beam energy to over 3 kilometers on the lunar surface. Very similar to the lunar spark, I guess. Very nice. Earlier this year, the team built and demonstrated wireless power transmission across a football field with a prototype satellite and ground receiver. So it's not just Airbus doing it, no? Ah, but that was in the US, so there we go. We should have Dr. Tate online, so if you'd like to take the floor, Ed, over to you.
All righty. Let's get a confirmation you can hear me and you can see my screen.
555.
I can hear you. He's coming. Yes, we can see your screen and it's good to go.
All right, fantastic. All right, well, thanks a lot for having the chance to speak today. Get my screen set up a little bit more for myself here. and talk about the physics, the technology, and the economics we're looking at with space-based solar at Virtus Solis. So first, I'd just like to introduce Virtus Solis. We were founded 5 years ago. We've been full-time and funded for the past 2 years. And John Bucknell and myself are the technical founders. We've got decades of experience in startups, including John at SpaceX and myself with large hardware manufacturers globally in electronics and other hardware. We've repeatedly reduced timelines to convert concepts to reality in multiple industries. Now, I started my career in clean transportation. I worked on GM's first commercial electric vehicle and helped speed up engineering by the engineering pace we had by orders of magnitude. And I actually repeated this across multiple OEMs and industries. From our start a few years ago, we've grown to a team of 30 people who've already delivered our first proof of concept. And our focus is on simplifying the space-based solar problem to get to high volume economies of scale. And these economies of scale are the things that will let us drive performance improvements and reduction in cost. And doing it right, space-based solar should scale like electronics. Fundamentally, space-based solar is more like electronics than rocket science. While developing our power beaming proof of concept, we looked at solving one of the problems with lunar operations, which was moving power long distances. NASA didn't want beaming from orbit, so we had to look at how to do it on the surface, and we won the NASA Centennial Challenge Watts on the Moon Phase 2. And the challenge was how to get a lightweight solution that moved 3 kilometer power 3 kilometers from a varying power source and delivering it to a load at the end that was also variable. And we solved it with our core wireless technology and a novel energy storage system. And the reason I think this is interesting is because one of the things that we're looking at as we scale out renewables is the use of resources to put renewables on the ground. And the fact that this kind of a solution works on the moon speaks very highly about the fact that it's very resource efficient. However, our goal is not simply moving power, our goal is to generate it. So where we are today is we're on a path to trying to get rid of fossil fuels in the electric grid. When we look at what the reality is of this, we got two fundamental issues. One is we produce power when it's not needed. Number two is we produce it in places where it's not used. And this is a great chart that was shared, which shows you the capacity factor in Germany over the years for the solar generated there. And a key point is in the middle of winter, the capacity factors are tiny compared to the rated power of the arrays that are installed. And this means that you're going to be looking at storage and other solutions to try to deal with it. It actually means you're putting a lot of wind into the mix to try to deal with the intermittency of solar. And we take a look at this. Right now, the projections are 1 to 3 trillion being spent over the next decade or two in order to get the global energy storage in place to make up for the shortfalls. But this is actually the cheap part of the bill. The more expensive part of the bill is Bloomberg estimates right now that we're looking at like $21 trillion to be spent to do nothing more than move power from one location to another. And the United States is a good example of this because our population is pretty much concentrated on the coast, and you can get wind out of the ocean and bring that in, but that's expensive transmission lines underwater. You can bring hydro in from Canada, and that requires long distance high voltage lines. And you can try to move energy from the deserts and the center of the country out to these coastal areas. And it's just a lot of money to be spent on putting wires in place. Now, clean firm generation is the solution. And, you know, we've got a history of having a clean firm solution, which is nuclear. For reference, just a kilogram of mined nuclear has an awful lot of megajoules in it. That's a lot of energy you can get out of some dirt you bring up out of the ground. But the reality is we're not going to scale it. You know, there's a host of reasons for this, but, you know, right now we're looking at nuclear as not the option we're pursuing. So you say, well, it'd be great if we could find something that was like that. And kind of surprisingly, if you put realistic numbers into space-based solar, on a kilogram per kilogram basis, what you manufacture with space-based solar has as much energy over its lifetime of operation as the uranium you mine out of the ground. So that's a pretty good indicator. This is a good technology to pursue, and it has a massive payback. I mean, I know we've seen presentations today that have talked about it, but this is one that kind of helped me settle in that this is the right thing to do. And there's another problem too, which is efficient distribution is critical. And mineral efficiency is something that is overlooked a bit, but it's a huge consumer of resources. It will drive a massive amount of mining and resource extraction in the next couple of decades. And that's because moving power requires something on the order of about 12 tons of copper per kilometer you're moving it. With space-based power, it's actually two things. It's power generation and it's power distribution. And even if you take into account everything it takes to put that space-based solar system together, or space-based power system together, and put a receiver on the ground and put another receiver on the ground, it's an order of magnitude better just at moving something tens of kilometers, hundreds of kilometers, much less trying to move power continentally between a lot of different nodes. So this is another indicator this is the right thing to do. So space-based solar offers a scalable, firm, clean, and renewable power source that can deliver power at all times, all seasons, all weather, and all latitudes. And very critically, it uses less land, less resources, and less cloth, and it can be done at less cost than any of the alternatives. So at Virtus Solis, our aim is to provide that cheapest power and replace fossil fuels globally by providing solar power from space. So the first thing is a lot of people still look at it and say that can't work. And physics are the key part of it not working. Well, the usual reaction is you can't beam power from that distance. It's never going to work. The inverse power scaling means you're going to lose all that power. And this is mostly because people have nothing they can look at on the ground that they can see in their daily life, which is even a small scale version of what space-based solar is. The example I always use is my cell phone. If my cell phone's a millimeter away from my charger, it stops working. Now, besides the fact it's a different technology, it just provides that feeling that you can't make space-based solar work. If I can't do it at a millimeter, why could I do it from tens of thousands of kilometers away? Well, the first point to look at is the technology and the physics, or the physics have been understood since the 60s of efficiently moving the power. The technology was looked at in depth in the late 70s by NASA, and I like to go back to this chart that was buried in the appendices, where they quite simply put out what they're going to get for efficiency for the reference system they did. And even with 1970s technology, they were saying they could get an 80% technology, 80% efficiency, as long as they had a big enough diameter aperture. And this is the three key parameters you've got for wireless power transfer are basically going to be the frequency you're operating at, the aperture of the transmitter and the receiver, and the distance between the two. And the piece that is hard for folks to understand is that when you start with something which is a very tiny aperture, like a pinhole in a camera, if you put energy through a small aperture, it's going to spray everywhere. And the animation here in the left-hand corner tries to illustrate that. As you can see, it's starting with a very small aperture, the light goes everywhere, and then kind of counterintuitively to most of our experience, as the aperture gets bigger, that beam actually gets tighter and tighter. And this is one of the keys why this is a scale-enabled technology. It simply doesn't work unless you get the pieces big enough at the frequencies that we can get through the atmosphere, at the frequencies we can control with electronics. So with that, I'd like to talk about the technology, which is how do we turn these physics, and what have we done to turn those physics into something useful? Well, this year we did a power beaming demo. March 21st, we did a public demo in Indianapolis. We moved at 100 meters, which is the length of a football field. We moved 70 watts, and we also demonstrated beam steering. Share a few details with you. Just to give you a feel for what 100 meters looks like, that's our transmitter. I'm walking away from there. And then we're walking across the football pitch to get to the point where we're right in front of the receiver. So that's a pretty good distance to be moving power. It's not as far as we need to, but it gives you a feel for what can be done. And then just to give you a little bit of a feel for what it looks like from the air, this was our public kind of getting a chance to go out and inspect things. And you can see our receiver here off in the distance. Now, what we did is we built and operated an RF transmitter. So we combined 6,400 antennas into a steerable phased array. It's about 2 meters by 2 meters, and we did the work at about 10 gigahertz. And this was all done off of commercial off-the-shelf parts. So we did the antenna design ourselves. We brought in existing amplifiers, and from this we had to live with the bits and pieces, the challenges you get from using commercial things. But we were able to get all this together. We got 100 meters of energy transfer. The final number was actually 68 watts of DC power received, and we had that limited by some of the beam safety that we needed to observe. We also had software control of the 6,400 antennas, which gave us the ability to do beam steering and hit multiple targets. Now, we did development on this for close to a year. And what was kind of interesting is we had interns that were working with us, and we've had other people that work with us, and we had all the hard demos where we had things in the lab. We showed folks the power measurements. And the funny thing is, when you actually did it and we put some loads on and people got a chance to interact with the beam, so this is a low power beam one of our chief scientists is working with, it suddenly became very real. And it was like the oddest thing actually when our interns had a chance to interact with it and we showed them that we were actually beaming power and doing something useful. It became very, very real to them that power beaming is a reality. Power beaming is something that can be done. Now, there have been demos since the 1970s on moving microwave power. This is a great chart here from Paul Jaffe. It goes through the demos through 2021, so it does not include the Airbus demo on here, and you guys did a great job with that. But we added on top of it our demonstrations we've done to date. So we've now done 3 demonstrations. We've done a 1 meter, a 5 meter, and we actually stretched that one up to about 10 meters. And we've done a 100-meter demo now. And that's the building blocks that need to be followed to get to an MVP, which by the end of the decade is intended to bring power from orbit down to the ground and do something useful with it. But there's a lot of parts that are inside of a wireless power transmission system. So you start taking a look at what is the performance that's been done. You need to be able to transmit. There's a lot of information on there and a lot of information on what you can achieve with antennas and with transmitters, but the rectennas are kind of a novel technology. So right now, from what we found, from what we're able to tell from published results, we've now got, we think, the best 10 gigahertz rectenna that's been built. And we think that we can actually do better with it as we evolve that design. So that's an important part, is not only being able to do the amplifiers, do the antennas, coordinate it through software, but eventually bring it down into our loads and efficiently pull the power out of the rectennas. So this is a picture of our proof of concept. We have the transmitter here on the left, and we have the rectenna partially assembled on the right. We've got a lectenna wall, which was used for aiming things. We actually used a thermal wall in order to figure out how power was moving to get a high resolution image of it. There's a ton of things to look at in any wireless power transfer system. And so part of our characterization is meant to go through and take a look at all of the different attributes, characterize them, and then we've built out a development plan, which is to improve each of these terms. One of the steps that we had to take as we went through all of this was we had to go from working with external suppliers to doing work in-house. It took us from about a 6 to 12 week iteration cycle to getting down to 24 hours per iteration. This is one of the tools we had in-house. We did a lot of modification to it, and I'm quite proud we were able to build 10 gigahertz circuits that performed to spec using a PCB mill. The company that we bought from had a good mill, and we had to do the work to get the accuracies up to get the milling to work the way it should. We also did a lot of small scale production. So we had over 8,000 individual components that came together to build this 100-meter demo. And you're getting kind of a snapshot of our build area and things as they came together. Now, this is not where a final system is going to end up, because what you want to do is you want to have very, very good scaling. So this is showing you right now the idea of doing hypermodularity, which is you get one design to work. Once that works, you can start scaling larger and larger. The rectenna is the easiest example of that. And then you want to also do up integration. So this is my blank chip carrier, and this should have enough room on it to carry all the semiconductors that are needed to carry 1 kilowatt from the solar panels all the way to the ground. So part of the path that you've got to follow is not just getting the commercial shelf, off-the-shelf parts to work, but up integrating that, getting the reduction in size, the reduction in losses, and the improvement in the overall packaging and mass of the system. And so this is our target to fill in with chips that will then let us get a kilowatt into our 4th generation of hardware. Now, analysis is another key part of it. So figuring out what size your pieces need to be, how they're going to behave, and what's going to happen there, really reinforces it's going to take a lot of aperture to make this happen. This is one of the analyses here in the middle that we did for one of the operating modes of the antenna, and it's just simply showing you the different ways the beam evolves as it goes from basically forming up what's called the near field to getting into far field performance. And space-based solar power simulations are actually a challenge because they're so big. So just like we talk about scale on everything else here, simulating this is big. So we're looking at potentially billions of antennas. There's lots of details that have to go with each one. And just simply looking at describing that as terabytes of data. And these results are big. I mean, you're doing scales that go from centimeters to tens of thousands of kilometers for the area that the beam is moving through. And there's lots of use cases, and there's a lot more to be discovered. So like we mentioned, we're actually doing we've developed our own internal tools. We use those right now for the work that we do, but we're also doing partnership with the University of Bristol to bring a set of open source tools out. By the way, I'll put a quick pitch in. Anybody's interested in participating, please contact me, and we'll get you involved in the work group that's supporting that. Now, the way our in-house simulation codes work, just a real quick snapshot. Let's do things like look at the power levels we're going to push through our array. We can take a look at variations. We can look at how sensitive we are to things like power variation, phase variation. We can do the software control on it to see how it's going to behave. And sometimes those really pretty circles that we ought to get and the really pretty beams from real world noise from manufacturing variations don't come out quite the way you expect. And this is an important part of not just scaling up, but also making sure you've got a robust system. And so once you've built this stuff in a very modular form, I'll go ahead and put a pitch in for blue tape is like an RF engineer's best friend. It allows you to reconfigure things very quickly. So we were able to take our parts, reconfigure them to take a look at some novel configurations to see that our software worked under edge cases. This is an example here of a 3-panel design that we did. And if you look very carefully, you can see that we looked at the simulation. The simulation was predicting we get lobes that go off in 3 different directions. And then we were able to verify that we get those lobes when we looked at images off of our RF absorbing foam. With our big system, we also did the same validation, and it was really satisfying when we looked at the simulation we had predicted months ago of what the beam would look like, and we were measuring the beam that showed up on our transmitter, and the results almost lined up perfectly. But that was just a start. Once you've got the beam where it needs to go, or once you've got the beam focusing the power like you expect, now the next thing is making it move. This is some thermal images showing the beam hitting our target and then moving to the right with the simulations that predicted the same behavior above. And you can see that, not only do we move, but also there's a slight change in the shape of the beam, and we're able to predict all those results through the validation testing that we did. And this is showing you what the setup looks like for it, so you can get deeper insight into what beam steering really looks like. So we're simply looking at changing phase across the system. And by controlling that with software, you're able to take the beam spot, move it from the center of your target, move it off, and we have this ability to electronically move what we're doing. This is a 3rd generation of hardware, limited by what we can do with off-the-shelf parts, and the next generation is going to do a lot more than this. Now, it's not just enough that I can look at what happens on these proof of concepts. I need to look at what happens with the full satellite. So this is the latest generation of analysis codes we've generated. This is kind of hot off the presses. It's a couple of days old, but we're looking at optimizing a 2 gigawatt power satellite beam. And the optimization is being done against 4 billion antenna elements. And then with that, we're able to look at different approaches to getting the power in the distribution we want on the target, so we can minimize the size of the receiver and minimize the other issues that may be there. And there's another piece that comes with actually making this work, which is it's not just enough to form the beam, but you also have to get it to steer with high accuracy. You're looking at needing something that's on the order of micro degrees of resolution to come from 37,000 kilometers away and hit your target and not have the neighbors notice they've got something going on. So another one of our development paths is been getting retrodirective beaming to work. This is a proof of concept on our 1st generation of retrodirective beaming hardware. And we're very far along. We've already managed to beat the best published results by about 3 orders of magnitude. And we see a path to get all the way to where we need to be. So this being integrated into our system will let us hit the accuracy targets we've got and let us be able to eliminate that as a source of losses in our modeling. So putting the beams together with the other pieces that are available, one of the questions that comes up is like, okay, well, how good is this and why should we even do it? There's a lot of stuff here. I mean, we are going to start with more power in space than you have on the ground because you don't lose it to the night, you don't lose it to the atmosphere, you don't lose seasonal and weather. We pay a price because we have to push power through microwaves, which we've got conversion losses, and we do end up with a little bit of loss, but it's tiny compared to what you get for daylight moving in. And at the end of the day, what we can say is when you compare these two, we're able to come up with something which is about 6 times better in terms of receiving area to terrestrial usage. And that's really useful because it means that instead of using all the land and resources that are currently slated for going into renewables, we can pack that very, very tightly. We can site these systems more easily, and we've got less total resource usage. So this is an example here of taking one of the US solar farms. This is the actual solar farm here, building it out. So we took over more land to say what the solar farm would look like to get it to 2 gigawatts. And then we said, well, what receiver do we have to put down to match that? And we can put a receiver in that's got the 6x advantage, like we pointed out. And not only does it have that advantage, but it provides that power 24/7 rather than only part of the day. And this is important going into economics. So our energy solutions cost competitive. This is the Lazard's levelized cost of energy. Take a look at it. Photovoltaics, wind, those are the ones that we're coming in with right now. And we're looking at space-based solar based on like the Fraser-Nash studies and all that makes it competitive with photovoltaics. We think we've got things that will let us drive the cost even lower. And we think that will allow us to enter the market successfully and then grow into that market. And as economies of scale kick in, drop the price even lower. And one of the reasons is if you take a look at it, this is what demand looks like in the California markets. And you can see that here's the demand on top. This is a famous duck curve here, which is the net demand after solar. The reason the duck curve does that is because we have solar generation during the day. We have a little bit of background wind generation. The place where space solar can really enter is coming in at night. And we've got a system that would let us do that. And if you come in at night, you can get almost twice the price of energy. So you can take advantage, you can solve the problem of the high prices at first by taking advantage of them and using those to scale up. And that's a key part of the economics is there's massive dislocations in the grid in terms of power being expensive because it's not produced when it's needed, it's not produced where it's needed. Now, we have a first customer lined up. He's our strategic partner at Intersect Power. Our lead investor is Sheldon Kimber, who's got experience in building some of the largest solar farms in the world. And they've got a pipeline right now of putting even more renewables on the ground. But they recognize that the solar has its limits and there's things that can be done better. And so they're going to work with us to make sure that we can focus on getting the satellites built. They can focus on getting the power in the ground. The timeline we've got, I'll start with the business model actually. We're intending to build power plants and that's what we intend to sell. And the timeline that we're following right now is we've successfully hit our demonstration that we've been working on. We've got another land-based demonstration we're planning for 2024. That's going to be a kilowatt at 100 kilometers. And then we're looking to launch an orbital pilot, which we've got a site on the ground picked out and we're starting to do the preliminary engineering for. And then eventually moving by the end of the decade to having a demonstration minimum value plant that would actually be producing useful power and be available for usage. So that's a quick summary. Appreciate the chance to talk to you today. Anybody would like to follow up, here's our email contact and we'd love to hear from you. All right, any questions? I think I saw that Pete asked one, but I have trouble seeing it while I'm presenting. Okay, is there such thing as a software-defined rectenna? Is there a role for generative AI in the design of a rectenna? I guess I'll start with that question. So first one is software-defined rectenna. There is actually a software component to making a rectenna work. You really need to look at this. What we have is a system. So between the transmitter and the receiver, we've got to deal with perturbations from the weather, from the atmosphere. We've potentially got to deal with localized conditions that may mean you want to change parts that have gotten too hot or have got other things going on. So yes, there's room in there to have software that's interacting between the transmitter and the receiver to boost the overall efficiency. There's also load management on the back end on how you extract the power from the rectenna, which is going to be something which is controlled. So there's kind of these software defined things that, in addition to the base hardware you build, will improve the overall efficiency. Now, is there a role for generative AI in design of rectennas? Of course there is. You build the simulations are accurate enough. You can apply those kind of simulations plus design techniques to make the rectennas better. Although I will tell you a quick story. We did a lot of design work, and the antenna we've got, which is performing very well, in fact, it's performing quite well, pretty much came out of one of our guys that sat down with pencil, paper, and effectively 1970s techniques, laid out what the design ought to be, and taking an antenna we developed for our transmitter, plus those pencil and paper techniques, he nailed it. We had to do a bit of tuning, but once we tuned it, the design worked like a champ. So yes, there's room for it. As we mature, we get more validation data. I'm sure we will push more and more towards using a software and simulation to drive it. But you know, just having good guys that can think through problems can make a massive difference on how quickly you get stuff together. All right, any other questions?
So is there any questions from the floor here? I'm just looking around the room. No? Matthias?
I had nice presentation. Did you have a chance to actually estimate the efficiency of energy used to generate the microwave and the energy generated in your outdoor experiment? Just a fraction of the power that is transmitted.
Yeah. So we characterized all that. I mean, these early systems are always challenging because you're using off the shelf. I mean, we got about 40% efficiency with our amplifiers. Antennas were sitting north of 90%. The beam itself was sitting about 30%. I'll actually share one bit because I saw some of the stuff that was being presented earlier, is that there are things that can be done to do focusing and beam forming, but at the distances we were working at, it actually works out doing uniform beams. We ended up getting a lot more power out than if we had done anything else. We also learned some really hard lessons on rectennas. So our received power should have been about 3 times higher than what we were able to book. And that's one of the corrections we have coming up. Rectennas ran at about 80%, and the big gap we had in our system was actually the effective aperture we had for the rectennas. And that's on our roadmap to get corrected in the next demo.
Thanks.
Thank you. Is there any more from the floor? No? Okay. Thank you, Ed. Thanks a lot for the time. Try to figure out how to stop. If you click on the left, yeah, you have to do that, and then you click on the just click somewhere else. There you go. We still see.
Yeah, you still see me. I'm trying to figure out how to turn myself off.
No, don't worry. Okay. Okay, now we have the pleasure to introduce Dr. Alejandro Salado. He's got over 15 years of experience as a system engineer, consultant, researcher, and instructor. He is currently an associate professor of system engineering with the Department of Systems and Industrial Engineering at the University of Arizona. In addition, he provides part-time consulting in areas related to enterprise transformation, cultural change of technical teams, system engineering, and engineering strategy. He conducts research into problem formulation, design and verification and validation strategies, model-based system engineering, and engineering education. Before joining academia, he held positions as a system engineer, chief architect, and chief system engineer in manned and unmanned space systems of up to €1 billion in development cost. He has published over 100 technical papers and has been a recipient of the NSF Career Award, International Fulbright Science and Technology Award, the Omega Alpha Association's Exemplary Dissertation Award, and many other best papers. Alejandro is a member of INCOSE and a senior member of the IEEE and AIAA. So we're very fortunate to have him here. And he's going to take us out a little bit. We've seen a lot of technical, a lot of vision, a lot of things around space-based solar power. He's going to maybe take us out a bit to overall system engineering, because it's important to have the focus around that when we come up with these challenges. So at that point, I'm just going to start the presentation here. And I need to share this screen over here. No, I've done that wrong. I did that wrong again. If I do this, share, share. And now you should be good to go.
Yeah, that works. Yeah. Yeah, the other way. So now you know the tricks.
Somebody knows the tricks. It's just not me. Yeah, I always click the wrong screen. Thank you. Over to you, sir.
Okay, good. I may try to use this, but I'm not used to working with them. Hey, can you hear me? Okay, now with two hands, I'm not very used to. Yeah, so as John was saying, I'm going to change topic a little bit. I'm not going to talk about technology at all. I'm not going to talk about solar power. I'm going to go back to systems engineering. And I want to start with a question first. Who's an engineer in the room? Okay, who's a systems engineer in the room? Okay, some of you. Good. So I will start easy and then try to evolve a little bit the presentation. So are you familiar with this? Is anyone in the room familiar with this? Yes? Well, it's super interesting because I didn't tell you what F means actually. But okay, let's assume that it's force equals mass acceleration, right? And would anyone here challenge me that this is not true? Peter, maybe, right? But in general, we accept it, right? What about those? Are you familiar with those? Some of you can. Let's make it easy, okay? I mean, at the end of the day, we use the one below, and that's good enough. And if I ask you, do you know this? Would you challenge that? The answer likely is no, I would not challenge it. And if I would ask you, can you do mechanical engineering without the first equation? Most of you would not dare. If I ask you to design a circuit without using Ohm's law, probably you tell me you're crazy. We use that, right? Okay. So now if I ask you, what is the science of systems engineering? What are those laws of systems engineering? Then we're not that comfortable anymore. And as a matter of fact, I will not do a poll because I know there are some students here, participants, that have not graduated yet. But, oh, actually, one more, let me check something. I thought something was coming here. Oh yeah, I made a mistake. So I uploaded the wrong presentation, but it doesn't matter. So, so I'll say it in words. If I would ask you, are verification and validation distinct joint, disjoint sets? Are those overlapping? Are those, is one a subset of the other one? If I take one activity, will it be verification or validation? Is any verification activity also a validation activity? Are activities that could be both verification and validation? I will have not a uniform answer. I will have one that is probably uniformly distributed. And the reason is, well, we do not really know what we're talking about. We might have opinions about it, but maybe we do not have a way today to plug the equation that it tells us this is actually the right answer. Now, what did humans do before we had science and laws of physics when they wanted to achieve something? This is what they did, right? They danced around a fire, they prayed to the sun, and then maybe something happened, right? When we didn't have science, this was the approach. And my claim today, and I did a SpaceTech, okay, is that this is today's systems engineer, okay? We pray, we hope really, really hard that everything is gonna be fine. And then we dance with our teams, and maybe it happens. And usually we say, oh, yeah, I know, the project's overrun, it's late, but my project is really, really difficult. Okay, that's all we say. And okay, so this is the status, right? We kind of pray, and we have a baseline or a status quo in the understanding of systems engineering, or at least the common or traditional approach, which is a few common principles that probably we can all agree. There is a common mission, right? You have a goal and you try to pursue it. Think about the end before the beginning. How are you going to operate the system? How will you maintain it? Like life cycle thinking. We know about unintended consequences now. Every time you create a solution, new problems emerge, and you do not want to solve the wrong problem, right? This is why we do problem definition, et cetera, et cetera, et cetera. And the role of the systems engineer is someone that has experience traditionally, right? You have a scar tissue. You've gone through stuff, right? Like, you know, there is problems that you've experienced. And traditionally, you've got this T-shaped profile. I am an electrical engineer, if you're a mechanical engineer, it's hopeless, don't try, but you might be electrical engineer, aerospace engineer, and you have that depth, and somehow during your career, you develop a little bit of breadth, and you have that T profile, you are interested in other domains, you get an understanding of how the thermal subsystem works with the power subsystem and the structures and so forth, and you have that kind of profile that allows you to understand the different domains. And we could claim that more or less you act as a technical manager, right? You are responsible, we're the chief engineers, right? We're responsible for the engineering effort. And in this sense, we could even say you do not really study systems engineering, you grow into a systems engineer, right? That's kind of a traditional view. Okay, so let's take this in mind as a starting point, and then I'm gonna ask you two questions, right? So imagine, and I've not put here a satellite, but you can change airplane by satellite, that I would ask you, you need to conduct the structural analysis of an airplane. Would you take an electrical engineer or an electronics engineer, give them a 1-week seminar in structures, and charge them with the task? Would someone here do that? I mean, electrical engineers are really good. But probably we would say, are you crazy or what? You're going to go to college, you go through at least 4 years of your degree, you come and do something really tiny and really stupid to make mistakes, and maybe in a few years, I will let you do the thermal analysis for the airplane, right? But if I ask you this, that you have to write requirements for a system, and you are a mechanical engineer, and I give you a 1-week training requirements, go write it, what's the answer? And the answer I usually get is, of course, I usually get only 2 days of training, okay? And we do this and we assume, sure, why not? That's the status quo. If you read any report about success and failure in engineering projects, I yet have to find one report that says they didn't know how to calculate the mechanical structure of something. They say requirements were wrong, the team was a disaster, culture was poor. I yet need to find one single main cause that was, oh, we used Newton's equations wrongly. Okay, I've not found it yet. Actually, you will not even find technology as a cause of the problems generally. We didn't manage information correctly. We used whatever, the different units. We forgot, I think, Peter, you said we forgot the screwdriver inside of the satellite, right? These things are the ones that actually kill the programs, and yet we're happy with 1-week training in those things. So now my claim is, well, maybe what we do is not the best thing we can do. But then we have to, to keep us humble, we always come up with the answer, but we went to the moon. And we did it like this. So, we know how to do this stuff. We went to the moon. So what are you talking about? And what I'm going to say is that it is true, we went to the moon and we used this traditional approach, which interestingly is still the paradigm to educate every engineer in the planet. Okay, we use the Apollo as the paradigm of education, but many things have changed actually. And it is really interesting to assess or analyze what things have changed and how. And I'm going to start with money. And this chart is super interesting because of three things. And the more you peel the onion, the more interesting it gets. Number one, you see the peak, right? Well, that peak is NASA budget during Apollo program. And it is, and the purple line is adjusted dollars, right? So that's the one that is important. So we start already by saying, oh yeah, they had more money. But then we peel the onion a little bit more, and most of that money was Apollo. The money they have today is distributed across all the programs that NASA has. So it's not even just a factor of 2, it's way a higher factor because of the allocation to projects. But then I learned something super interesting once I was presenting this, and that was the end of my story. And I get someone from the audience coming and saying, you know what, my PhD has been on the Apollo budget and all that. You know, the super interesting thing is that at the end, when you look at 2018, that's NASA budget. When you look at the Apollo peak, it's what they needed. Because every single budget request was approved by Congress. So it wasn't their budget. Money was unlimited. Okay? Has anyone here worked in a project with unlimited money? I've worked in one, and it was amazing, right? I get there, training the space industry, saying like, okay, what's the budget? No, we don't have that. I'm like, what? No, cost is not a problem. Just figure it out. So already with this, the fact that in those days, money was not a constraint, you just go do it. It's a significant change with respect to today, in which budgets are extremely limited. But that's not the only difference. We have way more. We need to be really fast to the market, and I guess you've been sharing applications and all that, but the regulatory demands are way heavier than they were because we have their regulations plus every new regulation that has built on top, because the old ones don't go away. So we have enforced really heavy processes, but at the same time, we have to be way faster. We need to have really long-lived systems, but at the same time, we need to upgrade frequently because technology evolves very rapidly. We want to come up with new solutions, but we do not have time for learning. The qualification model has died. It's PFM, right? Now, what's the meaning of PFM? That you have less time to learn. It's really easy to say, oh, it's more cost efficient, blah, 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 blah. The reality is they're saying, don't try to learn so much, just go faster. We don't do that much prototyping, okay? But at the same time, we need more novelty, more novelty. Oh. Okay. Then we came up with this super nice idea of specializing, right? More companies, now you focus on this technology, you get much better at that. And we have competition, but suddenly we have contractual structures that we do not know how to navigate. Okay, so again, another conflict. High technological diversity, but again, more needs for integrations and maintenance. And then finally, increased agency, and agency is the capability of someone to take their own decisions. So think about intelligent systems, blah, 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 blah. And at the same time, we have less tolerance for fragility. If you have this one failure, you're dead. There is no infinite amount of funding or investment to keep trying, okay? So all of those things just change the context dramatically from where Apollo days were and what's our situation today. But yet our practice is what Apollo days were. So there is a misalignment. So this is why my claim is that this idea of I'm an expert in a domain, I learn a little bit about systems engineering, and I do a good job, doesn't work today, okay? So let's think about what is systems engineering for real. And then you go to Nkosi and you go CBOK, which is written by Nkosi, and full disclosure. Am I being recorded here, by the way? Okay. Just, will the recording be shared? Okay, so I sit in the board of directors of Nkosi, so I really like Nkosi, and these are the definitions. But it doesn't mean that I'm super happy. I'm just happy with the definitions of INCOSE. And this is how it's defined, right? Oh, systems engineering is this really nice thing that we try to be successful. And to me, I'm thinking like, who doesn't want to be successful, right? So does it mean that if you're doing mechanical, you're not thinking about being successful? If you're doing electrical, you're not thinking about being successful? So I don't really like it, okay? That's my perspective. And then I was trying to really think about, well, if I move out of the traditional view of I'm an electrical engineer, and then I just try to think about the life cycle, but really think deeply about what is it that I do as a systems engineer and why is that important, I started to try to define it differently or in a more rigorous way. The way this definition is built, which is really good, is by consensus. So you bring a lot of people together and you say who's happy with the definition or who is not really happy with the definition. And the end they say, well, can you live with it? And because many people can live with it, then they accept it. I try to follow a different route. So I looked at how are other engineering disciplines, how are they defined? And this is what I found. There are two patterns. Either you say, this engineering is the study and application of a phenomena, or this engineering discipline is the process to accomplish this engineering feat. Okay, that's it. If you really look at all the engineering domains, this is how they define them, and you can really classify them in two ways. So you have application agnostic disciplines, electrical, thermal, industrial, acoustic, blah, 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 blah. And then you've got application-centered engineering domains, mining, naval, aerospace, civil, and so forth, okay? And as I said before, the ones on the left are defined as study and application of topics. The one on the right is design and development of a kind of a system, okay? So what is it that we do? And for that, I'm gonna show a chart, and this is gonna be the most complicated chart of my entire presentation. No equations or anything like that. So when I really think about how an engineering endeavor happens today, this is how I see it. So we have this notion of expected value. That is why I do this system. I may, like today's symposium, it's all about we're gonna make a lot of money, right? Lots of profit and profit and profit. This is really cool being at ESA, where most of it is we don't care about money. This is about science and science and science. But that's another value that it could be, right? I just want discovery for the fan of whoever or for the future of humanity and so forth. But there is something that actually dictates why we're developing a system. And then you've got resources, and you allocate those resources when you develop a system. And you can allocate them in two ways. There is no other way. Well, you can, of course, steal money and defraud and all that. But in general, there are two things you can do with money. You can either choose things for your system. I'm going to put two wings. I'm going to use this solar cell. I'm going to use this kind of material. Or you can use the money to gain knowledge. I'm going to do a test. I will do an analysis because I don't know enough, right? And those things will, the decisions you make when you design the system, when you choose a material, will dictate what kind of results you will have, and the knowledge that you generate affects expected value. And that's a detail that I don't need to go into detail. And then, of course, you have limitations, right? There are lots of physics that we cannot break. We may want, but in general, you cannot break them. There are limitations in your team. You get what you get, right? And sometimes that's really good, and sometimes that's not that good, and you live with them. And if you think about it, right, you have those three elements. You have the why, the what, right? We design a system because we want to generate value, and this is how we build it. And at college, we learn about the product a lot. We do the equations and the physics and the blah, blah, and the blah, blah, and the blah, blah. But if you look at that, that's really tiny in the overall context. And we spend 4, 6, 8 years only learning about that. But we need the process because we choose what to do. And we need the business because we understand why. We need to understand why we're doing this, okay? And the beauty of systems engineering is that we play at the center of all of that. That's our job. How do I balance all of those things? How do I choose what to do so that it gives me the system that may maximize my business interest? That's our job. when you create an architecture, actually a requirement, why do we care about requirements? Because I want to make sure that I generate business. When I create an architecture, why do I create an architecture? I don't need it. Well, because if I structure it in this way, I can allocate effort in this way, and now this is risky, this is not risky, blah, 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 blah. So our work is really at the combination of all of that. And this is why this is my own definition of systems engineering. It's all about strategies. That's it, okay? An architecture is a strategy, a verification plan is a strategy, a set of requirements is part of your strategy because you're deciding what to address and what not to address. Choosing vendors is part of your strategy. Creating a flexible solution is strategic. We just do strategies, that's all we do. And for that, we've got a set of activities. We can do functional analysis to predict what it might do, and that's null information that I have so that I can act upon that information. And again, architecture, risk management, trade space, and all that. And now this is, okay, I'm doing okay with time. So this is when it's the mindset change. If I really want to do those things correctly, the way we learn them today is process-based. But as I said before, with validation and verification, in which we will not have agreement, it will happen with anything in this list. If I ask someone here to tell me what a requirement is and actually to identify, we will have disagreement. I'm already telling you, I'm going to disagree almost with everyone in the room. Okay? The only agreement might be among the SpaceTech participants this year because it's still fresh, right? But then in 1 year, it will be gone. If I ask you to identify an architecture, we will have disagreement because there is no commonality. But if you really want to do all of this in a really good way, there is some stuff that helps us. We have behavioral economics. There is a theory of knowledge, believe it or not. Okay, there is systems theory. There is psychology. There is not only statistics, but actual probability theory, decision theory, organizational theory. How much have we learned about those topics? Nothing. That's the reality. Lots of physics, really, really good. That, we don't cover it. However, all those elements that I showed about, you allocate effort and you do this and you do that and you instruct your team how to behave, what you want them to do, how they're going to react, they are driven by those elements there, and we don't learn about them, okay? So now what's next? And this is why we need a change. If we really want to improve in the context we have today, where you have all these different factors that we did not have before, if we do not have those theories there or concepts, ideas, methodologies, there is no way we can navigate the problem space, I claim, okay? So what's next? And with this, I'm open for questions. So what are we doing in the field to improve upon this? And it is really interesting, actually, to look at historical literature, because there was a time in the 50s and 60s and 70s where some people were trying to create this theory, science of systems engineering. That book is called Model-Based Systems Engineering by Wayne Wymore. He founded the first department in systems engineering ever in 1961 at my university. And it was called Model-Based Systems Engineering. There was not even a tool at that time doing that. And if you try to read that book, good luck, because it's all math and all that. I've tried like 4 times. I'm going to try this year the 5th one. Let's see if I can go beyond. But there are actually lots of resources out there that at that time were not usable because of computer power. So when you look at those, they died because they were not implementable at scale. But, reality has changed now. We have a lot of papers coming in from the academia and all that. So there are things that we're starting to do, but we also have barriers. And I'm going to focus on 3 barriers. Number one is, who's doing this? It's too few of us. In academia, there is almost no researchers doing systems engineering work because agencies and companies, they do not fund that kind of work. They like technology, technology, technology. Now, the other one is education. We do not get enough education in systems engineering, let alone all those other things that I mentioned. So that's one barrier. We do not have enough people that is versed and educated in the topic. The number 2 is what I call illumination. Because this is kind of novel. We have a lot of illuminated people coming new to cozy and to all that, right? They come suddenly, it's like, oh, I see systems everywhere. I see them. And they are super well illuminated, and they don't try to learn from the past. So they try to come up with their own things, and we have a circle that does not evolve. And then finally, we have impatience. And here I'm talking about industry and corporate world. Oh, we need to fix this. MBSC, buy many licenses of SysML, not train the people. They don't need to know. Just buy the tools. Let's go for it, okay? And those are actual barriers to do good systems engineering. So what can you do about that? Well, this is my recommendation to finish. Number one, get educated. Not that I'm promoting SpaceTech here, but that's a way to start. And also read, because there is a lot of stuff out there that you can learn about and improve, but with one caveat, also be critical about what you read, because it is not that like mechanical engineering. Our field, even if it began in the 50s, it's still in its infancy to a great extent. So much of the stuff that we're working with is extremely volatile. And with that, I'm open for questions. I think, yeah, I'm good with time. So I managed that. Any question? Yeah.
Thanks for the presentation. You mentioned many interesting subjects that should go into the systems engineering field. Have you thought about ways of developing new systems? Like for software, it's common to use agile development frameworks. I am thinking about this for systems engineering because this is for me an interesting approach to maybe develop things faster.
It's a great question. And because this was the short version of the presentation, there are some slides that will have fit that. So I go to the same issue, right? So this is the impatience. So now you get software projects that are very specific in how they're organized and how you can resource them. And they're really successful with Agile. So what do companies do? Be Agile. So now they buy Agile for everything. You need to go to the restroom, be Agile. You know, everything works like that. And the problem that I see, they hire a coach, we give you some training, we try to adopt the methodology, and we're going to be milking the cow enough until I have the next methodology, right? Because you will realize it's not working, and that's, you know, as you expect. My personal opinion is that it is important to understand what aspects of those methodologies work and why, right? So you get Agile, for instance. Why does Agile work in those specific projects? Number one, you can allocate tasks to every engineer, right? You have all the software engineers and computer scientists, and any task in your project can be allocated to any person. Can you do that in a hardware project? No, because you cannot suddenly take, oh, now we need to do the structural analysis, who is free, the electrical engineer? No, it doesn't work that way. So that's number one. But there are things that work. Sprints work. Why do sprints work? Because psychologically, having a deadline, you have this inrush of adrenaline, and the sprints work really well. So my opinion is that you want to understand why, what aspects of those things work and why, and then you replicate them. Another example I have is the, you know, because otherwise you fall in the trap of symptom, but not cause. So I guess you've read this, Amazon forbids to sit down during meetings, right? Have you seen that? And then a company says, awesome, I'm going to be equally successful. Now, no chairs in my company. We do meetings just standing up. We're going to be Amazon. You're not going to be Amazon. It's not because they stand up at meetings that they are who they are. So yes, I think we should train, but with care. There is no silver bullet. And when you get into actual systems, there are many things in other domains like software that make it simpler in certain ways, and we cannot just take those. I hope I answer your question. Yeah.
What is your opinion in terms of, because you mentioned research in systems engineering. Yeah. How do we do research in systems engineering?
You come to my department to do a PhD. That's what I was told when I did the SpaceTech, and actually I did it. But you can do research. I mean, if your company sponsors you to do that, you can do it. If you want to go to a university, there are some universities in Europe also that have started to do research in systems engineering. But there is. I tell you what the difficulty is, to be honest. I think there are two difficulties with research in systems engineering. Number one, or 3 difficulties actually. Number 1 is number of faculty members, too few. Number 2, number of students, too few. Why? Because systems engineering is still a profession that you learn when you are in industry, not that you go directly. So if you have not been to industry, you do not even know that it exists. So when we get students, it's like, oh, I don't know what systems is. I'm doing electrical or this or robotics, right? And even understanding the value that the discipline has, you need that scar tissue to start. When you teach systems engineering to an undergrad that has no work experience, it's an interesting experience because they don't get it. They're like, you say, well, if you want to solve a problem, you have to do a requirement. And they're like, of course, right? Everything seems obvious to them because they've not suffered certain things. So those are 2 barriers. And then, is a question or did I stop? A question? Okay. So I think those are barriers because it's difficult to access someone who is in industry and tell them, either you do the PhD on top of your job, so you know SpaceTech. I thought a PhD was going to be just longer. I was really wrong. So, it's a huge effort. Or I tell you, well, you have your loan and your mortgage and all the stuff. Just live your life and come to do a PhD at college. And you're like, yeah, I'm not doing that. So it's difficult. But if you're interested in, we can certainly talk because it is important, I think. You had a question? Yeah.
We have a question from online. I'm going to read it out, so bear with me. Thanks, Alejandro, for your presentations. As a student, I had to be a system engineer in a team of over 50 people. For helping me, I used the ECSS manual, but even the NASA handbook manual and the SMAD. I found them useful, but of course, I noted my complete ignorance in the field. What do you suggest to me as necessary for this T culture structure you talked about? Are there some books you suggest? This is from Paolo Lucent, who works on the Paraloon team.
Okay, so a few things. So number 1, I think it is, so the first thing that I always recommend is read as many books as you can, because there are many ways, there is no common science. So when you read different books, they present the material in a different way. And I believe when you read many, many books, you start to really conceptualizing in a better way what makes sense and what not. If you cannot read many books, I recommend 1 book, and Wiley's here, which is the Applied Space Systems Engineering. I think it's really the best book in systems engineering out there by far, and not because Wiley's here. I genuinely believe that. It's an awesome book. So if I can only choose 1, I would do that. The problem with ECSS and the COSI handbook and the NASA handbook, probably the NASA handbook is the best one, is that they are process documents. So they tell you what to do, not how to do it, okay? And it's good to know what you have to do, but if you want to know how to do it, you need to go to a textbook, okay? And then there was one more question, I think.
What do you suggest me to have necessary to foster a T culture structure?
To foster a T culture. Okay. I have a paper on T structure, but I'm a strong believer that we have to go away from T structures, I think. So I believe that, so first of all, not everyone needs to have a T shape. It's not necessary. So that's number 1. Number 2, I don't think you need the depth of the T. That's why I don't think it's necessary. I've not been, and then the discussion is when you look at every systems engineer, they all have a T shape. But my belief is that they have it because there was no other way to grow into a systems engineering position. You had to have a T because that was the only thing you could do. I don't believe you need that. I think you need the breadth. Not the breadth from the perspective of knowledge on everything, but I found that having a good understanding of first principles of other domains is a strength. I don't need to understand about structures, but I need to understand that if you hit something, that thing distributes forces. Just to put an example, Yeah, no, I mean, you're raising the question, so.
I've got one question for me. One more question, Alejandro. And this was from me. And it's probably from a senior engineer who's been a system engineer for too long. I frequently have to deal with the outside world. And when we get asked what's a system engineer, or what they think system engineer is, we get told they're like people who install Windows computers. Or we get told we're too broad, we don't know how to deal with you. How would you suggest we change the worldwide perception and not just in our own little system engineering field?
I've been recorded, Jose. That's the only thing I can say to that is I've been recorded. I think the naming will eventually change. I don't think that problem, for instance, in the US is so strong because the presence of systems engineering it's very strong. I believe that in COSI is helping breaking that. So I don't think we will have that. In terms of the breadth that you mentioned, my position is that in the past, and because how we were trained, there was a mischaracterization for systems engineers in which you would say a systems engineer is broad, it is a generalist, and it was really good for me to understand what it was, but today I don't believe that's a good way of characterizing. A systems engineer is deep in systems engineering, right? So it's simply saying, oh, I'm a generalist. No, you are not a generalist, you are detail-oriented. It's only that you're looking at different kinds of details. So, and I will share one experience with that and I'll stop it there. But this was really eye-opening back in the industry. We were working on a set of requirements for an instrument. And I remember I was one of the few trained in systems engineering. And of course, you know, you try to come up to the requirements, you go to the experts and it was an optical instrument and you have everything chosen down to every single material, right? And it's like, I mean, we don't even have the requirements yet. So I'm trying to figure out the use cases. And I go to the experts of the mission profile and I say, well, I want to know if there will be any time in which the instrument will receive light while it is being powered off, operational condition, right? And the answer was awesome. They say, oh, Alejandro, that's a detail. And I thought, that's really interesting because for them, the material is not a detail. The operational condition is a detail, whereas for me, the material was a detail, the other one was the generalist in me. And then I figured out, well, it's not that we're generalists, it's we're detail-oriented, but on different kinds of detail. And I believe we need to start reshaping the conversation into what it is that we do. We're not just managing, we're really understanding operational conditions, defining the problem, strategizing, and so forth. And with that, I'll leave it here. I'll be happy to talk to you later. Thanks for the overtime in the Q&A. Thank you, John.
Many thanks, Alejandro. So, very nice penultimate presentation of the day. I see nobody's asleep, which means it's been a very good success to have Alejandro here. So, can you move it forward one slide for me? It's going to play some music, and then if you click. Okay, so now, more entertainment for you. Now you're all relaxed at the end of the day. So our last presentation of the day, let's bid a warm welcome to some very tired, but very happy SpaceTech Masters colleagues who are here to give us a short overview of their fantastic space-based power solution. Fresh from their exploits of the last 18 months, these two gentlemen are representing part of a larger team who are here today. Nathan Wittenbrook, sorry if I didn't say it properly, is currently the Orion Software Integration and Verification Lead in the NASA Johnson Space Center in Houston, Texas. Prior to this, he worked with an integration and verification team for the ISS. In the late 1990s, Nathan was a software engineer specializing in cockpit displays, I'll say that not too quickly, within Rockwell Commercial Aircraft Division. We also have Nuno Santos, who is a scientist for Philips Research based here in the Netherlands. His work is currently focused on emergent sensor technologies, including the industrialization of critical to safety sensors and functions for complex medical products. His passion for space has been a constant, and he worked first within the ESA Estec, so here in his premises, Control Systems Lab, and later as an engineer in the Space Systems and Engineering Department in TU Delft. Sirs, if you would like to take the stage for our final talk of the day, and I'll just set you up for your presentation.
Should we do that?
handheld?
As you want.
Well, thank you for that nice introduction, and thank you for sticking with us till the evening here. We'll see what we can do. So, humanity is going back to the lunar surface, and we're going as eventually inhabitants, but first we're going to be exploring and prospecting. But the first things that are going to do that prospecting and exploring for us are going to be rovers. And they're going to face some pretty big challenges. The biggest one is the lunar night. It lasts 14 days. It's very dark and it's very cold.
No, on shed.
Do you want me to stop? I'm in the middle of my story. It's very dark and it's very cold. How cold, you might ask? It's so cold, your lithium-ion batteries are freezing. Your rover is dying. And there's no light. You need power. And you've got 2 weeks. So you might think, okay, I'll explore the lunar surface during the 14 days of daylight. Well, this is a picture of the Shackleton crater on the South Pole. And as you can see, the sun angle on this photo is very low. The shadows are very long. And this is how it stays for 14 days as the sun just bobs along the horizon, casting these long shadows. In fact, the interior of that Shackleton crater never sees light. And that's good, because that's where we think the resources have been preserved. So as an explorer and a prospector, you need to go into the dark and find those resources. So this is a big problem. We have to solve the problem of the lunar night. So we've got a closer look here at the Viper mission that NASA's doing. This is a chart that I've modified from one of their presentations. And they've got 4 major constraints to their mission, sun illumination being a big one. And when you put these 4 constraints into a Venn diagram, you end up with just these limited areas that are available for exploration. And they chose this site up here as their place to explore. So when they land, you can see on this animation that you're going to see an orange arrow that represents their rover. And I'll start the movie here. They land and they pursue immediately to this dark region of the map, which is where the permanently shaded regions are. And they work and they work and they work. As you can see, the gray, which represents the shadowed regions, are changing incredibly dynamically. So once the shadows start moving too much, they have to retreat to a safe haven, and they just wait. They're waiting through an entire lunar night cycle on a hill so that they can continue to get sun on their solar arrays. And then you'll see as the lunar night retreats, they traverse back to the working site and start working again. So if you break down this whole mission, 58% of their time they're spent in a safe haven doing no work, and 23% of the time they're just traversing. So only 19% of this about 400 million euro mission is spent actually doing work. So that's a big problem. And Lunar Spark is the answer to that problem. We will beam you power from space. And you're asking yourself, well, what is Lunar Spark? Well, Lunar Spark is the theoretical company that our SpaceTech CCP team formed to solve this problem. We were 10 individuals from different backgrounds and different places around the world. We were given the challenge of creating a business that would be profitable in 2030 in the lunar economy. So a pretty big challenge. And Nuno and I are happy to represent the work of all these people that have contributed. So what were our mission objectives? First one, we needed to deliver the power. And we decided that in order to survive the lunar night, if you're this big Viper rover, you need 80 watts of continuous power. Number two, we wanted to provide an end-to-end solution. We want to be integrated with your rover so that you don't have almost no work to do. All you do is end up getting the power. Third, there's no lunar positioning system around the moon. We need to find you and detect you and localize you and be able to put our beam on you. Lastly, we had to define a service area. Most of the resources that have been hypothesized are around the poles. So we've chosen to target the south pole of the moon as our service area. And as the lunar economy increases, we want to be able to scale with it and continue to provide for more customers and bigger customers. So what do we sell? We sell power on demand. That's our main product. We give you power where you need it, when you need it, anywhere within the South Polar region. We sell you a Lunar Spark receiver, and then we help you to integrate it and integrate your mission around our power provision. So how do we accomplish this? We've seen some of these technologies today, and don't have to convince anyone in this room probably that space-based power beaming is the right solution. But we evaluated it based on mobility and its capability to work in darkness. And we also needed to create something that had a multi-mission infrastructure to it so that we could use it for multiple missions and extend the current missions. Now, here's where we kind of diverged from some of the things we talked about today. We considered laser and we considered microwave. The reason we ended up with laser is many of our customers are going to be small rovers. So that means incredibly small receive apertures. We chose 75 centimeters as our largest receive aperture. So for that reason, we ended up with laser-based power beaming. So this is a high-level look at our system. We've got 2 satellites in our system that are collecting solar energy. We're beaming it down to the receivers that are on top of the rovers who are our customers, and we control it from the Earth-based ground stations. So this is an animation that we put together. This is a shot from a lunar reconnaissance orbiter. The blue on the surface indicates places where we think there are resources. These are the landing sites of actual missions that are planned. The Viper mission is number 2 up here, and that Shackleton crater picture is number 4. The outer diameter of this region is the 80 degrees south latitude. It's about a 600-kilometer radius, or diameter. And the yellow represents our polar orbit. We're at 700 kilometers, which gives us a 3-hour period with 2 satellites. We have a satellite flying over every 90 minutes, and you get a 15-minute drink of energy every 90 minutes. So what are the challenges? I think we've talked today about a lot of the challenges of space-based power, and we have very similar challenges to what you guys have talked about. The good thing is we're delivering a lot less power. 80 watts is much more achievable than the megawatts and gigawatts that you guys were talking about. So we have our 75 centimeter receiver. We need to create the beam to put on top of it. We've got the pointing challenges that come along with beaming a narrow beam from space. And we have to have a high power laser, and we have to deal with all the thermal. And now I'm going to bring up my colleague Nuno to explain a little bit more about how we deal with those challenges.
All right, Nate, thank you. So we really went deep into the design, but given the time constraints, we'll just scratch the surface on these details, and hopefully not the surface of our receiver. So what is this receiver? So it's something that you will integrate in your rover, and the main functions of this receiver are essentially receive optical power, convert that optical power into electrical power, store it, and then further distribute to the customer's load, being it a science payload or whatever they want to do in the lunar surface. To achieve this, you also need to have some sort of beacon to communicate with our spacecraft. And of course, you also need to send some sort of information on the status of the batteries, because we will have multiple customers, and we need to send, or we need to choose which customer now needs energy. Now, looking a little bit into the spacecraft, we will have a spacecraft that we estimate to have roughly 3,000 kilograms, and we'll measure 2 meters by 2 meters by 3 meters. You can see this 3D printed model here, scale 1 to 50, if I'm not mistaken. And the spacecraft itself has quite some challenges. We have a pretty much standard bus, and there are a few subsystems that we will like to talk about, namely the payload. That poses one of the main challenges, the thermal, that's another challenge, and the pointing. We're happy to answer any question related to the other subsystems, but we'll focus on these 3. Now, here we have the payload concept, double redundant, and we have the lasers, the laser module, the laser receiver. There is a steerable mirror that will be able to steer the laser beam. Here we see pretty large radiators, and they are driven by a mechanically pumped loop with ammonia. We estimate that the payload will have a mass of 233 kilograms with the dimensions that we see on the screen. Now, this laser has to be something special because it needs to be quite powerful. I will not go into the details here, but suffice to say that we selected semiconductor lasers because of their lifetime, and we are essentially combining multiple of these lasers into a single beam to achieve an optical output power of 12.8 kilowatts, which is quite significant. But that means that, and considering an efficiency of 30%, it means that we have a thermal output in terms of thermal load of almost 30 kilowatts. We also chose the wavelength to be 445 nanometers, but I will not go into details on that. Any questions are appreciated. Now, how to deal with this 30 kilowatts of thermal load? Well, you have to have a pretty good thermal system. As I mentioned, it's a mechanically pumped loop based on ammonia, and ammonia was selected because of its low density, and it essentially means that we have a larger volume for a lower mass. And of course, due to its thermal properties. And we end up with a wingspan of these radiators of 14 meters. So essentially it works, we pump the loop towards the radiators, they radiate outwards, and with a valve we can essentially control and select what kind of temperature our system will be subject to. The last challenge is the pointing. This is a really big challenge. In a nutshell, we have coarse pointing and fine pointing. The coarse pointing will be based on an RF beacon. We essentially need to locate the receiver on the lunar surface, and for that we use this RF beacon that the receiver contains. And for that we also use the spacecraft attitude control system. So the spacecraft will steer towards the expected position of this rover, and then for the fine pointing we will use a 4-quadrant topology on our receiver, on the photovoltaic cells, to actually measure the received power that the laser beam is sending. This, however, works with a cerebral mechanism and a spiral looping. So we call it a spiral scan with a defocused beam. So the idea is that we don't use the full power of this laser, we start to do a spiral scan, and as soon as the receiver detects, it will close the feedback loop back to the spacecraft until we track, and then we are able to follow this rover. Then, how do we measure effectiveness of our system? Well, there are a few parameters that we looked at. We'll just touch upon a few of these. One is power in darkness. Again, going back to Nate's story on the Viper rover, if they're operating in the darkness, well, bad luck. They don't get anything. They have solar panels. However, if they have our system, they will get the required 80 watts to survive the lunar night. Going back again to their mission breakdown, well, this means that we will end up with an increase of their mission lifetime. So they are not required anymore to move away or chase the light anymore. So they can just simply stop, wait for our power, wait for the lunar night to pass, and then they can continue their mission. So that's, I think, great value, which allows them to have bigger flexibility. In terms of flexibility, well, you can also have mission extension, because obviously, if you can just simply wait and survive this lunar night, you can simply extend your mission. In this slide, we simply want to point out that the sun or the light conditions are not driving the mission anymore. Your hardware will be driving that. If you can survive longer, well done. You can perform more science. Now, a little bit on the business side, because we did have to go quite deep into the business. A couple of slides. So our potential customers are robotic missions and small rovers due to their low energy needs and the expected number of customers. That leads me to the study that we referenced. So PricewaterhouseCoopers, they predict and forecast an increase in the next 10 to 20 years, a very large increase on lunar actors, which by the way, it's not a coincidence, our strategy closely follows. So the idea is that we will start our Lunar Spark company in 2023, and up until 2030, we'll have our first generation of satellites. So 2 satellites orbiting the South Pole, and on the second generation, around 2035, we will have a second generation of satellites. So 2 more satellites to increase our operation capability and surface availability. What are our business phases? What did we consider? How are we going to execute this? Well, the first 3 years, we expect to have some terrestrial demonstrators and potential even cooperation with some other companies that we could eventually have space demonstrators as well, because that will allow us not only to raise confidence on investors, but also prove that the technology is feasible. But why do we need to raise confidence among investors? Well, because we will need quite some funding, especially for this first manufacturing of the first generation of our satellites. After that, we expect to have our launch of our first generation on year 7, and we will be also busy from year 8 to year 10 building our second generation, and then a launch on year 11. So we estimated the business case for the first 15 years, but here only the first 11 are shown. Well, very important now, the cash flow. There's no company if there's no money. And here we see that the company stays afloat for the whole duration of the 15 years. And essentially, here we see that we don't go negative. There is some money that is required to actually build and manufacture the first generation. But very important here is the company will rely on its own revenues from year 7 onwards. So that's very important. What we also see here is, and maybe for the investment people, your investment multiple is between 11 and 13, which means that depending on the point that you start investing in our company, you will get a higher or lower return. In both cases, the return rate is quite high, so around 25 to 26%. After that, we are not stopping, so the third generation will be in the works, and not only we expect to improve capacity, but also the capabilities of the satellites. Now, Kubrick said it well. However vast the darkness, we must supply our own light. Lunar Spark will bring you power, lifetime, and flexibility to your missions. Thank you. So, any questions?
We have one online from Sid.
From Sid?
From Sid. This is why I'm concerned. Sid, this is your project. What are you asking?
Traitor.
First of all, great presentation. How did you arrive to 80 watts? And do you think your system is capable of delivering you that power? Sid, if they can't answer this, we're taking back your degree.
Well, Sid, thanks a lot for the question. Well, I think you already know the answer, but yes, we think we can deliver that power. We have a couple of backup slides. Maybe we can explain it.
Backup slides. Yeah, so we interviewed several stakeholders and we studied the Viper mission to come up with the 80 watts for the large customers surviving the lunar night. The smaller rovers, their survival power needs are much lower, so we could probably power many different smaller rovers to survive the night. But 80 watts is also a good number to keep the smaller rovers working during the night if they wanted to. So that's how we centered it on the 80 watts. And as far as delivery capability, we have 2 lasers on each satellite. Each laser is capable of delivering the 80 watts, and we have 2 satellites. So there's a lot of redundancy in the system. So I think we'll be in good shape for delivering the 80 watts. I don't know if I want to go through that slide.
Does this answer the question?
Sid says thank you. I'm assuming.
Sid has heard this slide be presented 6 times. So, any other questions? Thanks, Sid. Okay, Leon.
What is the total efficiency of the system?
Yes, we can. We worked a little bit on that, and I can run you through a story. So we did analyze the end-to-end efficiency model, and I will go through it very quickly. So here we see the sun and the moon. In orange, you will see optical power. pink electrical power and red thermal power. We have our satellite. We considered some initial maximum power point tracking losses from the sun to our satellite because we don't have a perfect pointing. We assume solar efficiency, the solar cells efficiency of 39%. Part of it is lost into heat when it's being converted between optical energy to thermal energy. And then, of course, from the batteries and the electrical power system, we need to provide some energy to the laser. And here we consider an efficiency of 30%, although this we expect it to improve in the next few years. Then on the moon, we have one of our customers with our receiver installed. In between, we have free space. Our satellite is orbiting at 700 kilometers, circular polar orbit. And here we have our laser beam down to the lunar surface. And here we consider two very important losses. One is geometrical, because we need to be able to point very accurately to our customer, but we will have losses. In fact, we account for 86% of losses. And finally, actually, we had a question, we discussed it a little bit earlier in one of the presentations. Well, we do think that lunar dust is a very big challenge. It's such a big challenge that we did account for 10% of optical losses in the last few meters and 35% on the last few millimeters. From here, this energy is absorbed and transferred to the lunar rover. We account for a photovoltaics efficiency, which are tuned to the monochromatic wavelength of our laser. And we account for 90% of our customers' electrical power system. And finally, unfortunately, we don't see it here, we end up here with 80 watts of survival power. So in total, to Leon's point, we have, let me see, as only a 0.4% end-to-end efficiency, but it works, and we did account for all the different losses in the whole chain-to-chain, which is something that not every time whoever tells you the story, it's accounted for. So really consider every single loss in the chain. Our satellite has an efficiency of 8.6%, and the laser 2 receiver efficiency is 1.4% because of the free space and all the divergence and all the geometrical losses. Does this answer the question?
Yes, thank you.
John, go ahead.
On a couple of previous slides ago, you had this dust effect on the rover.
Right.
I don't know if you can pull that slide up very quickly. And I know I think you were leading this, so that's why I'm asking you.
I'm not sure if we have that slide here.
The
John.
one just 2 slides ago.
On this, on this. On
You
the
just
back
showed
of
it 2
the
slides.
back 3 slides.
Yeah.
No.
This one?
One before. No. Okay. Efficiency slide, exactly, yeah. On the middle of that,
all right.
you had two numbers, yeah.
This
10%
one, yes.
last few meters. But
this, yes.
Yeah, but doesn't that get worse as time goes on? Like we saw on Mars where the solar panels got more and more dust. Surely that's going to affect these as well over life. Now, how do you manage that with your solution?
You want to answer? I do. I want to answer. Well, we also looked into that. It does get worse. There are several effects. So although the lunar surface seems rather bare, there's quite some dynamics going on there. One of the most interesting ones, I would say, is if this lunar regolith is subject to ultraviolet radiation, it's being positively charged. And as the terminator line goes across it, there is some sort of voltage potential that will swirl lunar dust up in the air, and this can go up to a few meters. So every single terminator that goes on, you can see it almost as a rolling wave of lunar dust being deposited over. There's plenty of other effects that you can read a lot about. There's a lot of testimonials from the astronauts from the Apollo and all sorts of issues that they had with seals, with scratches, not being able to see equipment. There's really plenty of information there. We did study a little bit on how to mitigate this problem because we don't want to have our receiver covered in dust. So for example, electron beams is something that is being investigated today. or electromagnets or permanent magnets. Just to give you an idea, with electron beams, if you subject a flat surface of 100 seconds, and it's covered by this dust, roughly 80 to 90% of this dust is simply gone. And what's left is a single layer of dust, which is very difficult to remove. Yeah.
Thank you, Nuno. I do have another question, probably for the students in general. So you've seen today a number of presentations on different areas, technologies, techniques. Did it give you any pause for thought in terms of, maybe we could have used that, or maybe even reinforce some of the decisions you made? I mean, I don't know, just your feeling maybe, just from today's session.
Well, I think you look at the efficiency model here and you can tell we would benefit from more efficient transition from the solar energy to electrical energy on the front end. And it was interesting to hear about all the megawatts and gigawatts when we're talking about watts. So the economies of scale and things like that, we could benefit from other people pursuing those avenues as sort of we could be a side beneficiary of all that efficiency gain. But we can't probably drive it with our pretty specialized use case here. Did you have any?
Maybe we are really interested in the peroxide technology.
Yeah, I thought that was pretty cool.
Thank you. And I've got one last question, but more about the course. So I think we know it's a difficult course. It's very challenging. It's a huge amount of work, thousands of hours work. You have no family for 2 years, it's clear. But why would you recommend this? After you've been through, you've suffered, as Wiley said at the beginning, you've got scars now. You know, you guys have got scars now. But there's people online here, young people online who will see this. Would you recommend it? Would you say suffer it? And why would you say suffer it?
I would absolutely say suffer it. I started this program with no European experience whatsoever. And now I've got 9 excellent friends spread across all of Europe. And any amount of suffering that I suffered was definitely worth all of that. So thanks.
Well, I think besides that, which I think is a very important component, is just the experience, just the knowledge that you get from all these different experts spread all over Europe and the US. I think that's quite unique. And that's one of the things that, at least personally, made me join this program. And in the end, you also get a degree, by the way. So that's also pretty important. Just saying.
So again, have a warm round of applause for our presenters today. I think we only have time for a very quick question. I don't know if you can read that, but as we have seen and heard today, space-based power has been investigated since the 70s. There's been many studies, initiatives. Every 10 or 15 years, it comes round again with a little bit more impetus. Why do you think it's not been taken up, and what is stopping it moving? That's the wrong slide, sorry. But let's go forward. Why is it stopping moving forward, and why is it suddenly so relevant? I think that question's been partially answered, but just to take your last takeaways of the day, and maybe try and keep your answer for less than 2 minutes. So I don't know who would like to offer up a position first. Anybody from the panelists? Online, maybe? Wants to pick that up?
I'll jump in.
Go on, Peter.
Okay, so the first part is what's been holding it back. And quite frankly, launch costs have made it uneconomic. So up until SpaceX managed to drive the prices down, you could not make the economic case that would close to make space-based solar come together. Now, since the 1970s, what's changed is with that, obviously launch costs have come down. We've got in-space assembly now doesn't require having astronauts in space. Miniaturization means the loft cost for what needs to put into orbit is a lot lower, and the overall efficiency is a lot higher. So that's why I think this has suddenly changed. This is now on the forefront. And I'll add one other comment, which I think regardless of what happens, I think the price of making this happen will keep dropping over the years. It's really a matter of who's going to be the first mover that's able to make it happen.
I think I'd be a little bit harsher than that. I would say that, you know, we have lacked the vision, the constancy of purpose, and the moral courage required on the part of our public servants.
For the question itself, I think there are three reasons why this has not been picked up and why it's suddenly become relevant. I touched a little bit on that in my presentation. So one is that, you know, first of all, demonstration. So I come from the space policy and more of the academic world, and I do interviews across communities. And I think one of the biggest reasons technology gets traction is a demonstration followed by funding, and then, of course, followed by a policy program. So I think that's where space-based solar power really needs to go now. I think we already have a lot of proof of concept, you know, PowerPoints. We have a lot of engineering as well as scientific study as to that this is feasible, that this can be done. And now with the cost of launch coming down, it's even possible to build big satellites. So I think now is the phase where we need to move from the problem identification to the policy formulation stage. And why has it become suddenly so relevant? I think it's because countries like China, Japan, United Kingdom have suddenly picked it up. And because of that, there is state funding and state interest, and the technology is suddenly becoming relevant. Also, we had a demonstration, for example, a small demonstration by Caltech. I'll stop there.
Can I talk?
Please, please.
Yeah, I think it's actually the climate and energy crisis have come together, have created an incredible context and urgency to deploy space-based solar power as soon as possible, because we're up against some very serious challenges in the future, supplying energy to the world population, addressing the energy crisis. So I think that's what's really driving ESA and Solaris right now, but I think also the whole community.
So maybe as we've got a couple of minutes left, I mean, from the end of the day today, we've heard a lot of, obviously, a diverse set of presentations on technology, on what we need to do, on the positioning of it. What would be your, let's say, your personal takeaway of the day? Any messages you might want to give people who see this afterwards online, or to, you know, maybe to say, okay, if you learn one thing from today, what would it be? What should you do? So maybe I might pitch that to the guys here in the auditorium, just to give us a quick tagline, you know, a quick media tagline we can reach out.
I think it's very nice. What I see today, it's very nice that so many people are dreaming about this goal, and that a lot of people are, hope to make this dream come true one day, and it will inspire also universities, it will inspire so many people, and I hope we will be able to build on this somehow in the future. And I hope to see the dream come true one day, and I think teamwork makes the dream work. That's what I said before, and I hope we will find some collaboration as well between companies and the agency and etc.
Yeah, it says. I agree with most everything that has been said today, but I'd like to add two important points. First of all, we are beating also against entrenched political powers, for example, that support nuclear fusion. They attract 1 billion per year and do this for 30 years and still haven't made anything working, and they still get the money. This is what this is an uphill battle for us. We have to prove so many things before even getting funding that is really not so easy to achieve. The second point is, as I said today in my talk, there's a lot of know-how already around, but it's not in the same country, not even in the same continent, but it's there. So in my view, there is no way without international collaboration to get anywhere. This is my strong belief.
Maybe I'll open the floor up to our colleagues online. If any of you would like to give us a key takeaway of the day, that would be appreciated. Mike, please, we didn't hear from you in person, so welcome. Thank you.
Yes, I apologize, but being 6 hours behind, it was a little bit early to get up and give a presentation this morning. I hope you enjoyed it. Anyway, I would say that I think one thing we need now is we need a true international advocacy group focused on space solar power to bring the potential benefits and the dream really of transitioning the world from fossil carbon fuels to clean, true global clean energy by the end of the century, to give people some hope for the future instead of the despair that I think is growing around the world today. I think we can do that, but we need to bring that passion that we have for space solar power to our representatives in the government by explaining to them the path forward to make this a reality.
Ed, Namrata, Peter, any last words before we close the panel? Arthur?
Yeah, I think I would like to say, if I carry a tagline from the presentations I heard today, first of all, I was so inspired of such amazingly detailed explanation of different models. So the tagline I would say is that if I put out a media article, I would say space-based solar power is scalable and challenges this conception we had that there is limits to growth, given the fact that, as Abdul Kalam had said in his vision statement before he died, that the only technology that's going to enable 9 billion people to have a developed world lifestyle is space-based solar power. And I think that's the tagline I would put forward. It's inspirational as well as it seems very practical, given what I've heard today.
Yeah, I'll throw one out as a quick tagline, which is I think space-based power is the only solution that can deliver more power with less resources, less land, and less cost.
Andreas, you want to take it away? The last message of the day?
I think at the current moment, with all the constellation of technological development, launch costs, and energy crisis, the window of opportunity is really open, and that we have with SPS a kind of stepstone to become really a spacefaring species. And if we don't do it now, we're going to sit here again in 50 years and wonder why it was not possible in the 2020s to do that. So I think we really should push this opportunity, take this opportunity, and make it happen.
Thank you so much. And I think from everybody today, I'd like to express our deep appreciation to all the panelists who've come online and all the speakers of the day for all your efforts, the video team, everybody online with the coordination committee. So a hearty round of applause, please, for everybody. And I'd just like to thank everybody again, and we shall see you in 2 years' time at the end of the panel. Oh, sorry, Wiley, you've got one last.
Just thank you, John and Jose. What a yes. Buy a round.
So apparently now I have to buy a round of drinks. So thank you, everybody. That's the end of SpaceTech 2023. We'll see you in SpaceTech 2025. Thank you.